Hello everyone, and welcome to the section on machine learning. We'll start by looking at the Scikit-Learn library, which is one of the most popular machine learning modules in Python. And then we'll look at the definition of machine learning and some of its applications. And later we'll look at the various forms of machine learning algorithms. Here we have various categories of machine learning like classification, clustering, and regression. Let's see what the Scikit-Learn library is. Scikit-Learn, as I mentioned, is the most popular machine learning modules in Python. And here is the location of Scikit-Learn. We'll look at it in a few minutes. We are going to use Scikit-Learn library a lot in this section. And Scikit-Learn is dependent on NumPy, Pandas, and Matplotlib. We have already seen those. And we can install Scikit-Learn by using these commands: pip install scikit-learn or conda install scikit-learn. If you are using Mac, open up your terminal and simply type conda space install space scikit-learn, and this will install the scikit-learn module for you. And if you are using Windows, open up your command prompt and simply type conda space install space scikit-learn. And again, the dependencies of Scikit-Learn are Matplotlib, Pandas, and NumPy. Now let's look at the Scikit-Learn official website, which is located here. Here we are. This is Scikit-Learn's official website. And as I mentioned, it's a simple and efficient tool for data analysis. And it's free source, open source. These are some of the methods that we'll use in machine learning: classification, regression, clustering, and so on. So this is the home page. If you click on the installation, here we see that Scikit-Learn requires Python, NumPy, and SciPy. As I mentioned, we can install it by using this command, conda install scikit-learn. If we go to the documentation page, you can get tutorials, flowcharts, and various information regarding versions, FAQs, and so on. And if you go to the examples, you can click on any of these graphs and learn more about it. They have plenty of examples here. Here we have some general examples about classification algorithms, clustering. So they have lots of examples. And if I click on any one of this, you can read more about that example. We'll see some of this in our lectures, but feel free to explore the site and read about any of these examples or algorithms that you are interested in. Now let's go back and define what machine learning is. What is machine learning then? Here is Tom Michel's definition of machine learning. It's a computer program is said to learn from experience E with respect to some class of tasks T and performance measure P if its performance at tasks in T as measured by P improves with experience. So machine learning is all about learning from experience and applying what it has learned. Machine learning is the field of study that focuses on computer systems that can learn from data. So you'll see various definitions of machine learning. But all definitions of machine learning have one or two things in common, which is learning and applying what it has learned by building various models. So machine learning focuses on computer systems which can learn from data. That is, the systems often called models can learn to perform a specific task by analyzing lots of examples for a particular problem. For instance, a machine learning model can learn to recognize an image of a dog by being shown lots and lots of images of dogs. What does learning from data means? It means that a machine learning model can learn a specific task without being explicitly programmed. That is, the machine learning model is not given instructions on how to recognize the image of a dog. How does it do it then? Machine learning models learn what features are important in determining whether a picture contains a dog from the data that it has analyzed. Since machine learning models learn to perform this task from data, the amount and quality of data available for building the model are important factors in how well the model learns the task. We will learn more about models in future lectures. You will see how important the amount of data is in model building. If you build 2 different models, if one model learns on a data that contains let's say, 5,000 data points versus another model which learns from 10 or 20,000 data points, those models' algorithms are different, and you'll see some difference in their prediction. When you evaluate those models, usually the one that learns from more data points tends to predict better. This is in general, but it also depends on the quality of data presented for the models to learn. The use of machine learning allows for data-driven decisions to be made for a particular problem. Machine learning algorithms and techniques are used to build models to discover hidden patterns and trends in the dataset. This allows data-driven decisions to be made. Machine learning is an interdisciplinary field. It means it combines methods and techniques from various fields and subjects like statistics, math, artificial intelligence, and computer science, to name just a few. Here are some applications of machine learning: robotics, medicine, credit card fraud detection, handwritten digit recognition, face detection, and various forms of recommendations. Let's see some of the applications of machine learning in detail. Let's take credit card fraud detection. When we use our credit cards, the current purchase is analyzed against our history of credit card transactions to determine if the current purchase is a legitimate transaction or a potentially fraudulent transaction. If we make a purchase that's different from our common past purchases, for instance, if the point of sales location is from another country, then it will be flagged as a suspicious activity, in which case the transaction could be denied, or we may get a call from our credit card company to confirm that the purchase was made by us. You might have experienced this in one way or another. For instance, you might have bought a plane ticket from a different country's airways. For instance, if you live in Europe and make a plane ticket purchase from an airways found in, let's say, North America or South America, you might have experienced this. This is one application of machine learning, credit card fraud detection. Now let's look at another application, which is handwritten digit recognition. When you deposit a handwritten check into an ATM, for instance, a machine learning process is used to read the numbers written on the check to determine the amount of deposit. And as you can see from the picture here, handwritten digits are very tricky to recognize compared to typed digits due to the many variations in people's handwriting. You can check it out here. So this is one application of machine learning. By being presented lots and lots of examples of these different variations of handwritten digits, a machine learning algorithm learns and recognizes those digits. Another application of machine learning is in recommendation systems. When you buy an item on a website, let's say clothing for example, usually you'll get a list of related items. You probably have seen this. Customers who bought this item also bought these items, or you may also like this based on a certain purchase. So this is a common application of machine learning used in sales and marketing. Another application of machine learning in recommendation systems is Netflix, for instance. If you watch a certain movie, Netflix recommends a list of other movies based on the movie you watched, or you might see people who watched this movie have also seen these other movies. So you'll see those recommendations like that. So those are applications of machine learning. We'll look at recommendation systems later on. So these are some applications of machine learning. Just to recap what we have learned in this lecture, we looked at the definitions of machine learning. Most of them focus on learning from data. And we saw some applications of machine learning. In the next lecture, we'll look at classification of machine learning. Thank you, everyone. Hello, everyone, and welcome. In this lecture, we'll look at classification of machine learning. In general, a machine learning problem can be assigned to one of the two broad classifications, and they are supervised learning and unsupervised learning. Let's start by looking at what a supervised learning is. In supervised learning, we have data with a set of features, and our goal is to predict where the object will fall given the set of features. We are given a data set and we already know what our correct output should look like, having the idea that there's a relationship between the input and the output. Let's see some examples of supervised learning. One is predicting car price. We all know that the value or price of a car depends on certain features like mileage, consumption of diesel, model of the car, year of the car, condition of the car, and so on. So these are features, and we try to predict price based on these features. Generally, a car that has a higher mileage tends to be cheaper compared to a car with low mileage. And car price depends on the model of the car, year of the car. Usually, cars made in recent years tend to be more expensive than cars made in previous years. So those are all the features that will help us predict the price of a car. So price in this case is called what is known as a target. We try to predict the target based on these features. Another example of supervised learning is predicting house price. And a house price depends on features like number of bedrooms, square feet living, lot size, location of the house, whether the house has a basement or not, number of bathrooms, and so on. So in this example, house price is the target, and we try to predict house price based on features like number of bedrooms, number of bathrooms, square feet living, lot size, presence or absence of a basement, location of the house, and so on. Regression and classification are some methods used by supervised learning to predict values of our data. Let's see regression and classification. The following are examples of regression: predicting score on a test, determining likelihood of a drug's effectiveness for a patient, and predicting amount of rain. Some examples of classification: classifying tumor as benign or malignant, predicting if it will rain tomorrow or not, determining if a loan application is high risk, medium risk, or low risk, and identifying sentiment as positive or negative. We'll see classification and regression in detail, but I just wanted to give you some examples in regression and classification. And regression and classification, as I mentioned, are methods used by supervised learning. Now let's go to unsupervised learning. In unsupervised learning, there is no learning of data features. We will be discovering data features given the data. That way we can find similarities between objects of interest. In unsupervised learning, we approach problems with little or no idea what our results should look like. Here, data is presented and the algorithm analyzes and comes up with similarities by clustering together similar data features. And by analyzing the data, unsupervised learning tries to find out some structure of the presented data. K-means clustering and nearest neighbors are some of the techniques used in unsupervised learning. Let's see some examples of unsupervised learning. Identifying areas of similar topography like desert, grass, forest, and so on. Determining different groups of weather patterns. Discovering crime hotspots. Recommending items based on purchasing history. So those are all unsupervised learning. Now let's look at the machine learning process. So these are some of the techniques that we apply in any machine learning algorithm. The first step or process is acquiring or obtaining our data. And once we obtain our data, we explore and process our data. This will involve understanding our data set. We try to see if there is any trend or correlation in our data. We see if there is any visible outliers by visualizing our data set. Those are all techniques in exploring and processing our data. After that, we have data cleaning. In data cleaning, we see if there are any missing values or any duplicates. If that's the case, we remove those missing values or duplicates. And the next technique is feature selection and selecting techniques. So once we learn and process our data, we deploy what features to study to analyze our data. For instance, in the previous example, we mentioned that predicting a house price depends on features like number of bedrooms, number of bathrooms, area where the house is located, square foot of the living space, and so on. So once we identify those features, we select techniques and we build our machine learning models. Once we build our model, the next step is evaluation. We evaluate our model and we see how our model does on some data sets that it hasn't seen before. This is how we will approach the machine learning sections. We'll start by looking at the theory of the machine learning class, and I'll provide links if you are interested in more of the math theories. We won't look into detail about the math of each of the algorithms, but I'll provide links so that you can go and learn more about the math theories behind if you are interested. Then we will use various data analysis techniques for obtaining data, formatting and cleaning data, model training, building and testing our model. And finally, we will evaluate our model. We will look at many projects on machine learning. So we'll approach machine learning in this format. First, we'll look at the theory, and I'll provide links where you can check out the math behind if you are interested. And then we'll deploy various techniques for data analysis, formatting and cleaning, model building, and then testing our models. So far, we have seen various machine learning techniques like regression, classification, clustering, and so on. So, how do we choose a machine learning model? This is the Scikit-Learn algorithm cheat sheet. It's located at this URL. So let me go to this URL and show you the machine learning algorithm cheat sheet. Okay, here we are at the Scikit-Learn algorithm cheat sheet. So you can check it out. It has certain techniques. So you start here, follow the arrows. Is your samples greater than 50? If no, if yes, follow this direction. Here you see some classification methods, some clustering techniques here. We have regression and dimensionality reduction. So this is a nice algorithm cheat sheet. You can check it out. Just wanted to show you that. Again, check out the documentation that Scikit-Learn has. It has various examples. It serves as a good resource on any of the techniques. You can read more about what we will learn in the Scikit-Learn's documentation. Just to recap what we have learned in this lecture, we looked at the two classifications of machine learning, which are supervised learning and unsupervised learning. And in supervised learning, we are given data with certain features and we try to predict where the object will fall given those features. And some examples of supervised learning are predicting a house price, predicting price of a car, and so on. And we deploy techniques like regression and classification in supervised learning. Whereas in unsupervised learning, there is no learning of data features. Data is presented and the algorithm analyzes and comes up with similarities by clustering together similar data features. We mentioned that k-means clustering and nearest neighbors are some methods used in unsupervised learning. And we looked at some examples of unsupervised learning, like discovering crime hotspots and recommendation systems. And we briefly looked at machine learning process. We start by acquiring or obtaining our data. Then we explore and process our data to see if there is any trend or correlation, whether there are any visible outliers or not. And visualizing your dataset helps a lot in the exploration process. Then we have data cleaning, where we remove any missing values or any duplicates. And then we determine and select our features. After that, we build a model based on those features and we evaluate our models. Thank you everyone, and in the next lecture we'll look at linear regression. Hello everyone, and welcome to the section on linear regression. We will briefly look at the theory behind linear regression, and then we'll jump into Jupyter Notebook and see some live coding. As we have seen, regression is one of the most widely used statistical tools, and it's an example of supervised learning. So what's the idea behind linear regression? In linear regression, we have some set of features and we want to model how our observations that are associated with these features change as we change the values of the features. Let's see an example. Let's say we are trying to predict house values or house prices. We can say that a house has some sets of features like size of the house, how many bedrooms it has, number of bathrooms, lot size, and so on. The observation that we have is what's the price of the house, which is also known as target. In linear regression, we are given some input samples x and output samples y, and the outputs of this function is given by the outputs of the sample is given by the function y is equal to f of x. In this function, we would like to learn f and evaluate it on new data. In this case, y is a continuous variable, which is price of a house. Let's just consider the number of bedrooms as our features, which is x, and price as our target. So here we have a graph. On the x-axis we have number of bedrooms, which will represent our feature, and on the y-axis we have price, which is our target. Here we can consider the price in hundred thousands, and each of these blue points indicate data points or data sets, or specifically houses. So all these data points indicate houses in a given neighborhood. And as you see here, as the number of bedrooms increases, the price of the house seems to be higher. So again, in linear regression, we try to predict a target from the given features. Here we are trying to predict the price of a house given the number of bedrooms. We are only considering a single feature, which is number of bedrooms in this example. And if we look at this graph here, again on the x-axis, we have our feature, which is number of bedrooms, and on the y-axis is the price, which is our target or observation. And each of these red points indicate our data points or houses, and this black line indicates a linear regression fit line, and the blue lines indicate the distance or the difference between the actual price of the house and the predicted price. So the goal of a linear regression model is to minimize these errors, to minimize this distance as much as possible. So the best fit regression line, linear regression line, is the one with the lowest or minimal distance between the actual and the predicted price. So that's the goal of linear regression. Okay, let's talk about defining a cost for a given line. And one very common cost associated with a specific fit to the data is what is known as residual sum of squares, or mean square error. In residual sum of squares or mean square errors, we take our fitted line and we look at each of our observations. In the previous example, the red points are observations, and our fitted line is the black line. All these red points are observations, and this is our fit line, the black line. So the goal of this residual sum of squares will be to minimize the distance between observation and our fit line. So here in residual sum of squares, we take our fitted line and we look at each of our observations. Then we look at how far the observation is from what the model would predict, which is just a point on the line. So we look at all of these distances here, and we actually look at the square of the distances. That's why it's called the residual. The residual is the difference of your prediction and your actual observation. So we're looking at the same graph here. If you fit a line, if you fit this black line and define the residual error by these blue lines, this residual errors are the distances between our true points, which are the red points, and our desired price, which is the target, the black line here. So we want this blue lines or these errors to be as low or as small as possible. Hence, we try out various lines and we consider the line with the least error value. Okay, so this is one regression line. We try out another regression line and we consider so many regression lines, and the one with the least residual error is considered to be the best fit line. Again, this is a brief theory on linear regression, and in these examples we looked at only one feature, which is number of bedrooms. In the coming lectures, we'll look at live coding by first looking at a simple linear regression model where we will only consider one feature, for instance number of bedrooms, and we'll compare that to price of a house. And then once we understand that, we'll consider more features. What if we have more than one feature and we know that the house price depends on many features like number of bedrooms, number of bathrooms, how big is the living space, how big is the lot, where the house is located, whether the house has a basement or not, and so on. So we'll consider more than one feature. We'll consider a few of the features that I mentioned, and we'll try to build a model and try to predict the price. And we'll compare our two models. So I didn't go into the depths of the math, but if you are interested about the techniques behind the math, you can check out this Wikipedia link, and it has lots of details about the methods used behind the least square method and linear regression in general. Let's go to the wiki link and see it briefly. So here we are at the Wikipedia link that I provided. So it has a method and more description, formulas about the least square estimation technique. You can read more about it here. And here we have some data points in red, and we try to come up with a best fit line for our data points. So feel free to read more of this on the Wikipedia to learn more about the least square method. And also don't forget to check out the Scikit-Learn's documentation on linear models or linear regression. As I mentioned, linear regression fits a linear model to minimize the residual sum of squares between the observed data points and the predicted line. Just to summarize what we have learned, in linear regression we have certain features and we try to predict a target based on those features by learning those features. In the next lecture, we'll look at live coding of linear regression. Thank you everyone. Hello everyone and welcome. In this lecture, we'll look at linear regression from a case study approach. What we'll do is we'll explore a data set, which is an actual data set, and we'll see some examples of linear regression. So this is a summary of what we will go through. We'll start by exploring our data set and try to visualize it. And then we'll train and create a linear regression model of our data set. After that, we'll evaluate our model and make some predictions, which will be followed by a calculation of the root mean square error. And then we'll consider some more features or less features and build another linear regression model and compare the two models that we got. Great. So we'll start by importing the libraries that we need. Import Pandas as PD, import NumPy as NP, import Seaborn as SNS, and we have the magic function here, Matplotlib inline, to visualize our graphs in Jupyter Notebook. And we'll import the remaining libraries that we need as we go on. Let's start by loading our dataset by using Pandas readCSV method. And we'll save our dataset in a variable called house. This dataset is regarding the price of different houses in the Seattle area. Okay, let's check it out. pd.readCSV, and then I saved it where my Jupyter Homebook is located. So I'll just pass name of my file. I named it home_data.csv. Let's see what our dataset looks like. So I'll call the head method. And this is what it looks like. It has 21 columns. This is ID of a specific house, date, we have price of the house, bedrooms, bathroom, square living, square lot, floors, waterfront, and so on. So one row is regarding a single house, and here is the zip code. Again, this is a dataset obtained from the Seattle area, and this is the zip code for the specific house. Okay, what we'll do is we'll try to predict the price of a house using linear regression models. So this will be our target. Price will be our target. And for features, we'll use, for instance, number of bedrooms, bathroom, square living, and so on. So all of those are features, right? And based on these features, we'll predict the price of a house. So for our first model, we'll take a few of these features. Maybe we'll consider 5 or 6 features and then try to predict the price by using our linear regression models. Okay, so this is our data set, and to show you how many houses are in this data set, we'll call the tail method house.tail. So we have about 21,600 rows. Let's call the info method to get some information about our house dataset. So house.info and run it. So we have a data frame and we have about 21,613 rows. Okay, so this is a general information about our house dataset. Okay, and you see here the memory is 3.5 megabyte. It's a bit big. And if we want to see some statistics, we can call the describe method on our house dataset. So house.describe, and we have a count, mean, standard deviation, and percentiles, maximum value for each of our columns. And if you want to see each of the individual column names, we can of course call the columns method. So house.columns, and you'll see our column names. So those are some general information about our dataset. Next, let's visualize our dataset. Let's start by plotting a scatter plot. So I'll call the scatter method plt.scatter, and we'll pass what do we want to see. Let's consider one of the features, for instance, square living. So there's a feature known as square living. So that's how big the house is. So we'll see a scatter plot of square living versus price. As we know, that's one of the important features in predicting a house price, how big the house is. So plt.scatter, we'll call the square feet living, that's the column name, and then price will be on the y-axis. So plt.scatter, and we can label our x and y-axis by calling the x label and y label methods. Let's say square feet of the house, and then let's also label our y-axis. So I'll call the y label method and then price of house. Run it. Oh, import plt is not defined. Let's import Matplotlib. Import matplotlib.pyplot as plt. Let's run the cell again. Okay, let's go back to our cell. Run it again. And this is what it looks like. We have square feet of the house versus price of house. As you can see, as the square feet of the house increases, the price of the house seems to increase, right? Let me make this a bit bigger. Let's pass the figure attribute, the figure method, and then pass the fig size attribute. Let's make it 10 by 6 maybe. You can pass whatever fits your notebook very well. Okay, so this is what it looks like. As the square feet of the house increases, the price seems to increase. Next, let's call the lmplot method and try to get like a linear regression line for our scatter plots. So sns.lmplot, and then we'll pass the x and y axis. So square feet, square underscore living. Make sure you can just copy paste the column names from here. Okay, so spelling and everything is important, otherwise you'll get an error. So the easiest way is to copy paste from the columns list that I just showed. Okay, and our data is coming from the house data set. Okay, let's run this, and this is what it looks like. So this is our linear regression line passed to our plot, and this is where it intercepts the y-axis. So we'll try to calculate this point where the line intercepts or crosses the y-axis later on. And notice here the price is in e to the power of 7, so that's in million. Okay, let's see some more plots for our house data set. Okay, let's see a heat map and a dist plot for our house data set. sns.heatmap to see a heat map, and then we can call house.core, run it, and this is a heat map for our house data set. We have ID, price, bedroom, bathroom, and then this is their correlation. So for instance, if you take square living and then its correlation with price, it's more of red, so it lies somewhere around here, right? So the higher the correlation, it goes towards red. And you can take a certain feature and then compare its correlation with price. For instance, let's say view. If you take this view attribute or feature and see its correlation with price, it's more in the orange in this area. So this is some general information about your dataset. You can see some correlation here. Okay, let's see one more plot, a dist plot. So we'll call the dist plot method that Seaborn has, and then simply pass what you want to see. I want to see, of course, we are interested in the price of the house. So we'll index our price column from our house data set, and then let's pass a red color. So you see here a normal distribution. So you can use any of these methods to visualize your data set. So that gives you some visualization about, the relationship of any of the features to your target and so on. Okay, one last plot I want to show you is a box plot. Okay, let's do that. So we'll call the box plot method that Seaborn has, and for our x variable, for our x-axis we'll pass zip code, and for our y-axis we'll pass the price. Okay, and data comes from our house data set. Let's run this. So here is a box plot of our zip code versus price. So if you look at the box plot closely, here we have different zip codes and the prices on the y-axis. Notice here you see one of the zip codes here, the price looks different than the rest of the zip codes, right? they seem to follow a close price range, whereas for this particular zip code, you see the price goes all the way to about 4 million, right? Okay, so those are some interesting things that you can see by visualizing your data. And you can explore why, the price is a little bit higher or different than the rest of your zip codes. So those are some things that you can obtain by visualizing your data set. Before making any prediction or any analysis, it's a good idea to explore and visualize your data. And that's what we did in this lecture. In the next lecture, we'll continue our discussion on linear regression, and we'll see a linear regression model. Thank you, everyone. Hello, everyone, and welcome back. In this lecture, we'll look at a linear regression model, but to get there, we'll have to do some initial steps. The first thing we need to do is define our features and target. And once we have that, we'll divide or split our data set into training and testing sets, and we'll use the training set of data to train our model, and then we'll use the testing part of our data set to test our model. Great. If you remember, in the previous lecture, we used the info method to get some information about our house data set. For instance, it has the following columns: ID, date, price, bedroom, and so on. We have a total of 21 columns. What we'll do is we'll take 10 of these columns and use those as our features. So we'll take the number of bedrooms, bathrooms, square living, floors, and so on. Okay, so what I will do is I just prepared this. So we'll use these columns as our feature and save it in a variable called x. So x is equal to house, and then we indexed those 10 columns. So bedrooms, bathrooms, square living, square foot lot, floors, square feet, above, and so on. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 features. So I just considered these 10 features out of the 21 columns. So that will be our x, and we'll save our target in a variable called y. So y is equal to house, and then we'll use price, of course. Okay, so we'll build our model based on these features. Okay, and just to give you a preview of what we'll do later on is we'll consider maybe 15 features or 18 features and build another linear regression model on those new features, and then we'll compare the results with this regression model. Great. Okay, let's start. So the reason why I saved our features in uppercase X, whereas our target is in lower y, the reason is because this capital X means it's a two-dimensional array, whereas the lowercase y means it's one-dimensional. So you will see this often in literature. Okay, but you don't have to save this in upper X and lower y. You can use whatever variable that you want, but you'll see this often in literature, and most people use this. So for instance, to show you what I mean, if you call the shape method, so x.shape, you see here it's two-dimensional array, 21,613 rows by 10 columns. Okay, whereas if you call the shape method on y, you'll see that it's one-dimensional. Okay, that's why I have them in upper X and lower y, but it doesn't matter. So this is just in case you are wondering why I chose upper X and lower Y. Great. So our model, we'll train our model on these features, on the specific 10 features. Great. The next thing we'll do is Scikit-Learn has a library or function known as the train test split method, and we'll use that method or function to train our dataset. So the first thing we need to do is import that library from Scikit-Learn. So to do that, we need to say from scikit-learn.cross-validation import train test split. So from sklearn that cross_validation import train test split, train test underscore split. Okay, that's the method we will use, the train test split method. So what we'll do is we'll use this method to first split our dataset into training and testing data. So we'll split them into training and then testing datasets, and we'll train our model on those training datasets and then use the testing datasets to test our model. Okay, so if I go to Scikit-Learn, the documentation here, the train test split, so this is the method, and then we'll divide our data into training and then testing. So we have xtrain, xtest, ytrain, and ytest. So the test parts are the testing datasets, whereas the train part are the training datasets. Okay, and once we divide it into those training and testing datasets, we'll use the training sets, xtrain and ytrain, to train our model. And once we train our model, we'll use the testing dataset to test and see how well our model does. Okay, let's do that. So we have xtrain, xtest, ytrain, and ytest. So you'll see this commonly used. These variables are commonly used. But again, you can use any variable that you want. But be consistent throughout your methods. Okay, so we'll use the train test split method, and then we'll pass our dataset, our x and y that we defined earlier. Okay, and we can pass the optional parameter known as test size. So by default, 75, the test size is 75 and 25%. So 75% will be used for training, and then 25% of the dataset will be used for testing. That's by default. If you don't pass the test size attribute, this default values will be used. But for our example, let's pass 0.3. That means we'll use 70% for training and then 30% of our dataset for testing. Okay, and there's also another variable, another attribute known as random state, and you can set this to whatever value that you want. Let me set mine to 7 or any number. So if you want to get the same result as me, you can set your random state to 7. That way we'll all get the same result. Okay, again, this is optional. Okay, now our x and y are divided into training and testing dataset. Okay, and you can also print out your xtrain and ytrain datasets. So for instance, I can say print xtrain dot shape, and let's also print our ytrain dot shape. So our xtrain, again, it's two-dimensional, 15,129 by 10, whereas your ytrain is 15,129.
Okay, one-dimensional, two-dimensional. Again, your training dataset is, in this case, 70% of your dataset, which is 70% of 21,613. Similarly, if you consider your testing dataset, say print xtest.shape. So xtest is two-dimensional and it's 30% of your dataset. So 30% of 21,600 is 6484. Okay, so that's one thing to remember. And again, if you print out the shape of your y-test, that shape, you will again see it's one-dimensional and it's 6484. Great. Next, we can create our model. Before we do that, we need to import the linear regression from Scikit-Learn. So for that, we'll need to say from sklearn.linear model import linear regression. So from sklearn dot linear underscore model import linear regression. Okay, now that we have imported our linear regression model, the next thing we need to do is we need to instantiate the linear regression model. We need to create an instance of this linear regression class. Okay, so to do that, we simply call the linear regression method. So linear regression, and then we'll save this in a variable, whatever variable we want. I'll just save it in a variable called model. So this is instantiating our linear regression model. Okay, so here we are creating an instance of this linear regression class. So once we divide our dataset into training and testing datasets, we instantiate our linear regression model. And once we instantiate our model, we'll pass or call the fit method on our linear regression model. So the next thing we do is call the fit method on our model. And what this fit method does is it will train the linear regression model by using the training dataset. So we need to pass our training datasets, which are xtrain and ytrain. So x underscore train and then y underscore train. Great, and once we fit our model, we can predict by using the predict method. So we can take our model and then call the predict method and then pass xtest, and we can save this in a variable called, let's say, prediction. Okay, so these are the general steps. We start by instantiating our linear regression model, and then we use the fit method to train our linear regression model on the training datasets, and after that we can call the predict method to predict the price by using our model. Great, so just to recap what we did here, we first started by splitting our dataset into training and then testing datasets. Once we do that, we instantiated our linear regression model, and then we trained our model using the training datasets, and then we used our testing datasets to predict based on what our model did, based on our model. So we'll continue our discussion on linear regression model in the next lecture. Thank you, everyone. Hello, everyone, and welcome back. In the last lecture, we built a linear regression model, and in this lecture, we'll evaluate our model. Great. So I'll start by looking at our house dataset by calling the head method. So here we have house ID. What I will do is I'll see how our model predicted the price for a certain house. So let me copy this house ID, and what we can do is we can save this in some variable. I'll just call it house1, and that will be equal to our house data frame, and then we'll simply index the ID column. Okay, so we'll say house, and then we'll index the ID column, and we'll set that to be equal to that specific ID. Okay, so that's house1. So if I simply call house1, we have one row with all the house information, with all information regarding that house. Okay, from here we can simply index the price and see the price of that house. So if I say house1 and then simply index the price column, we see that the actual price of the house is 538,000. And here we see that this house is at index 1. So row 0, row 1, right? To see how well our model predicts the price for that house, what we can do is, so in the previous lecture, we have saved our prediction in a variable called prediction, right? So I can call that object prediction and then simply pass the index of the row for our house, which is 1 in this case. So if I run this, so our model predicts the price of the house to be 724,000, whereas the actual price is 538,000. So that's just an example of how our model predicted the price of that specific house. And to see how good or how well our prediction did, we can plot a scatter plot of the prediction versus the actual price and see the relationship from there. So we can call the scatter method plt.scatter, and then we'll pass. So on the x-axis, let's pass y-test, and on the y-axis we'll pass prediction. So y-test is the actual price for our house, whereas this prediction is the price our model predicts. Okay, let me run this. So here we have a scatter plot. Let me make the plot a bit bigger. plt.figure. Let's pass the fig size attribute and set the size to be 10 by 7. Let's run it again. Okay, so this is a scatter plot of the actual price versus prediction. And what we can tell from this is, if you see more of like a straight line or linear relationship, we can tell that our model did good compared to the actual price. Okay, if you see kind of a linear relationship, that means our linear regression model is doing good compared to the actual price. So that's what you can tell from a scatter plot. If you see more of a linear relationship, that means the model is good. Okay, what I want to show you next is evaluate some of the coefficients that we used. If I call x, we know that we have used 10 features, right? And we can call a method known as coefficient to find out the coefficient values for our model. So if I say model.coefficient underscore, that's the name of the method, you'll see a coefficient value for each of our features. Okay, remember the features that we used? So these are the 10 features: bedroom, bathroom, square living, and so on. And that's the coefficient for our features. What we can do is we can use this coefficient and map it to the specific feature and see what kind of effect it has. Okay, to do that, we can create a data frame by using Pandas data frame method. So pd.data frame, and then we'll use this model.coefficient. So model.coefficient underscore, so we'll use those values and we'll map it with the specific features that we defined earlier. So we have x.columns, and then for columns we can name it, let's say, coefficient value or whatever you want. Coefficient, let's say, value. And we can save this in a variable called data frame coefficient. Okay, now let's see what our data frame coefficient looks like. So if I run this, so here we have our 10 features: bedroom, bathroom, square living, and so on. And then we have our coefficient values here. Okay, so what does this tell us? So this tells us the relationship or the weight of each of our features on the target price. So for instance, if you consider the specific feature square feet living, it means that a 1 unit increase in the square feet living value will result in an increase in $293 in the price of your house. Okay, so that means if all the other conditions are kept constant. And similarly, if you take another feature here, for instance bathrooms, and if there is like a 1 unit increase in this feature bathroom, that could be maybe 1 additional bathroom, that's associated with an increase of this much amount in your target price. Okay, so that's the general information that you can get from this coefficient method. So again, this is an average value. Some of it might not be. So this doesn't look realistic, An increase in bedroom, according to this, an increase in a bedroom will result in a decrease in the value of the house. But those are the general information that you get about your features. Okay, that's the coefficient method. And you can read more about this coefficient method from the Scikit documentation. Just wanted to show you that method. Okay, and earlier I mentioned that there's a method known as intercept. So you can call the intercept method on your model to see where your linear regression line crosses the y-axis. That's the y-intercept. So model.intercept, that's the method name, intercept underscore. So the value is negative 269,000. So that's where this line crosses the y-axis. The next thing I want to talk about is what is known as the root mean square error. So this is one of the methods that we can use to evaluate our linear regression model, root mean square error. You can read more about it online or Wikipedia. It's a common method used. What it does is we take the difference between the actual value and our prediction. And once we take the difference, we'll calculate the mean of those and finally take the square root of that. Okay, we can read more about it here. Let's consider this regression line. So the blue dots are the actual prices or the actual value, whereas this red regression line indicates your prediction. So what we do is you take 1 point and then calculate the distance from the line. So take that difference and then you take another point, calculate the distance from the line, and then you take the mean of the difference of each of your points in your data set, okay, and that will give you the mean square error. That's also another method. And then once you get your mean square error, you take the square root of your mean square error, and that gives you the root mean square error. In regression problems, so you want to minimize this root mean square error. Okay, that means you want the distance to be as close to your regression fit line, right? So the closer the data points are to your regression line, or if you have a lot of those data points or data sets close to your regression fit line, that means your model predicts very well compared to the actual price. Okay, so that's how you calculate the root mean square error, and every time you want that root mean square error to be as low as possible. Okay, for us, Scikit-Learn has this method, so we'll import the matrix. We'll import this matrix library, and then we can call a method known as the mean square error method to calculate the mean square error, and then we can find out the root mean square error from there. Great. We'll see that in the next lecture. Thank you, everyone. Everyone, and welcome back. In this lecture, we'll look at the root mean square error. In the previous lecture, we briefly mentioned what the root mean square error is, and it's one of the methods that we use to see how well our linear regression model did. Okay, and we want this root mean square error to be as low as possible. So the lower your root mean square error is, the better your model predicts compared to the actual price. Okay, so in this example, the blue data points represent the actual price of your, for instance, housing data, and the red line indicates your model, your linear regression model. And what we do is we calculate the distance of each data point from your regression line, and then we take the difference, the distance between your data point and then your line. And then if you square that and take the mean, that will be your mean squared error. And then the root mean squared error, we said, is the square root of your mean squared error. So you can read more about that here on Wikipedia. I just wanted to give you a brief overview of what a root mean square error is. For us, Scikit-Learn has a library known as matrix, and this matrix has a method known as the mean square error method, and we can use that to find out the mean squared error, and later we'll take the square root of the mean square error to find the root mean squared error. Let's see how we can do that. So first we need to import matrix from Scikit-Learn. So from sklearn, let's import matrix. And once we import matrix, we can simply call the mean square error method. So mean underscore square underscore error. And then this mean square error method accepts two values, which are your actual and then your actual price and your prediction. So the actual price, we said that it's y test, whereas our prediction is our prediction that we came up with from our model. Okay, so if we run this, so this is mean squared error. Let's run this again. So this is your mean square error. Okay, so we can save this in a variable called mean squared mean underscore squared underscore error. So this will be our mean squared error. Okay, and our root mean square error will be the square root of our mean square error. So NumPy has a method called square root. We can use that to calculate the square root of our mean square error, and that will give us
247,262. So that will be our root mean square error. Root mean square error, RMSE. Okay? So using our linear regression model, the root mean square error is this much, this amount. And for that we used, if you remember, we used 10 features, right? So if I go back, here are the features that we used. We used 10 features. Great. What we can do next is we can build another linear regression model with different features and calculate the root mean square error, and we can compare our two models. Okay? If you remember, these are the 10 features that we used for our first model. And for our second model, let's consider fewer features. For instance, let's consider number of bedrooms, bathrooms, square living, square lot, year built, and zip code. So let's remove some other features. So let's build another model with these fewer features. So for features, we'll only consider bedrooms, bathrooms, square living, square lot, year built, and zip code. And our target, of course, is the house price. Okay? So what we'll do next is split our dataset using the train test split method. We'll use that to split the dataset into training sets and then testing datasets. So we can say X train, X test, Y train and Y test, Y train, Y test, and we'll use the train test split method. Train underscore test underscore split, and then we'll pass our X and Y. So those are our target and then our features and target. And we mentioned we can pass the optional test size attribute. So we'll use the same 30%. So 70-30 split, which is 70% for training and then 30% for testing. Okay? And then a random state of what did we use last time? 7. So as I mentioned, this random state is, if you use the same random state, you'll get the same values that I get. But feel free to use any other random state if you want. But if you want to get the same result as me, you can use this random state of 7. So once we split our datasets into training and then testing set, the next thing we need to do is instantiate our linear regression model, and I will save it in a variable called model2. We have linear regression, and once we instantiate our model, we'll use the fit method to train our model with the training dataset. Okay, so model2 dot fit, and then we'll pass our training dataset, which are X train and then Y train, right? And then once we train our model with the training dataset, we can predict by using the testing dataset, the X test dataset. So we can say model2 dot predict, that's the method, model2 dot predict, and then pass our X test dataset, and we'll save this in a variable called prediction2, since we have prediction already. And if you remember, in the previous lecture we calculated the price, the actual price, and the prediction of one of the houses, which is ID this. So that's row index 1. So similarly, if I say prediction to row index 1, so this is the prediction for that house, 780
18,000 using our model 2, whereas model 1 predicts as follows: prediction index 1, our model 1 predicted 724,000, whereas the actual price of the houses, house 1 index the price, so this is the actual price, right? This is the actual price of the house. And what I want to show you next is calculate the root mean square error for our second model and compare that value to our first model. Okay? So to calculate the root mean square error, we have already imported the matrix, so we can simply call the mean squared error method mean underscore squared underscore error, and then we'll pass our y-test and then our prediction 2, and we can save this in a variable called mean underscore square underscore error 2, and we can simply take the square root of this mean square error 2 value and save it in a variable called root mean square error 2 is equal to np dot square root, and then pass your mean square error 2 value. Okay, if we run this and call root mean square error 2, we see that our root mean square error 2 is 248,257. Root mean square error 1 is, using our first model, we saw that the root mean square error value is 247,262, whereas using our second model, the root mean square error value is 248,257. And we mentioned that we want the root mean square error to be as low or as minimum as possible. So looking at these two root mean square error values, we can say that our first model predicts better compared to our second model based on the root mean square error, since the root mean square error value for our first model is lower than the root mean square error value for the second model. Okay, so one reason could be, remember, the features that we used for our first model are 10 features, right? We used 10 features, so more features are used, whereas in our second model we only considered 6 features, right? So the more features that you include, the better the prediction will be for your model, because as we saw earlier, we can use the coefficient method to see the effect of each of the feature on your target price, right? We saw that in the previous lecture. We calculated the coefficient for our first model and saw the effect of each of the features on the price. We mentioned that if we take, let's say, one of these features, and if you keep all the other features constant, we can say that, an increase, for instance, this could be, I just said, in literature you'll find the term unit. So 1 unit increase in that specific feature will result in this much amount increase in your target price, for instance. So you can use the same coefficient method to calculate the coefficient for the 6 features and then see what you can generalize from the coefficient values. Okay, you can do that for your second model. So that could be one reason why your first model is better than the second model. That's by looking at the root mean square error. So here, the actual price for your house 1 is 538,000, right? And your first model predicted 724,000, whereas your model 2 predicted the price to be 718,000. So for this specific, which one is closer to your actual price? So model 2 predicts the price better than your first model, right? Since that price 718,000 is closer to 538 than 724 is. So that's something to consider. Even if one model predicts the price better than the other model, it doesn't mean that model will predict the price for every single house. It means that your model 1 will predict better than your model 2 on average. Okay, that's one thing to note. Not for every single house price, but on average, your first model will predict the price better than your second model. Okay, again, remember we have how many data points here? We saw that we have 20,000 rows, right? We have 20,000 values. So basically, it's on average. On average, your model 1 predicts the price better than your model 2. Okay, that's one thing to consider. And another example, another assignment for you is you can build another model. So this is an assignment for you. Build another model and consider maybe 12 or 13 or 14 features. Okay, so if we call our house.info, we saw that we have about 21 columns. So try to build another model by considering or taking more than 10 features. So for instance, ignore this ID column. You can also ignore the date column and take, for instance, price, bedroom, bathroom, square living, floor, waterfront. So take, let's say, 14 or 15 features. Okay, so build another model and consider, let's say, 14 to 16 features and compare the root mean square error to model 1 and model 2. Okay, so we have already seen model 1 and model 2. So build another model and build another model with, let's say, 15 features and compare the root mean square error of your model to models 1 and 2 and what can you generalize from that. Okay, so you can try that out. Okay, before we end this lecture, let me summarize what we learned in linear regression. So we mentioned that exploring our dataset and visualizing our dataset will give us a good idea about our dataset and what to look for. Okay, so those are important techniques while working with any dataset. And then we looked at our linear regression model. We considered certain features. We started by defining our features. In this example, in our model 1, we defined 10 features and our target is the house price. After that, we divided our dataset into training and then testing data. And once we did that, we used the fit method. We first instantiated our linear regression model and then we used the fit method to train our linear regression model on the training datasets. And once we did that, we used the predict method to make some predictions. And we mentioned that we can quickly make a scatter plot and compare the prediction to the actual price. And if you see like more of a linear relationship, that means our model is good, right? If you see more of a linear relationship between your prediction and the actual price, it means your model is good. And another common method to evaluate your linear regression model is using the root mean square error. We also saw the coefficient method to see the effect of each of your feature on your target price. And later we considered another model with fewer features. So in our model 2, we used only the 6 features and compare the root mean squared error of those two models. So again, you can try out this example. You can take it as an assignment and consider 14 to 16 features and see if you can come up with the root mean square error for that model and compare it to the first two models that we saw. Great. Thank you, everyone. Hello, everyone, and welcome to the project section on linear regression. In this project, we'll try to predict the interest rates based on a person's credit score and loan amounts. So we'll be using the data from lendingclub.com. So this is their website, lendingclub.com. It's a lending site and members make loans to each other. And the site kind of collects data on loans and borrowers, so they save anonymous data. Okay? And we'll be using their data for this project. So what's a FICO score? Here I mentioned based on a person's FICO score. FICO is like a credit score, and if you read the definition here, a FICO score is a credit score developed by FICO, which is a company that specializes in predicting a person's credit score. Okay, that's a FICO score. FICO credit score. Okay. So these are some of the steps that we saw while learning linear regression. We followed the steps like setting up our data, cleaning up our data, and visualizing our data. And then we used NumPy's linear regression tools. And then we used Scikit-Learn to implement a multivariate regression. We'll be following some of the steps in the project. Okay? So we start as usual by importing NumPy and Pandas, and we import Matplotlib and Seaborn. So these are the main imports, and anything else that we need, we'll import it. Okay? Now let's start by browsing our data. So I have a site here that contains the data related to this loans and borrowing. Okay, so we'll be using this data. Let's see what this data contains. For that, I'll use the read CSV method. Okay, so pd.read CSV, and then I'll simply pass the URL. Okay, and let's save that in a variable. Let's say loan data. Okay, loans data, and let's see what it looks like by calling the heads method. Loans data that head. Let's run it. Oh, let me run my Panda. Okay, so this is what it looks like. It has these columns. It has so many columns. We have amount that requested, amount funded by investors. We have data a column related to interest rate, loan length, and so on. Okay. Now let's see some of the columns related to this data. Okay, let's start by looking the loan length, which is this column. So loans data, and then we'll pass the loan length, loan.length. Okay, let's see the first 10 rows. Okay, so I'll pass index 0 to 10. Let's run it. Okay, so this is what it looks like. 36 months, 36, 60 months, and so on. For our purpose, we don't need this months, we just need the numbers here. Okay, so we'll have to remove the months from that. Now let's look at the interest rate. I'll use the same method. So loans data, and then I'll pass the interest rate, interest that rate. Okay, and let's see the first 10 rows. So we have an interest rate of 8.9, 12.12, and so on. And we don't need this percentage symbols. We just need the number for our purpose. Okay? Next, let's look at some information related to FICO score. Let me go back to my table here. So here I have, this is the FICO score, FICO.range. So this is basically the credit score. For instance, 735 to 739 and so on. Let's see that data. So loans underscore data, and then we'll pass the FICO range, FICO.range, and we want to see the first 10 rows. Let's run that. Okay, we have a range here. Okay, but for our purpose, we don't need this range. We just need one of the numbers here, right? When we worked with credit score. So what we will do is we need to convert this range into strings. First, we need to convert the range into strings. And then once we convert that to a string, we need to parse that string, right? So for instance, the second row, 715 to 719, right? So this range, we need to convert it into string, which is in this form. And then we need to parse that string so that we get two numbers. Okay, like this, 715 and 719. Okay, and then once we have this, we can just pick any number just for our purpose. We can either pick 715 or 719. It wouldn't make that much difference. Or we can randomly select a number between 715 or 719, or we can take the mean value. Okay, we can use any of those values. It doesn't make a difference. It wouldn't affect our results much. Okay, I'll just be picking the lowest limit, for instance in this case 715. Okay, and you guys can take the highest number or a number in between, anything, but I'll just pick the lowest limit, 715 in this case. Okay, so these are the information, some of the information related to this data that we will need. But first, from the loan data, from loan.length, we need to remove the months. And then from the interest rate, we need to remove this percentage signs. And from here, from the FICO range, we need to convert this into a string and then parse the string so that we can choose a number. Okay, so that's the data cleaning process. And once we have that, we can work directly with this data, which will be more easier. So we have that cleaned up data already. I grabbed that from the internet and I have saved it, and I have saved that in my Jupyter's Homebook location directory. It's the loan.csv file. Okay, so this is the file loan.csv. Let's open and see what it looks like now. So I'll use the read CSV method, read CSV, and then name of my file, loan.csv. Okay, and make sure to place this file where your Jupyter notebook is located. And let's save that in a variable loans. Okay, loans.head, let's view it. Okay, now we have this interest rate, FICO score, loan length, monthly income, and loan amount. So here we see that the interest rate has no longer the percentage symbol, and FICO score is just a single number instead of a range, and our loan length doesn't have months anymore. Okay, and in the next lecture we'll continue with visualization. Thank you everyone. Hello everyone and welcome back. So now that we have a clean data, let's try to visualize it. Okay, so we'll try to see it on a histogram. A histogram helps us to see the distribution of values for a single variable, right? So let's see what the FICO score looks like on a histogram. Okay, so we'll see the distribution of this FICO score. Let's do that. So we have already imported Pandas and Matplotlib earlier. If you haven't, we need to import that. Okay, and then plt.figure, we'll be using the loans data that we created here. Okay, pd.readcsv, let me just copy this, Command C, Command V. So we have our loans data, and then we'll plot the FICO score. Okay, so let's say we have our loans, and then we just pass FICO score, and then let me save that in a variable. Let's say FICO. Okay, and then I'll print a histogram of this FICO score. So FICO.histogram. Okay, histogram, FICO.hist, and let's pass beans. Let's use 20. Okay, let's run it. So this is a histogram of the FICO score. Okay, and from the graph we see that the distribution is not a normal distribution. Normal distribution is usually like a bell curve, right? So it's different than a normal distribution. Okay, and we know that our credit score, FICO score, is one of the most important factors for borrowing money. That's why we're looking at the FICO score. Okay, so from this graph we see that, from this histogram we see that the distribution is not normal distribution, which means there are some other factors that are influencing our borrowing. Okay, so it's not only FICO score that has an effect on our borrowing. So there are some other factors. That's why the shape is a little bit distorted compared to a normal distribution curve. Okay, next we'll have a box plot, and that will allow us to see if there are any other factors that have influence on this borrowing. Okay, let's do that. We have plt.figure, and then we have our loan.csv file. Okay, and then let's plot a box plot. Okay, so for that I have my loans that box plot, and let's see a box plot of interest rate and FICO score. So interest that rate and FICO score, FICO that score. Okay, and let's store that in a variable called x. Okay, and next let's label our axis. We'll label our x and y axis. We'll label our x-axis as the FICO score and y-axis as the interest rate. Let's do that. So we have our x, which is our box plot. We'll use the set x and y label methods. Okay, so set x label, we call that on our box plot, and then whatever name we want for that. Let's say FICO score, and let's do the same for our y label. X dot set y label. It's the interest rate in percentage. Okay, and if we want, we can also set title by passing the set title method. Okay, this is the method set title. Okay, I'm just gonna leave it like this and see what my box plot looks like. Okay, so here I have my box plot. FICO score on the x-axis and interest rate on the y-axis. Let me zoom in. Here on the x-axis, you can't see the FICO scores very much, right? Basically it goes, let's say some number 630, and then 640, 650, 660. It goes on until 830. So we can modify our graph here a little bit so that we can see this box plot more clearly. We can see this x, the labels on our x-axis. Let's do that. So for that we'll use the set x tick labels method. Okay, so I can call my box plot x and then call the set x tick labels method. Okay, that's the method name, and then we just pass a list of what label we want. So for instance, we can start with 630, maybe 630. Okay, and then we can have a space in between, and then let's do 660 then we can have a space. So I'm incrementing 30 each time. So 690. That's the credit score, the FICO score. A space and then 720. Okay. And then we have a space. Let's have 750. A space. 780. Space. 810. And finally, let's have a space and 840. Okay, I think that should be enough for our credit score. And let's make our space 2 characters wide. Okay. Let's see our box plot now. Okay, so still it doesn't align with our points here, and in this case, basically what you have to do is add more spaces. Okay, we just need to add more spaces. So I just paused the video and then added some more space in between our FICO scores so that it looks much better. Okay, you can do that. So here we have a box plot for each of for our FICO scores versus interest rate, right? And I see a trend here. The trend is like it goes downward as we proceed towards the higher FICO scores, right? So it starts here and then it goes downward. So the interest rate in percentage gets lower as the FICO score gets higher, right? But if we take the same range of FICO score, let's take this range. For instance, let's say 800. So if we take this 800, there's a range between what? Around 12% and 7%. Let's say 7 to 12. So I see there's, given the same FICO score of 800, I see there's a range of interest rates, which is not a single value, right? So for a FICO score of 800, I see an interest rate range between 7% and 12%, right? So this means that there might be some other factors determining this interest rate given the same FICO score, right? The same FICO score. So what are these other factors that affect this interest rate besides the FICO score? Okay. So these are the important factors which we need to investigate in order to determine the interest rate and what are the factors that influence the interest rate. Okay? So we want to look at all these factors and see how they might affect the interest rate. And there is one way to look at all of this, and it's called the scatter plot matrix. Okay? We have not seen that before, but I will show you that. A scatter plot matrix. Okay? And this scatter plot matrix is a great way to look at multiple factors simultaneously at the same time, okay, to see which factors influence, for instance, interest rate in this case. Okay, and this scatter plot matrix, it just consists of a grid of plots of multiple variables, and they will plot those variables against each other. That way we can see the relationship those variables have to each other. Okay, so we'll look at that next. Okay, let's see that. I have my loans, pd.readCSV, loan.csv, okay, and I'll call the scatter matrix method, okay, to see the scatter plot matrix. So pd that scatter matrix, that's the method, and then we pass our loans object, and then we call the alpha, that's for transparency. Let's try a transparency of maybe 0.1, so alpha range from 0 to 1, and then let's pass another parameter, fixed size, and let's pass 10 by 10, and there's one more parameter, diagonal, and we'll pass histogram so that the histogram will be printed diagonally. Okay, let's run that. Okay, now I have my scatter matrix plot. Let me zoom out a little bit so that we can see the whole picture. And you can adjust this fixed size. Let's make it 8 by 8. Okay. Now I think you can see. Let me zoom out a little bit. Okay. Now I think it's much more visible, right? Okay, the default color is blue. Let me change. Let me pass a color argument. Color is equal to red. Let's run it. Oh, we need a comma here. Let's run it again. Okay. So the histogram is plotted diagonally, and here we have interest rate, FICO score, loan length, monthly income, and loan amount, and I have the same on the y-axis. And so this scatter plot matrix, it allows us to compare the effect of each individual variable to each other, right, and to the other variables. So for our case, we don't need to consider the effect of the same variable on each other, right? Like the effect of interest rate to interest rate, we don't need that. The effect of FICO score to FICO score, we don't need that. So we don't need to consider this histograms. But we want to know the effect of, for instance, FICO score on interest rate, monthly income on interest rate, and so on. So we'll focus on that. And the way we read the scatter matrix plot is, for instance, if I want to compare loan amount, the effect of loan amount and FICO score, I just go to loan amount and then FICO score. Okay? And then I will consider this figure. Okay. From here, just by looking at this, I can tell that there's a linear relationship here, right? and there's also a linear relationship here. Especially here I can see it. That's for, if we consider FICO score and interest rate, I see a very linear relationship, right? You can see a linear trend. And these are all the scatter plots, all the stats. So there's a relationship. So what does that mean? That means a person's FICO score is an important factor in knowing the interest rate, right? In influencing the interest rate. That's why the linear relationship is very clear, this trend. And here I see a somehow, it looks linear somehow, right? So that's the relationship between loan amount and interest rate. So the loan amount also determines the interest rate or influences. Okay? And if we look at, let's say, monthly income, so monthly income and interest rate, we don't see any linear relationship, right? We can say that. And loan length, relationship between loan length and interest rate, not very clear, right? So those two factors, they don't have any linear relationship. But from what we have seen on FICO score and loan amount, we can say that based on this linear relationship, we can say that FICO score and loan amount are more of an independent variable, right? For our model, for our linear regression model. Okay? So in the next lecture, we'll do some more analysis and we'll work with FICO score and loan amount with interest rate. So we don't need to consider the other two variables, which are loan length and monthly income. Okay? So I want to introduce this scatter matrix plot. We haven't seen it before, but I want to introduce this as part of this project. Okay? And you can play around with these variables. You can change this alpha values and see the effect on your scatter matrix plot. Okay? And work around with this figure size so that you have the best fit on your notebook. So you can see the trend more now, right? So you can play around with that. Good. Now that, let's recap what we have done in the last two lectures. So we have our data. We cleaned it up a little bit so that it's more workable for our purpose. And then we looked at some visualization, histogram. We looked at the box plot and then a scatter matrix plot to see what factors might influence the interest rate. And in the next lecture, we'll do some analysis. Thank you, everyone. Hello, everyone. Hello, everyone, and welcome back. So now that we have done some data visualization, let's jump to analysis. Okay? We have seen that the interest rate variance depends on our FICO score and loan amount. So we'll be looking at a multivariate linear regression, right? Multivariate linear regression. That means more than one variable affects our interest rate. In this case, FICO score and loan amounts. Okay? So let's start by importing NumPy and Pandas. Okay, So I have already imported some of the libraries and modules that we need. Let's import the others. We'll be using the StatMods library. Okay, this library has a lot of functions for statistical analysis. So let's import that. Import stats models that API as SM. So this stats model has a lot of functions that will help us in statistical analysis. Okay. Then we'll import. I think that should be good. If we need to import anything else, we'll import it later on. Okay. So we have our data, right? Our loan.csv file. We have that data. And let's say, let me save it in another variable called data frame. Okay. And I'll make 3 separate variables. One for the interest rate, one for the loan amount, and one for the FICO score. Let's do that. Oh, PD is not defined. Let me run. Okay, let's run that. And let's run this again. Okay, so let's make the 3 separate variables. One for our interest rate. So that will be our data frame. And I'll pass interest rate. Okay. One for our loan amount. Let's say loan amount will be our data frame. And we'll pass the loan amount. Loan amount. And finally for our FICO score, right? I'll just name it FICO. Now let me call it FICO score. So we have our data frame. So FICO dot score. Okay. Now what we will do is reshape our data from a Pandas series to columns. Okay. That's what we'll do. And for that, we'll be using the transpose method. Okay. So we'll transpose our independent variables, which are our FICO score and loan amount. And then we'll transpose our dependent variable, the interest rate. Okay. Let's do that. So we'll be using NumPy's transpose method, which is found in the matrix library. Okay, so np that matrix, and then we'll pass what we want to transpose. Let's say interest rate, right? And then we call the transpose method on it, and we'll save that, let's say, in a variable y for dependent variable, right? And similarly, let's transpose our 2 independent variables. Okay, so np that matrix, and then we'll pass the loan amount, loan amount, and then we'll call the transpose method on it. And let's save this in a variable, x variable. So we have x, and we'll also transpose our FICO score. So np that matrix, and then we pass our FICO score, and we call the transpose method on it. And let's save that in an x variable too. Let me name this one x1 and x2. Okay, so now we have reshaped the data from our Panda series to columns. That's what we did for both of our independent variables and for our dependent variable interest rate. Now let's put our two independent variables x1 and x2. Let's put those two columns together so that we can create a matrix. Okay, so that will be our input matrix. Let's do that. So np that I'll introduce a new method. It's called column stack, and this helps us in putting together two columns so that we can create a matrix. Okay, then we'll pass x1 and x2. x1 and x2. Okay, and I'll save this in a variable called x. So this column underscore stack method takes a sequence of one-dimensional array and then stacks them as columns so that we can make a single two-dimensional array. Okay, now that we have an input matrix, we can create a linear model and then we can feed that to our data. We'll do that with the add constant method. Okay, we haven't seen the add constant method, but it's one of the the stats models method that helps us add a column to input a data set. Let's see that next. So I call the stats model API SM, that the method name is add constant, and then we pass the x that we created. Okay, the 2D input array. We haven't seen this before, but I want to introduce this now. Okay, so this add constant adds a column to input data set. Okay, and I'll save this in another variable, let's say x. Now we can create our model. Let me name this variable x3. Okay, now we can create our model. Okay, and I'll introduce to you what is known as OLS, ordinary least square. Okay, so we'll base our model on that. It's again also found on inside. It's a function found in the stats library API. Okay, it's called the OLS. Let me write it down. OLS, ordinary least square. What it does is that it takes two array objects like a data frame or array, and then it helps us to perform the regression of the predictor on the response. Okay, so in this case our predictors are the two x variables, FICO score and loan amount. So this OLS takes the two array objects that we created, so this x3 and then the y. Okay, so our independent variables, and then this y. It takes those two objects and then it helps us perform the regression of the predictor on the response. So the predictors are this x3 and the response is y, which is the interest rate. Okay, let's do that. So we have the stats module and then we call the OLS function, and then we pass our response and predictor x3. Okay, so that's our model, and let's save this in a variable called model. Okay, now that we have that, we can fit our model. Okay. Let's say model fit. Okay, and then we'll save that. We'll save our fitted model in this variable, model fit. So model dot fit. Okay. Good. Now that we have our model, there are certain functions in the stats module library that will help us determine some values. And one such value is called the p-value, the probability value, and the other one is called the r-squared method, which is the coefficient of determination. Okay, let's see those values now. So we can simply print those values. The p values are, then we just call the p values on our model fit. Okay, so model underscore fit dot p values, and then we'll do the same for our r squared value. So print the r squared value is, and then we call the r squared method on our model fit. So model underscore fit that r squared, squared. Okay, so this r squared value, it's called the coefficient of determination, and then it tells us how well the regression line approximates the real data points. Okay, let me write it down. How well the regression line approximates the real data points. Okay, that's what it tells us. And then for the probability function, for the probability value, for the p-value, it has some values, and we want that value to be below 5%, which is, we want it to be between 0 and 0.05. Okay, so that's the convention. You can read more about p-values online, okay, probability value, but basically the convention is that we want our value to be between 0 and 0.05. So if the value is less than 0.05, our model is really good. So if it's close to 0, it's really good. Okay, that's what we want our model to be. Okay, so if that value is greater than or equal to 0.05, which is if it's more than 5%, then we have less confidence in our particular dimension being useful in this model and predicting that it has an effect. Okay, in this case, if it's more than 0.05, that means we are less confident that the loan amount or the FICO score is useful for predicting the interest rate. Okay, let's run the results and see. Oh, and for the r squared value, usually the r squared lies between -1 and 1. Okay, and a good value is if it's close to 1, that's a good value. Okay, and you can read more about R squared online. I just want to touch upon those two. Let's run it and see the result. Okay, from the result we see that the p-values are, okay, we have 3 p-values. So the first one is 0, 0, then the third one is 5.96 times 10 to the power of. So this is a really close to 0 value, right? So this is almost 0 for all of our p-values. And we mentioned that p-values of less than 0.05 are great, and the closer it is to 0, the better it is. So we have really great p-values, and we have an R squared value of 0.66, and the R squared value lies between -1 and 1, and the closer it is to 1, the better it is. So our value is fairly good, right? Okay, so what can this tell us? So what we can summarize is that we have a linear regression model, right? A linear multivariate regression model. Multivariate because of FICO score and loan amount, right? So we have a linear multivariate regression model for our interest rate. And based on this results that we have, we can say that our multivariate regression model for interest rate based on FICO score and the loan amount is described by this values, right? By this model values. So we can summarize that the interest rate is influenced by both loan amounts and FICO score, right? So here we have our interest rate, loan amount, and FICO score, and we reshaped our data to columns, right? We did that for the independent variables, FICO score and loan amount, and for the dependent variable interest rate. And then we put together the two columns so that we can create an input matrix. And we did that by using the column stack method. And this column stack method takes a sequence of one-dimensional array and then stacks them as columns to make a single two-dimensional array. Once we have that, we use the StatModes API's add constant method to add a column to our input data. And then finally, we fit our data by using the OLS method to create a model. And this OLS, ordinary least square. Let me write it down. Ordinary least square. Okay. This OLS takes two array objects like data frames, and then it helps us to perform the regression of some predictor based on what we have. And then we evaluated our model based on the p-values and the r-squared values. Okay, so this is an example of a linear regression. Okay, so go through this project and see what we did. We started with our data and then we formatted it so that it serves us better, and then we visualized our data and then tried to see what other factors affect our interest rate, and then using the scatter matrix plot we discovered that the FICO score and loan amounts have an impact on interest rate, and we did an analysis on multivariate linear regression. Okay, thank you everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the lecture on logistic regression. In this lecture, we'll briefly look at logistic regression theory. Logistic regression is a form of regression which allows the prediction of discrete variables by a mix of categorical and continuous variables. Logistic regression is used to analyze the relationship between categorical dependent variables and categorical independent variables. And it's usually used if our predictors or independent variables are a mix of categorical and continuous variables. There are two types of logistic regression: binary and multinomial logistic regression. In binary logistic regression, we have two responses, either yes or no, whereas in multinomial logistic regression, the outcome variable has more than two categories. For instance, the response could be high, moderate, medium, or low. The purpose of logistic regression is to analyze the effects of multiple variables, numeric and categorical, on the outcome variable. Here, the logistic regression model is given by this formula. It's the natural log of the odds of the outcome, and this natural log of the odds of the outcome is given by the natural logarithm of probability of the outcome p divided by probability of not having the outcome, which is 1 minus p. In the above formula, each of the independent variable predictors is given a coefficient beta. So each of here the predictors are x1, x2, and they are given the coefficient beta, and that measures the contribution of variation seen in the dependent variable. And our goal is to predict the probability p that the dependent variable belongs to one group or another. Logistic regression does not assume a linear relationship between the independent variables and the dependent variables. And logistic regression also doesn't assume normality or linearity of the independent variables. Logistic regression uses what's known as a binomial probability theory, where there are only two values to predict. Either an event belongs to one group or the other, which is the binomial logistic regression. If we look at the graph here, the red line, the red straight line indicates linear probability model, whereas logistic regression model is represented by the blue curvy sigmoid line or curve. And in logistic regression, we have two outcomes. In this example, the outcome is y is equal to 0 and y is equal to 1. So this could be, if we take responses, y is equal to 0 could be no, whereas y is equal to 1 could be yes. So the outcome is either yes or no. And it's represented best by logistic regression models, the one in blue, the blue curve. Okay, here we have an example with two outputs. We have output yes here at the bottom and output no. And each of these blue lines indicate data points. And this is a linear regression model, a linear line. Whereas here, the graph below it, we have a logistic regression line. As you can see here, each of the data points are represented better with a logistic regression line or model or curve compared to the linear line here. And this is the formula for logistic regression. I won't go much into the depths of the math behind logistic regression, but if you are interested, you can check out Wikipedia. You can check out the wiki link on logistic regression to learn and read more about the math behind. Let's go to wiki and take a look quickly. So here we are at the Wikipedia link for logistic regression. As I mentioned, logistic regression is a regression model where the dependent variable is categorical. So if you scroll down here, they have an example of a logistic regression. In this example, they are showing the probability of passing an exam versus hours of study. So here they are trying to predict whether a student will pass an exam or not based on the hours of study spent. Okay, you can check out this example. A group of 20 students spend between 0 and 6 hours studying for an exam. And how does the number of hours spent studying after the probability that the student will pass? Passing is given by 0 and 1. 0 is failure and 1 is pass. And here we have the hours of sleep. This is the probability function that we briefly looked at. So they calculate whether a student will pass or not based on this function. You can read more about the coefficient, standard error, p-value, z-value, and the probability formula and method here. Okay, here we have a graph of a logistic regression curve that shows the probability of passing an exam versus the hours of study. Okay, here we have the value 0 is for failure and we have 1 here for passing the exam. So check out this example and read about more of logistic regression. You will see methods like the odd ratios, odds, and logits. You can check out what those are here. Great. We also have the Scikit-Learn, the documentation for logistic regression. Feel free to check it out to read about logistic regression. In the next lecture, we look at live coding of logistic regression. Thank you everyone, and welcome to the lecture on logistic regression. So we'll approach logistic regression in the following manner. We'll start by exploring our dataset and do some visualization. Then we'll train and create a logistic regression model, and we'll evaluate our model. We'll look at precision, F1 score, recall, and then we'll see less features and try to build another logistic regression model. We'll be looking at a dataset from University of California, and if you want to read more about logistic regression, you can see the documentation that Scikit-Learn has. Okay, you can read more about it there. Okay, back to our Jupyter notebook. As usual, we start by importing the libraries that we need. Import Pandas as PD, import NumPy as NP, Seaborn as SNS, Matplotlib as PLT, and then we have the magic function to see our graphs on Jupyter notebook. I just copied this from one of the previous lectures. Okay, and this is the location of the dataset we look at from University of California. So we'll start by loading this dataset. So we can use Pandas read CSV method, pd.read_CSV, and then we'll pass the URL, and I'll save this in a variable called data. Okay, run it. Now let's see what the dataset looks like by calling the head method. So this dataset is a dataset for students' admittance based on GRE, GPA, and the school's rank. So we'll approach this from a logistic regression perspective, and admittance will be our target. So based on these features, GRE, GPA, and rank, a student will be either admitted or not. So admittance has a value of either 0 or 1. 0 means not admitted, 1 means the student is admitted, and this is the GRE score. GPA is the student's GPA, and rank is the school's rank. So for rank, we have 4 ranks, 1 through 4, and that will be the school's rank. Okay, so based on these features, these 3 features, we'll try to build a model and see if we can predict admittance, either 0 or 1. Okay, so let's call the tail method to see how many datasets that we have. So we have about 400 records. So more about our dataset, we can call the info method to get an overall idea about our dataset. So we have 400 columns, 400 rows, GRE, GPA, rank, So they all are integers, they all are numbers, right? Integers or floats. And then the size is 12.6 KB, so not so big. Okay, let's see some statistics about our data set. For that, we can call the describe method, data.describe, and this will give us some statistics about our data set. We have a count of 400, mean value. For instance, the mean GPA of our data set is almost 3.4. We have standard deviation, and so on. Great. Next, let's do some data visualization and see what we can get from visualization. Okay, let's start by plotting a histogram of our GPA, for instance. So we can call the hist method that Matplotlib has, plt.histogram, and then pass our GPA. We can index GPA from our data frame. So GPA, make sure to pass the exact spelling. Okay, so we have our GPA, then we can specify some number of bins, let's say 35, and I like the color blue. Let's also add some labels for our x-axis by calling the xLabel method, plt.xLabel, and then we'll pass GPA. Okay, let's see. So this is what it looks like. We have GPAs ranging from about 2.3 to 4.0, and we have the number of students on our y-axis. So you see here at 4.0 we have the highest number of students with a GPA of 4.0, whereas most of the GPA lies in this area between 3.1 and 3.6. So that would be the average GPA, and that's what we saw earlier. The mean GPA is about 3.4, and you can make your plot bigger by calling the figure method and then pass the fig size attribute. You can set it to be, let's say, 10 by 6. That fits well for my Jupyter notebook. For you, this figure might be a bit different. So here we call the hist method that Matplotlib has. You can also just call the hist method on your data frame column. So we're trying to see the GPA column, right? The GPA of students. So we could have also called the hist method on it and then pass the number of bins we want to see, color, let's say blue, and then we can add labels by calling the xLabel method for our x-axis, and then simply say GPA and run it. You get the same figure. This is just to let you know that there's also another option. Next, let's see a histogram of our GRE scores. Okay, so I'll call the hist method and then index our GRE column, number of bins, let's say 35, and then let's use the green color. Okay, let's label our x-axis by calling the xLabel method and then pass the name you want, GRE score, and let's run this. So this is what the GRE score looks like. The lowest is about 230-ish, and the highest one, it looks like 800, whereas most of the GRE score, the mean of the GRE score, lies somewhere here between 500 and 700. And if we look at the admittance column, we'll see admittance as either 0 or 1, right? Those are the only two options for admittance. Let me see the column name. So if we try to see a histogram of our admittance, we'll see that we don't even need the number of bins. I'll just pass color, let's say blue. So this is what it looks like, either 0 or 1. And we see that most students are not admitted, right? So that's just to show you. We either have the values 0 or 1. Doesn't matter how many bins that you put, because the values are only 2. Okay, next let's see the rank column. We know that the rank column has the values either 1, 2, 3, or 4. So the maximum number of bins we'll have is 4. So to show you that, let's index our rank column and then call the hist method on it. So for color, let's use red. You can pass number of bins, it's optional, but it won't make any difference because you'll only get 4 bins, 1 for each rank. And from here we see that the most common rank is 2, so that's the school's rank. 2 is common, and then 3, then we have 4 followed by 1. We can also try to see the relationship between 2 of our columns. For instance, we can see the relationship between, let's say, GPA and GRE by using a joint plot. So to do that, we'll call Seaborn's joint plot method. So sns.jointplot, and then pass your x and y. For our x-axis, let's pass GPA, and for our y-axis, let's pass GRE scores. Okay, and our data comes from our data frame, and let's pass a color blue. Okay, and if we want to see a KDE plot, we can pass KDE for the kind attribute or parameter. Okay, let's run this. Joint plots, I am missing a T here. Let's run this again. Okay, here is a joint plot of your GPA versus GRE. Okay, here we see that our Pearson R value is 0.38. So there is some correlation, not a strong one. Remember, the maximum value for this is 1.0. So there is some correlation, not too much, right? So this visualization helps us to see any relationship that our features have. Okay, and we could have also plotted our joint plot without the KDE. So let's remove that so that we only have scatter plots and histograms. So that's what it looks like, GPA versus GRE. So this data visualization techniques give you an overall idea about your data set to see if they are related to each other and so on. So it's a very common technique before you build up your regression model. And in the next lecture, we'll continue our discussion on logistic regression. Thank you, everyone. Hello, everyone, and welcome back. In this lecture, we'll continue our discussion on logistic regression. Let's start by looking at our data set. So I'll call the head method. So we have 4 columns, right? Admittance, GRE, GPA, and rank. What we'll do is we'll try to predict admittance based on these 3 features: GRE, GPA, and rank. So if you consider rank, for instance, if you take the first row, the rank is 3. If you take the second row, rank is 3. Third row, rank is 1. We saw that the values for rank are either 1, 2, 3, 4. But this doesn't mean much for our logic, right? So what we'll need to do is convert these ranks into a 0 or 1 value. For instance, the first one, the rank for this first student is 3. So what we'll need to do is create a dummy variable for rank. So that dummy variable will have the values rank 1, rank 2, rank 3,
and rank 4. So we'll create these dummy variables, and for the first row the school's rank is 3, so rank 1, 2 and 4 will have the value 0, whereas rank 3 will have the value 1. And if you take this fifth row index 4, the school's rank is 4, right? So for that one, the first 3 ranks, rank 1, 2 and 3, will have the value 0, and rank 4 will have the value 1. That's more beneficial for our dataset to build our logistic regression. Otherwise, this just rank 1 through 4 doesn't mean much. So we'll create a dummy variable, and instead of rank, we'll have this rank 1 through 4. Let's start to do that, and we'll use a method known as getDummies. So Pandas has a method known as getDummies. So let's do that. pd.get_dummies, and then we'll pass our rank column. So let's index it, data, and then rank, and then we can pass the prefix attribute and then pass whatever prefix you want. I'll just pass rank, so that when we create our dummy variables, it will have rank _1, rank _2, and so on. Okay, and let's save this in a variable called, let's say, dummy ranks. Okay, now let's try to see our dummy ranks, dummy variables, by calling the head method. Let's run it. So we have, for the first row here, rank is 3, right? So rank 3 column here has the value 1. So we have created 4 dummy variables for our rank. Rank 1, 2, 3, 4. So wherever the value appears, we'll have 1. And if it doesn't appear, it will be 0. So if we call the tail method on our data set to show you the last 5 values, and let's call again the tail method on our dummy rank variable that we created here, dummy ranks.tail, run it. So here the very last row rank is 3, so the rank 3 column will have the value 1. Okay, so that's the importance of dummy variables. Okay, now that we have our dummy variables, there is a condition known as multicollinearity. What that means is, when you introduce dummy variables in your dataset, one dummy variable can influence another dummy variable. There might be some interdependence among the dummy variables, and that condition is called multicollinearity. And one method to avoid this multicollinearity is to exclude. Usually you exclude your first dummy variable. In our case, we'll exclude rank 1, and that will prevent this multicollinearity. And if you want to read and know more about multicollinearity, you can find more about it on Wikipedia. It's a phenomenon in which 2 or more predictor variables are highly correlated. You see, meaning one can be predicted from the others. So we don't want multicollinearity. That's why we'll drop the first column here, rank 1. Okay, that's what we'll do next. Okay, right now we have our dummy ranks, and then we have our other 2 features that we need, GRE and GPA. What we'll do is we'll use the data frame method and then merge or join this GRE and GPA with our dummy ranks. Okay, so let me create another variable. I'll just call it columns we need, and then I'll save we need admittance, which will be our target. GRE, and then GPA. So we'll need this from our original dataset, right? And we'll merge it with our dummy ranks data frame. Okay, for that we'll use the join method. So we have from our original dataset, we'll index our columns that we need, which are admittance, GRE, and GPA. Then we simply call the join method, and then we want to join it with our dummy ranks dataset, right? Our dummy ranks data frame here. But we said we will be dropping our rank 1 column, so we'll only index ranks 2, 3, and 4. So we can call the ix method on it, dummy ranks.ix, and we want to get all the rows, and for columns we only want columns rank 2, 3, and 4. So we have rank 2 and then colon, meaning rank 2 and everything after that. Rank 2, 3, 4. Okay, so that's the join method, and we can save this. I'll just save it in the same variable data. You can save it anywhere else in a different variable if you want, but I'll just save it in data. Okay, columns we need. Okay, we haven't run this cell. Let's run it again. Now let's run this. Okay, now if we call our data, we'll find the merged data set. We have admittance, GRE, and GPA from our original data set, and then we have the columns rank 2, 3, and 4 from our dummy ranks data set. Now we have a good data frame or data set to work with, and we are ready to build our logistic regression model. So what we'll do next is we'll split our data set into training and then testing data sets, and then we'll use the training data set to train our logistic regression model, and then we'll predict using the testing data set. And that's what we'll do in the next lecture. Thank you everyone, and see you at the next lecture. Everyone, and welcome back. In this lecture, we'll build our logistic regression model. If we look at our data set by calling the head method, we see that we have 6 columns. We'll use the admittance or admit column as our target, and we'll use GRE, GPA, and the 3 rank columns as our feature. Okay, so we'll save the features in one variable, and we'll save the target in another variable. And then we'll use the train test split method to split our data set into training and then testing sets. Once we have that, we'll instantiate our logistic regression model and then train our model on the training data sets, and we'll make predictions. That's what we'll do. The first thing we'll do is import the train test split from cross validation. Let's do that. So from Scikit-Learn cross validation, we'll import train test split, train underscore test underscore split. Okay. Next, let's save our features in a variable called x. Our features will be GRE, GPA, and the 3 rank columns that we just saw. So GRE, GPA, rank 2, rank underscore 2, rank underscore 3, and rank underscore 4. Those will be our features, whereas our target will be the admit column, which represents admittance. Okay. Now that we have our targets and features, we can split our data set into testing and training data sets. We'll use the train
test split method, and then this method accepts our target and feature, and we can pass the optional test size and random state attributes or parameters. So for test size, let's pass 0.3. So we'll use 70% of our data for training and 30% of our data set for testing. And then for the random state, let's pass a value of 23. So you can pass any value. If you want to get the same result as me, you need to pass 23, but we can pass any value for that. And once we split our data, we'll save them in 4 variables called xtrain, xtest, ytrain, and ytest. Xtrain, xtest, ytrain, and ytest. You can save it in any variable that we want, but these are common variables. If you look at the Scikit-Learn's documentation for train test split method, they use these variables: xtrain, xtest, ytrain, and ytest. But feel free to use any variables. The important thing is to keep consistent with your variables throughout your model. Okay, so later when you do predictions, make sure to pass whatever variable you define here. Okay, now if we print the shape of our xtrain, for instance, we'll see that it will be, we mentioned that we'll use 70% of our dataset for training. So the shape of xtrain will be 70% of 400 by 5, which is the number of columns. So if we run this, we have 280. So it's a 2-dimensional array, 280 by 5. 5 is the number of columns that we have, and 280 is 70% of 400. Okay. Similarly, if we print xtest.shape, we mentioned that we'll use 30% of our dataset for testing. So the shape of xtest will be 120 by 5, 120 by 5. Similarly, if we print ytrain.shape, we'll see that it's a 1-dimensional array. It will just be 280. Whereas the shape of ytest will be 120. Again, it's a 1-dimensional array, 120. Again, this is all derived from our x and y, right? So if we try to print the shape of x and y, let's first print the shape of x. Print x.shape and then y.shape. You'll see that the shape of x is 400 by 5, whereas the shape of y is just 400. So this is 2-dimensional array and y is 1-dimensional, right? 400 by 5 and just 400. So these numbers are 70% and 30% of our data set. Great. Now that we have split our data set into training and then testing data, we'll instantiate our logistic regression model and then train on the training dataset. First, we'll need to import logistic regression from Scikit-Learn. So from sklearn dot linear model, linear underscore model, import logistic regression. Okay, that's in the documentation, how to import it, where to import it. Okay, you don't need to memorize this. So from sklearn.linear model, import logistic regression. Now that we have imported logistic regression, let's create an instance of the logistic regression class. Okay, and we'll save it in a variable called model. So model is equal to logistic regression. So this is an instance of our logistic regression model. Okay, and you can read more about it on the documentation here on Scikit-Learn. Okay, Scikit-Learn that linear model
has our logistic regression class, and these are all the optional parameters, and the descriptions are in here. Okay, you can read more about it here. Great. Okay, so if you call your model now, you will see all the parameters used in your logistic regression model. You have the C value for regularization, class weight, and all of this. Okay, now that we have created an instance of our logistic regression model, the next thing we'll do is use the fit method to train our model on the training datasets. So we'll call the fit method on our model and then pass our training datasets, which are xtrain and then ytrain. Now that we have trained our logistic regression model, the next thing we'll do is call the predict method on our model and make a prediction by passing the testing dataset, the xtest. Let's do that. So model.predict, and then we'll pass xtest. So we'll be using the testing dataset for making predictions. Okay, that's why we divide our dataset into training and then testing. So we can use the training dataset to train our model, and we use the testing dataset to test our predictions. So we don't use the same dataset for both training and then testing. Okay, that's why we separate them into training and then testing. We'll see our model's prediction on the new dataset. Okay, so this dataset, our model has not seen this dataset. This is new. So we use that for our prediction. Okay, that's the importance of splitting your dataset into training and then testing sets. Okay, in any kind of model. And let's save this in a variable called prediction. So prediction is equal to model.predict. Great. Next, we need to evaluate our model, right? Our logistic regression model. We need to evaluate its prediction. For that, we'll be using what's known as classification report. Okay, this classification report will tell us the precision, recall, and F1 score values for our logistic regression model. Okay, first, we'll need to import classification report from Scikit-Learn, and it's in the metrics library. Let's do that. So from sklearn.metrics import classification report, classification underscore report. Okay, and this classification report takes the values, your actual and then your actual and prediction values, and then it will print out your precision, recall, and F1 score. Okay, so we can simply say print classification underscore report, and then pass your y-test, which is the actual value, the actual admittance value, and then our prediction from our model, and run it. So this is your classification report for our logistic regression model. Precision, recall, and F1 score. So here it splits it by for the two values for our admittance, not admitted, and then one is admitted. So we see that our model did great for the not admitted students. We see we have a precision of 77% for not admitted, a recall of 90%, and F1 score of 83%, whereas for the admitted students, the precision was 50%, recall was 28%, and F1 score 36%. And here you have the average of your entire model. So the average is 70% precision, recall value is 73%, and F1 score is 71. So these are low scores. You can read more about what precision, recall, and F1 score mean on Wikipedia, or you can refer to the Scikit-Learn's documentation. So in short, precision is the ability to not label as positive a sample that's negative. Okay? Whereas recall is the ability of your classifier to find all the positive samples. And you can read more about precision and recall and F1 score values on Wikipedia. But this is one method that we use to evaluate our logistic regression model classification report. Okay? We'll see classification report in some other models in the future lectures also. But this is generally a low score. So the higher the scores are, the better your model will predict the values. Okay? So now we have 70%. On average for precision, our model predicts 70%, recall 73%, and F1 score of 71%. So this is what we have based on these features: X, GRE, GPA, and the 3 rank columns: rank 2, rank 3, and rank 4. So if I go to the beginning of this notebook, when I introduced, I mentioned that we'll start by exploring our dataset and visualizing, and then we'll create a logistic regression model. And for evaluation, we used precision, F1 score, and recall. And here we have what if we consider less features. So here basically we only have 3 features, right? GRE, GPA, and rank. Even if we have 3 rank columns, we have 3 features, right? I'm taking rank as 1 feature, but we have split it into 3: rank 2, rank 3, and rank 4. Do you think we'll get a better classification report if we only consider, let's say, just GRE and GPA as features? What do you guys think? So we'll see that in the next lecture. We'll build a model using only GRE and GPA features and compare our model with this model and see if it can do a better result in the classification report. Thank you, everyone. Hello, everyone, and welcome. In this lecture, we'll build another logistic regression model using GRE and GPA as features. Okay, so let's start by looking at our dataset by calling the head method. So we have the admit column, GRE, GPA, and the rank columns. So we'll use the admit column as our target, and this time we'll use only GRE and GPA as our features. And once we build our model, we'll compare it to the first model that we built in the previous lecture. Okay, let's get started. So the first thing we need to do is save our features and target in variables. I'll save them in X and Y variables. So I'll set X to be our GRE and GPA. So data, and we'll index GRE and GPA, GRE and GPA. For our target, it will be the admit column. So data, and then let's index admit. Okay, so let's print the shape of our features and target. So x.shape, this should be 400 by 2. So a 2-dimensional array, 400 by 2, whereas the shape of y is just 400. Next, let's use the train test split method to split our dataset into training and then testing datasets. Okay, I have already imported the train test split in the previous lecture. If you haven't, you need to import it. So train test split, and then we'll pass our features and then target, and then let's use a test size of 30%. So we'll use 70% of our dataset for training and 30% of our dataset for testing. Then let's pass the optional random state
parameter, and then I'll set it to be 23 as in the previous lecture. So if you want to get the same result as me, you need to pass a random state of 23. Otherwise you can use any other random state. But if you want your results to match mine, pass 23 for random state. And we'll save, once we split our dataset, we'll save them in 4 variables: xtrain, ytrain, xtest, ytest, xtrain, xtest, ytrain, and then ytest. As I mentioned before, we can save it in any variables that we want, but these are common ones used and also mentioned in Scikit-Learn. Okay, so now if we print xtrain.shape, it will be, since this is a training dataset, it will be 70% of 400, which is 280. So it will be 280 by 2. Similarly, if we print xtest, it will be 120 by 2. Print xtest.shape, it will be 120 by 2. Whereas if we print our ytest.shape, and let's also print ytrain.shape, so this will give us, these two are one-dimensional arrays. So for testing ytest, it will be 70%, which is 280, and 120 for ytrain. I'm sorry, that's the way around. For testing it will be 120, whereas for training it will be 280. So once we split our dataset into training and then testing datasets, we are ready to instantiate our logistic regression model. Okay, and we'll save it in a variable called model2. So we'll set that to be equal to logistic regression. Okay, so we are creating an instance of the logistic regression class. Again, if you haven't imported logistic regression, please import it from Scikit-Learn's linear model. Okay, now that we have instantiated our model, the next thing we need to do is call the fit method and then train our model on our training datasets, which are xtrain and ytrain. Okay, now that we have trained our model, we can call the predict method and then pass our xtest dataset, and we'll save this in a variable called prediction2. Great. Next, let's evaluate our model by using classification report. So we can simply print classification report, classification underscore report, and then it takes the actual and then the actual value of the actual prediction, the actual admittance, and the prediction values. So the actual admittance is ytest, and then we'll pass our prediction 2. Okay, so this is the metrics that we use for evaluating our logistic regression model, classification report, and this will print out the precision, recall, and F1 score for our model. And if you haven't imported, you need to import it from Scikit-Learn, from matrix. Okay, now let's print the classification report. If I run this, so we have an average precision of 54%, recall of 73%, and F1 score of 62%. So let me also print out the classification report from our first model. So print classification underscore report, then we'll pass ytest and our first prediction, which we saved it as just as prediction. Okay, let's run it. So if we compare our two classification reports, so for precision, we see that our first model has a 70% precision, for recall 73%, and they are even, we'll talk about it. For F1 score,
our first model has a 71% F1 score. So it looks like our first model does a better job in predicting. So one reason we can state from this is that the 3 rank columns are important in this classification in predicting our logistic regression model. Okay, whereas in the second logistic regression model we omitted the 3 rank columns, right? We only consider GRE and GPA. So that's why the score is lower. The precision F1 score are lower compared to our first model. Okay, so those rank columns play a crucial role. So those are important features. Okay, and here we have a warning that says precision and F1 score are ill-defined and being set to 0 in levels with no predicted samples. Okay, that's what you see here. So for admittance, the second model set the values to 0. So it's important to consider all your features in building your logistic regression model. Okay, I just wanted to show you that by doing the second regression. Great. Just to summarize what we have learned in the previous lectures for logistic regression, we started by exploring our dataset and grabbing general information. We used methods like the info and describe to get some general information and statistics about our datasets, and then we used some data visualization techniques to get an overall idea about the distribution of the various features and to see if there is any relationship among our features or columns. After that, we analyzed our dataset furthermore and then created dummy variables for the rank column. And once we have that, we were able to generate a new data frame by joining the admit GRE and GPA columns with the newly created rank dummy variables data frame. And then we were able to build our logistic regression model. In order to do that, we first defined our features and targets and then split our dataset into training and then testing datasets. After that, we used our training datasets to train our model and then used the testing dataset to test our model. And we saw the classification report to evaluate our model. And we saw precision, recall, and F1 scores. Okay, that's what I have for the lecture on logistic regression. If you want to read more about logistic regression, a specific section or parameter or any specific attribute, you can refer to the Scikit-Learn documentation. You can read more about it there. It's a good documentation. Great. That's all I have for this lecture. Thank you, everyone. Hello, everyone, and welcome to this project. In this project, we look at logistic regression to predict diabetes status. We'll be looking at UCI's machine learning repository dataset on diabetes status. We'll look at the PIMA Indian diabetes status database. Okay. So we'll look at PIMA Indian diabetes dataset, which is in UCI's machine learning repository located here. This is the website. So we'll try to predict diabetes status based on certain health conditions, based on certain parameters like glucose level, blood pressure, age, BMI, and so on. So first thing we will do is, I already saved the data from this website. This is what it looks like. I saved it as a CSV file where my Jupyter notebook is located.
or you can directly work and grab data from this link. So I'll leave that to you. Let's get started. As usual, let's import pandas as PD, import numpy as np. I don't think we'll need numpy, but just in case. So you can copy all the modules and libraries from a previous lecture if you want. The first thing we'll do is try to grab the data and see the content. For that, we'll be using pandas read CSV method. So let's do that. pd.read CSV. Then if we want, we can save this as a URL and paste the URL. But in my case, I have already saved it as pima.csv. And let's save this in a variable called, just gonna name it pima. So pima.head. Let's see what it looks like. Okay, I have this. So the first row is indicated as a column name, but that's data. So what I will do is I'll create a list that will hold the column names for my data set. Let's do that. I'll just name it column and then pass. So these are like the pregnancy months, 6 months, 1 month pregnant. This person was 8 months pregnant, and so on. And this is the blood glucose level, blood pressure, and then it goes on like that. So let's do that. Pregnant. So those will be the title for our data set. Then glucose level. Then we have blood pressure. Then we have skin. Then we have insulin level. Then we have BMI. Then we have pedigree. We have age, and next we have diabetes level. So that's yes, they have diabetes, or no, they don't have diabetes. So I'll pass that in my pd.read CSV. We'll pass pima.csv. They will pass column names as colon. Let's visualize it. Let's see our data now. pima.head. Okay, looks much better. So we have all those column names now. And if I call the tail method on it, so we have about 760 records. We can count the count method on it also. So pima.count. So that tells us how many rows that we have. So we have 768. And we can also call the describe method on our dataset, pima.describe, and that gives us a statistical inference on all of these columns: pregnancy, glucose, BP, and so on. Okay, next let's see if we can predict the diabetes status of a person given some of these features. Okay, we look at pregnancy, insulin level, BMI, and age features. We'll use those to predict whether a person has diabetes or not. Let's do that. So I'll save those features in a variable called features. So pregnant, insulin level, BMI and age, and I'll define X and Y variables. So X will hold these features, whereas my Y will be the label, whether the person has diabetes or not. So let's do that. So X is equal to our PIMA dataset, and then we'll pass our features, and we'll define Y to be as the label. So PIMA dot diabetes label. This should be insulin level. Let's run it again. Okay, now we can split our dataset into training and testing datasets. So that's what we have been doing. So we'll set X train, Y train, X test, and Y test. Let's do that. So X train, Y train, X train, X test, Y train, and Y test. And we'll set that to be, we'll use the train test split method, and we'll pass our features and our label dataset, and let's use a random state of 0. Okay, before we do that, let me import the train test and split from Scikit-Learn, from sklearn.cross validation. We need to import train test and split. Once we have split our dataset into training and testing sets, the next thing we need to do is train our model on the training sets. We'll be using logistic regression, so we'll train our logistic regression model. Let me first import logistic regression from Scikit-Learn. So from sklearn, that linear model, import logistic regression. So let's train our model, logistic regression model. I'll save this in a variable logistic regression log reg, and then we'll fit our model with our training data set. So log reg, and then we'll call the fit method, and then pass our training datasets X train and Y train. Next, we can make a prediction on the testing set. Let's do that. So we call our fitted logistic regression model, and we call the predict method on it, and we pass our testing set. And I'll save that in a variable called ypred. Now that we have made a prediction for our testing data set, we can check the accuracy of our model in predicting diabetes status. Let's use accuracy score for that. We can simply print the accuracy score. Before I do that, let me import metrics from Scikit-Learn. Import metrics. Once we have that, we can simply print the accuracy score, right? Print metrics that accuracy score underscore, and then we pass our y test and ypred. So we have an accuracy score of 69%. So our logistic regression model can accurately predict diabetes status with an accuracy of 69%, given those features: BMI, insulin level, pregnancy, and age. So that's the logistic regressions model accuracy score. We have 69% accuracy using our logistic regression model that will predict diabetes status in the PIMA dataset given these features. Hello everyone and welcome back. Let's continue with our discussion. Next, we'll evaluate our model using a confusion matrix. Before we do that, let's see some more methods on our dataset. We can call the value count on our y-test data to see how many people have diabetes and how many don't. So value counts. Okay, we'll see that 62 people have diabetes. 1 means yes for diabetes, 0 means no diabetes, and 130 people don't have diabetes. And to calculate the percentage of those numbers, we can simply call the mean method. So y-test.mean. So it means 32.3% of all the people have diabetes, and the remaining percentage don't have diabetes. That's about 67.7%. And we can also print out the actual and predicted result by simply printing using a value method. So I can say print, let's say true status or true label, true diabetes label. Then we can pass our y-test dataset and then do a values count. So if we simply leave it like this, it will print out the result for all of those people. But let's just see the first 15 people. Okay, so I'll pass index 0 to 15, and that's the true diabetes label. And let's see our predicted diabetes label for those 15 people. Print, we can say predicted diabetes label, and for that we use our ypred data, ypred, and then pass the same index 0 to 15. Let's run it. So true diabetes label, let me put some more space so that it can align. Let's see now. Okay, so the first row we have true diabetes label, yes, no, no, yes, and so on. And here we see our predicted diabetes label. Our model predicted the label like that. So we can also have an overview of the true and predicted labels by just using a simple print statement. Now let's use confusion matrix. So we can simply print the confusion matrix. Print matrix that confusion matrix, confusion matrix, and then we simply pass our y-test and ypred datasets. So y test and then y print. Oh, this is confusion. Let's run it again. Okay, so here we have our confusion matrix. So these labels are 118 is true positive. So if you have heard of true positive, false positive, true negative, and false negative, so these are the results. 118 is true positive value, and then 12 is false positive, 47 is our false negative value, and then 15 is our true negative. So you can read more about confusion matrix and this true positive, true negative on this wiki site. So it talks about that in much more detail and depth. We'll briefly see it in this lecture, but you can read more about it here. I'll leave the link in our project. So true positive means that our model has correctly predicted that those people have diabetes. That's what true positive means. And true negative means our model has correctly predicted that those people do not have diabetes. That's true negative. And false positive means, so this false positive and false negatives are errors. They call it as type 1 and type 2 errors. And one predicts that we incorrectly predict that those people have diabetes. That's the false positive value. And the false negative value means that our model has incorrectly predicted that those people don't have diabetes. That's the false negative value. So you can read more about those in this wiki link. So earlier we have seen the accuracy of our model by printing the accuracy score. So this accuracy score is the same as true positive plus true negative divided by all these four results. True positive plus true negative plus false positive plus false negative. That's the accuracy score in general. Okay. How accurate is our model? How accurately can our model predict diabetes status? That's the accuracy score. So that's our classification, the accuracy of our model. And there's also error of our model. The error is basically, we saw that our model is 69% accurate, so the remaining 31% will be the error, and that's calculated by taking the sum of false positive plus false negative. So the error is calculated by taking the sum of false positive plus false negative, and we divide all of that by true positive plus true negative, true positive plus true negative plus false positive plus false negative. That's how the error is calculated. And the other terms you might come across as sensitivity and specificity. You'll read more of that here. And sensitivity is the ratio of true positive divided by true positive plus false negative. Sensitivity means when our value is positive, how well is our prediction doing? So how often is our prediction correct when the actual value of the result is positive? That's sensitivity. And you can also calculate sensitivity by using the recall score method. So if we print matrix that recall score, that's the sensitivity, and then we pass our y-test and y-print datasets. So that's the sensitivity, 24%. And there's a term known as specificity. Specificity is the opposite of sensitivity. So in sensitivity, we are calculating how well our prediction is correct, how often is our prediction correct when the value is positive, right? But in case of specificity, we check how often our prediction is correct when the actual value is negative. Okay, that's specificity. And the last point I want to touch is precision. And we can calculate precision by using the precision score method. And precision basically means how often is our prediction correct when our positive value is predicted. So that's only concerned with positive values. Okay, so it compares true positive with the sum of true positive and false positive. So when all our values are positive, when all our predicted values are positive, how often is our prediction? How often is our prediction correct? That's the precision. And we can calculate it by calling the precision score method. Print matrix that precision score, and then we pass y-test and y-pred, and we get about 55.6% precision. Okay, these are some of the terms that you might come across, and we have seen, you will also see recall, F1 score, and some other terms, but I just wanted to quickly touch on those. And again, you can read more about specificity and sensitivity and this true positive, false negative, all those values. So here you have the ratio and terminology, what each of them mean. F1 score, Matthews correlation coefficient, accuracy, and so on. Okay, so just to recap, in this project we looked at the Pima Indian diabetes dataset, and we tried to predict diabetes label by using logistic regression, and we considered pregnancy, age, BMI, and insulin level as features. And our logistic regression model has a 69% accuracy in predicting diabetes status in the Pima Indian dataset given these 4 features. Great. Thank you everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the lecture on k-means clustering. In this lecture, we look at the theory behind k-means clustering. Cluster analysis is an unsupervised learning method. The goal is to group or cluster observations into subsets based on the similarity of responses on multiple variables. Observations that have similar response patterns are grouped together to form clusters. Let's see an example. Researchers might use cluster analysis to identify individuals that are at greatest risk for health problems and to develop targeted health messages based on patterns of health behavior. With cluster analysis, what we want is to obtain clusters that have less variance within clusters and more variance between clusters. That is, we want observations within clusters to be more similar to each other than they are to observations in other clusters. More variance between clusters means the clusters are distinct. Let's look at the k-means clustering algorithm. So the first step in cluster analysis is to randomly choose 3 points. these points will start as the center or centroid for each of the clusters. So the 3 points are represented by the circles, which are called centers or centroids. And once we choose those 3 points, the next thing we do is we calculate the distance between each of the points, each of the individual points, and the cluster centroids. For instance, let's take the point X. We measure the distance between the point X and one centroid, and then we measure the distance between point X and the second centroid, and finally we measure the distance between X and the last centroid. Then the point is assigned to the cluster that has the smallest distance between it and the cluster centroid. In this case, the blue centroid. So that's done for every point or observation in our dataset. Then the process starts all over again by calculating the distances between the points and the new locations of the 3 centroids, reassigning points to the closest centroid, and then we relocate the centroid to the place where the sum of the new distances for the points assigned to the cluster is at the minimum. And the most common way to calculate the distance between observations is by using the Euclidean distance method. This Euclidean distance measure determines how close observations are to each other by drawing a straight line between pairs of observations and then calculating the distance between them based on the length of this line. Again, in this example of cluster analysis, we first choose 3 points randomly, and these points will start as the centroid for our clusters. Then the distance between each point and cluster centroids is calculated. For instance, if we take the point X in the figure and we measure the distance between point X and one centroid, and then between X and the second centroid, and then the third centroid, then the point is assigned to the cluster that has the smallest distance between point X and the cluster centroid. In this case, the blue centroid. Then we take another point and the process starts again. And the most common way to calculate the distance between observations is done by using what's known as the Euclidean distance method. We'll use this Euclidean distance method when we get to the live coding section. So for more documentation on k-means clustering and more examples, you can check out the k-means clustering on Scikit-Learn. I have provided the link here. Let's briefly look at it and we'll jump to Jupyter Notebook. Here we are at the Jupyter Notebook documentation for k-means clustering. You can read more about it here and the methods and algorithms used. Great. Let's jump to Jupyter Notebook and see some live codings. Thank you, everyone. Hello, everyone, and welcome to the lecture on k-means clustering. We'll approach k-means clustering from a case study approach. We'll look at a dataset of students, and this dataset has various characteristics and has information regarding whether the student has any alcohol problems or any violent problems, how's the student's relationship with their parent, and if there is any family connectedness or not. So these are some of the features of our dataset. And our goal is to group students or cluster together students with similar characteristics into a cluster. And once we group together similar students with similar characteristics into subgroups or clusters, we can then approach that subgroup and then apply the interventions that we need so that we can help them out. Let's start by importing the libraries and modules that we need. I copied this from one of our previous lectures. Import Pandas as PD, NumPy as NP, import series and data frames. We have Matplotlib for visualization, and we have our magic function Matplotlib inline to see graphs in our Jupyter Notebook. First, let's use Pandas read CSV method and check out our health data.csv. Let me copy this and then use Pandas read CSV method, and I'll save our dataset in a variable called data. pd.readcsv. Okay. Next, let's call the head method to check out our dataset, data.head, right? So these are the columns and some general information about our dataset. We have gender here, whether male or female, age, and notice here we have some missing values, no values here. We have age and a number of these columns. We have GPA, and I have left here so the meaning for some of the columns. Here means if you see alk probs 1, it means alcohol problems, and it has values from 0 to 6. Deviant 1 means, for instance, this deviant 1 column means it will give us information about a deviant behavior. We won't go into specifics of what is a deviant behavior or not, that's another topic, but we'll just approach and use these values to divide or subgroup our students into clusters with similar characteristics. And this violent means, viol 1 means violent behavior scale. DEP stands for depression. We have parental activity, parental presence, family connectedness, and self-esteem. So those are the meanings for some of these behaviors or characteristics. And for our approach, we will only consider the following variables. Okay, and you'll find out the meaning of these variables in here. Okay, so we'll use these variables, these clustering variables, to group together students with similar characters. If we call the tail method data.tail, run it, we have about 6,500 rows. And let's call the info method data.info. That's some information. The size of the file is about 1 megabyte, a bit over 1 megabyte. And here, if you see, we have some missing values, as the number of rows is different for each of these characters, for each of these columns. You see here 6,504, 6,369, 4,800, and so on. So what we'll do is we'll drop any of the no values by calling the drop NA method. And let's also make all the column names uppercase. Okay, we can do that for better visibility. So we can use the map method and then make all the column names uppercase. Let's do that. So we'll take our columns and simply call the map method, and we have a string upper method, and then we'll apply it to our columns. Okay, and we'll save them. Once we convert our columns into uppercase, we'll save it in the same variable. And let's also drop no values from our dataset, and we'll save it in the same variable data. That will be equal to data.drop NA. Okay. Now if we check out our dataset, we shouldn't have any NAs. So data.head, and all the column names should be uppercase. Okay, looks much better, much nicer, I guess. And then if we call data.info and run it, now we see we have 4,601 rows. Okay, there is no missing value now, no missing data. And the size of the file is a bit lower now because of that. And this is what we usually do in data science, in data analysis. We spend most of the time in preparing our data so that we can use our dataset for various purposes. Okay, and I have here, we will consider the following clustering variables. Okay, let's not forget that. Let me copy this. Okay, and then paste it somewhere here. What we'll do next is let's import all the libraries that we need for our k-means clustering. The first one is we need to import the train test split from Scikit-Learn's cross-validation from sklearn that cross-validation. Let's import train test and split. The next one is let's import k-means. We import the k-means library from Scikit-Learn's cluster from sklearn.cluster import k-means, and you can check out the documentation here for k-means clustering on Scikit-Learn. You can read more about any of the methods that we are going to use. We will also be using the pre-processing library, so let me import it now from sklearn import pre-processing. Yeah, this is learn, not lean. Let me run it again. So those are the libraries that we'll use mostly, and any other libraries that we need, we'll import them later on as we need them. Great. Again, our goal is to subdivide our dataset into subgroups, and we'll consider students with similar characteristics to form a cluster. And once we have that, we can apply various interventions to those clusters or subgroups, since they are going to have similar characters. And we'll be considering the following variables to do our k-means clustering. Okay, so I'll save these variables I'll save all these features in a variable called cluster, and then we'll simply index the variables from our dataset. Okay, and here we have a few variables, about 8-9 variables, and in cluster analysis, those variables with larger values contribute more towards distance calculations. And since all of these variables are measured on different scales, we'll have to standardize them before we do any kind of clustering. Okay, that way our clustering will not be influenced by variables which are measured on larger scales. So for that matter, standardizing these variables is important, and when we standardize these clustering variables, they will all have a mean of 0 and a standard deviation of 1. So that's an important point to remember. And once we standardize them, our clusters will not be influenced by variables measured on larger scales. That's what we'll do next. And for that, we'll use a method known as scale, which is found in the pre-processing library. That's why we imported this. Okay, let's do that. So let's standardize our variables so that they will have a mean of 0 and a standard deviation of 1. What I will do is I'll take our cluster data here, our clustering variables, and then make a copy, and I'll save this in a variable called, I'll just save it in a variable called cluster_s. You can save it anywhere that you like. Now what we'll do is we'll take each of these features and then apply the scale method on them. That way we'll standardize them to have a mean of 0 and standard deviation of 1. Okay, let's do that. So let's take the first feature here. I'll copy the feature and let's first index it. We have cluster_s, and then we'll index our first feature, and we'll set that to be equal to, we'll call the pre-processing that we imported, and then it has a method known as scale, and we'll pass our feature name, so we'll pass it as an index. So I'll copy that and paste it here, and then we'll call the asType method, and let's pass float 64 for asType. So what we're doing here is we are standardizing each of these clustering variables.
by using the scale method from pre-processing. So we call the scale method and then pass your clustering variable, and we'll convert it into a float 64. Okay, and then once we did that, we just saved it in the same variable, cluster s, and then our clustering variable name. Okay, so we'll do this for each of our clustering variables. So if I copy this and then paste it here, so I'll change this to the second variable, which is this. So we call the scale method and then pass the variable, our clustering variable, and then we'll change it to a float by calling the asType method. Okay, and what I'll do next is I'll just pause the video and standardize each of the clustering variables by doing the same thing. I'll just copy paste this and apply it for each of these clustering variables and then come back to it to save some time. Okay, now that we have standardized all our clustering variables, what we'll do is we'll calculate the average distance of observations from our cluster centroids, and later we'll plot the average distance to help us figure out how many clusters would be optimal for our problem or dataset. And then we'll create some object called clusters, and that object will have a value range between 1 and 10, and we'll use that object to specify the number of clusters that we want to test. For us, we'll try out k values from 0 to 10, and next we'll create a mean distance object to calculate the average distance that we calculate for each of those 1 to 10 clusters, and then after that we'll find out which k value or which is the optimal number of clusters. And that's what we'll see in the next lecture. Thank you, everyone. Hello, everyone, and welcome back. This lecture will continue our discussion on k-means clustering. Specifically, we'll do a k-means cluster analysis for 1 to 10 clusters. Okay, let's start by splitting our dataset into training and testing datasets. And for that, we'll use the train test split method. We have already imported that, and then we'll pass our cluster as standardized clustering variables. We'll pass a test size of 0.3, 30%, and then let's pass a random state of, let's say, 222. And if you want to get the same result as me, you can pass 222 for your random state. And we'll save this in a couple of variables. I'll name them cluster train and cluster test. Okay. Here we're not doing xtrain, xtest, ytrain, and ytest as before. We're not that much interested in all of those. We're simply interested in making clusters, right? That's our goal. So that's why I'm dividing our dataset into training and then testing datasets only. And if you check the shape of this cluster train and cluster test dataset, you'll see that it's two-dimensional. Okay, so let me show you that. Let's print out the cluster train dot shape and cluster test dot shape. Oh, I'm missing an alphabet here. Let me run it again. So here it's two-dimensional. For our cluster train, it's 3,200 rows by 11 columns, and for our testing, it's 30% of 4,600. I just wanted to divide our dataset into training and then testing sets. So when we build our cluster, I will be using the cluster train dataset for building our cluster. So we'll be doing a cluster analysis for 1 to 10 clusters. So I'll start by defining a variable called clusters, and it will have values from 1 to 10, so we can use the range method. And then once we create that object, we'll specifically
we can specify the number of clusters that we want to test from all those range values from 0 to 10. Okay, and then for that we'll use a for loop, and we can say something like for k in our cluster object, and then we can have some more codes. Okay, let me type the code and explain as we go by. I think that will make more sense. Okay, I'll start by defining the clusters variable, and we'll say range 1 to 11 so that we can have 10 clusters. Okay, let's also define another variable. I'll just call it mean distance, and I'll create an empty list, and later we'll append to that empty list. So what I will do is we can say for k in our clusters. So for k in clusters, we'll build our model, our k-means model, and then we'll pass number of clusters. Number of clusters, we'll set it to k. So when k is 1, the number of clusters will be 1. When k is 2, and so on. So for k in clusters. And let's save our model in a variable called model, and then we'll take our model and then train it with our training dataset by calling the fit method, and we'll pass the variable that we created, cluster, the training dataset that we created, cluster train, and then we'll use a method known as cdist. Or before we use that, let's import cdist from SciPy. So what I will do is from SciPy that spatial that distance, let's import cdist. It's used to calculate what is known as the Euclidean distance. I will talk more about that in a few minutes. Okay, let's apply the cdist method, and then it takes our data points, our centroids, and then Euclidean, which is the method. So let's pass those. For our dataset, we'll use the cluster train dataset, and then for the centroids, to calculate the centroids, there is a method known as cluster centers. So we can call that method on our model. So cluster underscore centers, that's the method name, and underscore. You can read more about this on the Scikit-Learn documentation. And the third attribute this method takes is Euclidean, which is the method that we'll use. Okay, and then what we'll do next is take our mean distance empty list, and we will append the result to it. So we'll call the append method, and we'll be appending this, but we're not just appending the result of this cdist method. We'll take the minimum of those errors. So for that, we'll pass another method known as minimum. NumPy has a method known as minimum. So we'll grab the minimum of those, and then we'll add each of that. Let me go to a new line. And since we are calculating mean, here we have mean distance. Since we are calculating mean, we'll divide our result by number of our cluster train dataset, which is 3220. So let's divide it by our cluster train, cluster underscore train that shape, and then we'll pass index 0. So this cluster train that shape is simply means the number of data points or rows, which is 3220. Okay, now let's break down what we did. We started by creating a variable clusters, and here we have 10 clusters, right? We use the range 1 to 11, that means 1, 2, 3, all the way to 10. And then we created an empty list known as mean distance. And then we used a for loop and said for k in clusters. So the first k value will be 1 when k is 1. Then we're building a model. K means we are instantiating our model, and then pass the number of clusters.
our k-means accepts an attribute known as n underscore clusters for number of clusters. So for each k in clusters, we are building our model, and then we're training our k-means model with our cluster train dataset. And here we have the mean distance. So this mean distance that append calculates the average of the sum of the distances between our observation in the cluster centroids. So this formula first calculates the distance between each observation and the cluster centroids, and then we use this cdist function or method to calculate the distance. And the cdist method accepts three parameters: your data points, in this case cluster train, you have number of centroids, and this Euclidean. So this Euclidean tells Python to use cdist to calculate the distance between each observation in our cluster train dataset in the cluster centroids using Euclidean distance. And once we calculate that distance, we use NumPy's minimum function to determine the smallest or the minimum difference for each observation among our cluster centroids. Okay? And this axis is equal to 1. It just means that the minimum should be determined by examining the distance between our observations and each centroid. And we take the smallest distance as the value of our minimum, and then we use the sum function to sum the minimum distances across all of our observations. And finally, we divided that result with this cluster train dot shape. This just means the number of observations in our cluster train dataset. So if I print out, just to show you that, if we simply print cluster train dot shape and index 0, we simply get 3220. Since we are calculating the mean, we are dividing it by the number of our observations in our cluster train dataset. Okay, now that we have the average distance calculated for each of our 1 to 10 clusters, we can plot the elbow plot or curve. We can plot the elbow curve by using Matplotlib. Okay, and that's what we'll do in the next lecture. Okay, it's important to understand what we did here. Again, just to summarize, once we created our clusters, we used for loops to create a model for each of our clusters, for each of our cluster value k, and this mean distance calculates the average of the sum of the distances between each of the observations in our cluster centroids. So we have a centroid, and then we calculate the distance from each observation up to the centroid, and it does that for all of our data points. Okay, so this first calculates the distance between each observation and our cluster centroids. Then we used this cdist method to calculate that distance. And the word Euclidean here in the cdist attribute, it just tells Python to calculate the distance between each observation in our cluster train dataset in the cluster centroids using Euclidean distance. And you can read more about this Euclidean distance on Wikipedia. Okay, I won't go much into that, but this is a common method now used to calculate the distance between observations and centroids in k-means clustering. I won't go in depth into that, but feel free to read more about this Euclidean distance on Wikipedia. Okay, and once we calculate the distance between each of our training dataset and the centroids, we use NumPy's minimum method or function to determine the minimum difference for each observation among our cluster centroids. And this axis is equal to 1. It means the minimum distance should be determined by examining the distance between the observation and each centroid by taking the smallest distance as our value of the minimum. And finally, we use the sum function to sum the minimum distances across all of our observations. And once we have that, we divide the result by the number of observations in our clustering dataset. Okay, and that's what this line of code means, or that's what it does. And in the next lecture, we'll plot an elbow curve graph for each of these clusters and see how many clusters to use for our k-means clustering model. Thank you, everyone. Hello, everyone, and welcome that. Now that we have calculated the average distance for each of our clusters, 1 to 10, we can plot the elbow curve using Matplotlib. Let's do that. So plt.plot. Okay, let me give it some title. Let's plot the elbow curve. So plt.plot will pass clusters, which is 1 to 10, and then we'll pass our mean distance. And let's label our graph plt.xLabel, and we'll call it number of clusters, and we'll name our y label distance or average distance. plt.ylabel, we'll name it average distance. Let's also give a title for our plot by calling the title method on our Matplotlib. So we'll call it elbow method for our k values. Okay, let me run it and show you what it looks like. So this is the elbow curve, and on the x-axis we have our number of clusters. From here are the number of clusters 1 to 10, right? And on the y-axis we have our average distance, and this is our elbow curve. And we can use this elbow curve to select specific k values for our clusters. So what this plot shows us is that the decrease in the average minimum distance of the observations from the cluster centroids for each of our clusters. And we see that as the average distance decreases, as the number of clusters increase, the average distance decreases, right? And since the goal of our cluster analysis is to minimize the distance between observations and their assigned clusters, so we want to choose the fewest numbers of clusters that provides us a low average distance. And what we look for in an elbow curve is a bend in our elbow, and that shows where the average distance value might be leveling off, such that adding more clusters will not decrease the average distance that much. Okay, so it's kind of subjective where we will choose. For instance, here we see a bend, one bend here when k value is 2, and then we have another bend here when k value is 3. Then we have our last bend, not that much, but I see a bit of bend here when k is equal to 6. So the main bends are when k is equal to 2 and k is equal to 3. So we'll consider those two bends mainly, and I'll also show you when number of clusters is 6 and compare our result to those two clusters. The bend appears when k value is 2 and when k value is 3. So which cluster shall we consider? And to help us figure out the solution, we'll deploy some more techniques. Just to summarize, we see that the average distance decreases as the number of clusters increases, and the goal of our cluster analysis is to minimize the distance between observations and their assigned clusters. So we want to choose the fewest number of clusters that provide a low average distance. And here there appears to be a bend when k is equal to 2 and k is equal to 3. And to help us figure out which of the cluster is the best, we'll further examine this cluster solutions when k is equal to 2 and k is equal to 3 to see whether they overlap or not. So for that matter, the first thing we will do is graph the clusters in a scatter plot to see if they overlap or not. But for our case, we are considering 11 clustering variables. So if we try to do a scatter plot, we are going to need 11 dimensions for our 11 clustering variables. And that will not be possible to visualize, right? Scatter plot will work to visualize just a few dimensions, but not 11 dimensions. For that reason, what we are going to do is use a method or analysis known as canonical discriminant analysis. Okay? Canonical discriminant analysis. Okay. You can read more about it on Wikipedia, but I'll give you a brief description about canonical discriminant analysis. It's a data reduction technique which creates a smaller number of variables that are linear combinations of our 11 clustering variables in our case. Okay? And we'll create new variables which are called canonical variables, and they are ordered in terms of the proportion of the variance and the clustering variables which is accounted for by each of those canonical variables. So the first canonical variable will count for the largest proportion of the variance, and the second canonical variable will account for the next largest proportion of variance, and it goes on like that. Okay, that's basically the method. And usually the majority of the variance in the clustering variables will be accounted for by the first two canonical variables, by the first two usually. And those are the variables that we can plot. And luckily for us in Python, there is a function known as PCA, and this PCA function will allow us to do this canonical discriminant analysis. So the first thing we'll do is import this function, and then we'll create an object that we will call PCA. That's the function name also. We'll just call this is the method name or the function name, and we'll create a variable and call this function name, and then we'll ask Python, by using this method or function, we'll ask Python to return the first two canonical variables, and then we'll create some matrix and include these two variables to estimate, which will be estimated by the canonical discriminant analysis. And after that, we'll plot those two canonical variables by assigning 3 cluster, and then we'll plot another one by assigning 2 cluster for our k values. Okay, so that's what we'll do in the next few minutes. Okay, let's go ahead and write the code and do some more explanation. So first, let's import PCA from Scikit-Learn. So from sklearn .decomposition, import PCA, and we'll call the PCA method and pass 2. Usually, as I mentioned, we just need the first two canonical variables. Okay, and I'll save the method in a variable called PCA2 since we are using 2 canonical variables since we're calculating that. And as I mentioned earlier, we'll be deploying, as I mentioned before, we'll be deploying this for 3 clusters when k is equal to 3 and when k is equal to 2. So let's first see when k is equal to 3, right? Which is 3 clusters. Let's see the 3 cluster solution first. So we'll call our k-means model, we'll instantiate it, and then for number of clusters, we'll pass 3, and clusters, we'll pass 3, and we'll save our k-means model in a variable called, let's call it model1, and then we'll train our model by passing the training dataset, which is cluster train. So let's call the fit method on our k-means model for 3 number of clusters, and then simply pass cluster train. Okay, and those are the values that are used, the default values. Okay, back to our PCA method. So we have our PCA2, and then we'll call the
fit transform method and pass our cluster train dataset. So I'll explain about this method once I write down the code. Okay, and I'll save this in a variable called plot columns, and then we'll do a scatter plot by calling Matplotlib scatter method, and then we'll pass our x and y variables. So on our x-axis we'll pass or use the first canonical variable, and for our y-axis we'll pass or use the second canonical variable. So plot columns, and let's index this. This means the first canonical variable, and then for our y-axis we'll use the second canonical variable, plot columns, and then index 1. And for our C, we'll call our model's label function. So we have our k-means model 1, and then we'll simply call the labels method. Okay, and check out the Scikit-Learn documentation about this labels method. Next, let's label our x and y axis plt.x label. So for our x label, this is our canonical variable 1, and our y label will be canonical variable 2. Canonical variable 2 for our y-axis. And let's give it a title by calling the title method scatter plot for 3 clusters solution using 2 canonical variables. Okay, and we'll finally call the show method to show our figures, and let me call the figure method and pass the fig size attribute. Fig size we'll use 10 by 6. Okay, now let's discuss what we did here. So as I mentioned earlier, we can use the PCA function or method to do the canonical discriminant analysis. So the first thing we did is imported that function, and then we created an object that we called PCA2. So this PCA2 means we want to use 2 canonical variables. So this PCA2 asks Python to return the first 2 canonical variables. Then we created this matrix called plot columns, and this will include the 2 canonical variables, which is estimated by our canonical discriminant analysis. And then this PCA2 that fit asks Python to fit the canonical discriminant analysis that we specified with this PCA command or method, and the transform part of the method applies the canonical discriminant analysis to the cluster train dataset to calculate the canonical variables. Okay, that's what this line of code is doing in short. And then we call the scatter method to plot those 2 canonical variables by the cluster assignment. In this case, the value is 3 since we are doing 3 cluster solution. So this part, x is equal to plot columns, index colon, comma 0. It means plot the first canonical variable on our x-axis, and this part means plot the second canonical variable on the y-axis. And this model.labels method contains the cluster assignment variable from our 3 cluster solution. Okay, so that way when we plot and see our graph, we'll see 3 different color codes. Okay, so this tells Python to color code our points for each of the clusters. That way they will be visible. Okay, the 3 clusters will be visible. So that's what this method is. Okay, and then we have our labels, and finally plt.show. Let's run the cell, and there you go. You have your first canonical variable on the x-axis, second canonical variable on our y-axis, and here is our scatter plot for 3 cluster solution using 2 canonical variables. As you see here, we have 3 distinct clusters. One cluster is in green, another cluster in
blue, and the third cluster is in red. As you see here, there is some overlap in here between the red and blue clusters. So some general observations from our scatter plot is that these three clusters are densely packed, meaning that the observations within the clusters are highly correlated with each other, and within each cluster the variance is relatively low. But there appears to be a good deal of overlap, meaning that it's not a good separation between these two clusters, the blue and red clusters, whereas the cluster in green shows a much better separation, but it's also at the same time it's kind of spread out, and this indicates less correlation among the observations. Okay, so that's some general observation about our three cluster solution. So with that observation, we'll go and check out the two cluster solution in the next lecture. Okay, and we'll also summarize and revisit this PCA and canonical variables. Thank you, everyone. Hello, everyone, and welcome back. Let's start the lecture by summarizing what we did in the previous lecture. So here we have the elbow curve, and we see that the average distance decreases as the number of clusters increases. And we mentioned that the goal of our cluster analysis is to minimize the distance between observations and their clusters. So we want to choose the fewest number of clusters, which provides a low average distance. And we said that what we're looking for is a bend in our elbow curve, and we identified a couple of bends when k is equal to 2 and when k is equal to 3. And to determine which would be a better fit, we said that we can use a scatter plot to plot this. However, with our 11 clustering variables, we have 11 dimensions, and that will be impossible to visualize on a scatter plot, since a scatter plot works to visualize only a few dimensions, but not 11 dimensions in our case. So what we did was use a method known as canonical discriminant analysis, and this is a data reduction technique which creates a smaller number of variables which are linear combinations of our 11 clustering variables. And those new variables are called canonical variables, and as I mentioned, they are ordered in terms of the proportion of their variance and the clustering variables, which is accounted for by each of the canonical variables. So again, those canonical variables are ordered in terms of the proportion of the variance. So the first canonical variable accounts for the largest proportion of the variance, and the second canonical variable will account for the next largest proportion of the variance, and the third canonical variable will account for the third largest proportion of the variance, and it goes on like that. But in most cases, we see that the majority of the variance in the clustering variables will be accounted for by the first two canonical variables, and so we use those two canonical variables for our plot. And we mentioned that Python has a method or function known as the PCA function, which will help us do the canonical discriminant analysis. And we did that by first importing PCA, and this PCA2 asks Python to return the first two canonical variables. Then we created a matrix known as plot columns, and this plot columns matrix includes the first two canonical variables, which we estimated by the canonical discriminant analysis. And then we call this fit transform method. So the fit asks Python to fit our canonical discriminant analysis, which we specified in here in our PCA2 command, and the transform part of the method applies the canonical discriminant analysis to our cluster trained dataset, and that will help us calculate the canonical variables. Okay, and then we assigned x and y axis as canonical variable 1 and canonical variable 2, and here we see a solution or scatter plot for our 3 cluster solution. And what we observe from our 3 cluster solution is that the 3 clusters are densely packed, as you see here. And this means that the observations within the clusters are highly correlated with each other. And within each cluster, the variance is very low or relatively low. And here there appears to be some kind of overlap between our blue and red clusters, meaning that there isn't good separation between these 2 clusters. And here, if you look at the green clusters, they seem to be more spread out. And this indicates that there is less correlation among the observations in our green clusters. This, on the other hand, means there is a higher cluster variance within the green clusters. So those are some ups and downs for our 3 cluster solution. Okay, next we'll see, let's explore 2 cluster solution. 2 cluster solution. Okay, remember from our elbow curve, there seems to be a bend when k is equal to 3 and k is equal to 2. So now we are considering the 2 cluster solution. Okay, let's first instantiate our k-means model and pass 2 for our number of clusters. We'll set this to be equal to 2, and we'll save our model in a variable called model2. Okay, next we'll call the fit method on our model and pass our training dataset. So we'll train our k-means clustering model with the training dataset, which is cluster train. Okay, and those are some of the attributes. Okay, next we'll use the PCA method as we did in the previous lecture for our 3 cluster solution. So we have our PCA2. Again, we're only interested in 2 canonical variables. So we'll save this in a variable called PCA2. Then we can create our plot columns matrix, and that will be equal to PCA2. We'll call the fit transform method and then pass our cluster train dataset. Next, let's call the scatter method and pass x and y variables as our canonical variable 1 and canonical variable 2. For that matter, let me copy it from our previous lecture to save time. So I'll copy this part from our scatter plot and paste it here. So we have our plt.scatter. On our x-axis, we'll have canonical variable 1. That's what this means. On our y-axis, we'll have our second canonical variable. And we'll pass a c value model2.labels. And this tells Python to color code the number of clusters. In this case, we are looking for 2 clusters. So we'll see 2 color codes, 2 different colors for each of our clusters. We have our x label, canonical variable 1. For our y label, canonical variable 2. And for title, we'll call it scatter plot for 2 clusters solution using 2 canonical variables. And finally, we'll call the show method. Now let's run it. Okay, I just passed the figure method and then used a fixed size of 10 by 6 to make it a bit bigger. Okay, so here you see 2 cluster solution, canonical variable 1 on the x-axis, canonical variable 2 on the y-axis, and we have 2 distinct clusters here, one in red, one in blue. Okay, again, what we see from the scatter plot is that the 2 clusters are densely packed, and that means the observations within each clusters are highly correlated to each other and within each other also. And within each cluster, the variance is relatively low. And there appears to be some overlap around here, right? The separation is hard when it's around the borderline. And here, if you consider the red cluster, it seems to be more spread out. And this indicates less correlation among the observations within the red clusters. That also suggests a higher variance within these red clusters.
But compared to the 3-cluster solution, this seems to be a better cluster solution, right? Because in the 3-cluster, you see way more overlap of these two clusters, the one in red and the one in blue. But from what we see here, a 2-cluster solution might be better for our problem. Again, we see that these 2 clusters are very densely packed, and this tells us that each observation within the clusters are very highly correlated, and that the cluster variance is relatively low. Okay, last thing I want to show you is if you go to your elbow curve, here you might see like this might look like a little bit of a bend, right? But it's not as much compared to 2-cluster and 3-cluster solutions. But let me quickly show you a model and show you the 6-cluster solution, and we'll compare it to these two results. Okay, so I just copied the methods and models that we have from our previous models, and let me rename this to model 3. So k-means, we'll start by building our k-means model, and for number of clusters we'll use 6. Okay, so we're doing the same thing that we did before. The only thing is we're considering 6-cluster solutions. Let's run this, and here plt.figure scatter, so we'll change this to model 3.label so that we will have 6 different color codes representing each of our clusters. Okay, and scatter plot for 6-cluster solution using 2 canonical variables. Everything else stays the same. Let's run it and see. So here there is a lot of overlap between our clusters, so a 6-cluster solution is not a good choice. So I just wanted to quickly show you this 6-cluster solution. And again, if I go back to our elbow curve, the 2 bends are very clear when k value is 2 and 3, right? And in elbow curves, what we look for is a bend in the elbow, and that kind of shows where the average distance value might be leveling off. And adding more clusters does not decrease the average distance as much. Okay, it's kind of subjective, but adding more clusters won't have much effect on the average distance. Even if the average distance is decreasing, at some point the average distance value will be leveling off, and then adding more clusters after that point, it won't make any difference. Okay, it doesn't decrease the average distance much. That's what you see here. You saw the scatter plot for 6-cluster solution, but it wasn't that great, right? That's the reason why. So we went through a few topics in this lecture. I will advise you to go over it and practice these methods. And if you are interested about the canonical discriminant analysis, you can check out Wikipedia to learn more about it. But we went over the main methods of canonical discriminant analysis. Okay, and here we saw that the 2-cluster solution is a better fit for our problem. So back to our data set. Now once we group our population, our data set, our students, into 2 separate clusters, the next thing we can do is evaluate each of these clusters and then find out what kind of characters they have, the common characters that each of these clusters have, and then we can intervene based on those characters. So this is one big use of k-means clustering. Once we identify our clusters based on similar characteristics, we can then study those characters, those features, and then intervene and provide some solution for those characters. So that's what I have for the lecture on k-means clustering. And as an assignment for you, you can change this canonical variables to 3 and see if you get a different result. So you can compare the result that you get with 2 canonical variables. Okay, but usually 2 is enough. The first 2 canonical variables are enough, as we discussed. Okay, so go through the lectures and try out the examples by yourself, and also check out the Scikit-Learn documentation on k-means clustering. You can read more about it there. So for instance here, this is one of the methods that we looked at, fit_transform, and you can read more about it here. Okay, great. Oh, and one last thing you can do is change the number of clusters. So if I go here, you can change the number of clusters to different values and see what kind of clusters that you get. In our exercise, we looked at 2 clusters, 3 clusters, and 6 clusters solution. You can change it to 5, 4, 7, 8, and see what kind of clusters that you get and whether it will be a good fit or not by comparing it to the 2 and 3 cluster solution. Okay, those are some analysis that you can do. Great, thanks again everyone. Hello everyone, and welcome to the lecture on decision trees and random forests. We'll first look at decision trees briefly, and then we'll look at random forests. Decision trees are a form of supervised learning, and as in supervised learning, a set of explanatory variables, also known as inputs or features or predictors, are used to predict the value of a response variable called target variables or the outcome variables. The name decision trees is because the predictive model can be represented in a tree-like structure that you see on the right. When the response variable is categorical, the model is called a classification tree, and decision trees are read from the top down, starting at the root node. Each internal node represents a split on the values of the explanatory variables. In a decision tree, each internal node represents a test on an attribute. Example, whether a heads or a tails in flipping a coin, whether petal length is less than 3 cm, or whether sepal length is less than 4 cm. And each branch represents the outcome of the test, and each leaf node represents a class label. Decision is then taken once all the attributes are computed. Decision trees work by making binary splits in a given sample to maximize correct classification of those with and without the target of interest. And all possible separations or cut points are tested, and the separation yielding the minimum error is selected. There are certain advantages and disadvantages of using decision trees, and check out the link below to find out and read more about the advantages and disadvantages of decision trees. Here I am at the Scikit-Learn documentation on decision trees. So if you scroll down, you'll see some advantages and disadvantages of decision trees. One advantage of decision tree is it's simple to understand and interpret because the trees can be visualized, and it requires little data preparation. The cost of the tree is logarithmic in the number of data points, and we are able to handle multi-output problems. And some disadvantages of decision trees are decision tree learners can create over-complex trees that do not generalize the data well, and decision tree learners create biased trees if some classes dominate. So it's good that we have to balance the dataset prior to fitting if we are using decision trees. Now let's go back to the presentation and look at random forests. Random forests algorithm is based on decision trees, but proceeds by growing many trees. It's the same as decision trees, and random forest allows us to make binary splits in our dataset that creates subgroups. By applying a series of criteria over and over again, we choose variables that best predict our target variable. And random forest consists of a collection or ensemble of simple tree predictors, and each predictor is capable of producing a response when presented with a set of predictor values. For classification problems, this response takes the form of a class membership, which classifies a set of
independent predictor values with one of the categories present in the dependent variable. And random forests search for a split on only one variable in a node. Then the variable that has the largest association with the target among all the candidate explanatory variables, but only among those explanatory variables that have been randomly selected to be tested for that node. In random forests, a small subset of explanatory variables is selected at random. Then the node is split with the best variable among the small number of randomly selected variables. So these random forests are similar to decision trees, and when we look at the live coding example, we'll build models using random forest classifiers and decision tree classifiers and compare those two models. For more explanation on random forests, check out the Scikit-Learn documentation, and I also have a wiki link here. Let's go to those links and quickly see it. So here is the Scikit-Learn documentation for the random forest classifier model. You can check out the documentation here. We'll see a live coding example in the next lecture. And let's go to the wiki link for random forests. As we mentioned, random forests are an ensemble learning method for classification, and they operate by constructing a multitude of decision trees at training time and outputting the class that is the mode of the classes. So you can read more about the algorithm of random forests here. Great, now let's jump into Jupyter Notebook and see some live coding examples of decision trees and random forests. Thank you everyone. Hello everyone and welcome. In this lecture we'll look at decision trees and random forests. Let me give you an overview of what we will do. We'll start by looking at a dataset from a lending club, and what this dataset contains is a couple of columns that has information about credit history, interest rate, installment, accounts, and so on. So what we'll do is we'll use those information to decide whether a person will get a good loan or a bad loan. Once we look at the dataset, we'll use a decision tree classifier model to build our model and check out if our decision tree does well or not. And after that, we'll consider random forests. Okay, let's start by looking at the dataset. As usual, we import numpy as np, pandas as pd. I copied this from the previous lecture. Okay, now let's use pandas read CSV method to check out our dataset, and I'll save it in a variable called loans pd.read CSV. Then this is the name of the file, lending club data01.csv. Paste it here and run it. Let's check out what it looks like by calling the head method, loans.head. Okay, so these are the columns that we have: interest rate, installment, open account, revolving balance, total account, bad loans, and grade number. What we'll do is we'll try to come up if a person will get a good loan or a bad loan. So whether the loan is good or bad will be our target, and we'll use all these columns except our target column as our features. Let's check out let's get some information about our dataset. I'm going to call the info method. So we have about 1468 rows and 8 columns. The size of the file is about 92 kilobytes. And you can check out the last 5 rows of your dataset by calling the tail method. Okay, that's what it looks like. What we'll do next is let's add a new column, and we'll call that column good loans, and we'll use this bad loans column and map it to our good loans, so we can set our good loans values 0 and 1 to yes and no. So we'll apply the lambda function, and we can set 0 to yes and 1 to no. Let's go ahead and do that. So the name of our new column will be good loans, and we'll use the bad loans column
to create our good loans column, and we'll apply the lambda function. So what I will do is call the apply method and then pass the lambda function. So let's say lambda y, we can say yes if y is equal to 0, else no. We can do that. Okay, now let's look at our loans dataset. So if we call the head method, we have a new column here, bad good loans, and the results are based on what we have for bad loans, 0 and 1. We set 0 to yes, 1 to no. What we'll do next is define our features and targets. So for our features, we'll use all the columns except the bad loans and good loans columns. And for our target, we'll use the good loans column. So let's do that. We'll save our features in a variable x, and then let's use the drop method and then drop the columns that we don't need, which are bad loans and good loans columns. So we can call the drop method and then pass the column names. We'll pass them as a list. So bad loans and good loans. And we're dropping the column, so we'll pass an axis value of 1. That means to drop the columns. And for our y, which is target, we'll use the good loans column, good underscore loans. Now let's check out the shape of our features and target, x and y. So print x.shape, y.shape. So our x's, or our feature, 1468 rows by 7 columns, whereas our y, our target, is 1468. Okay, 2-dimensional and 1-dimensional. Now that we have our features and target, what we'll do next is use the train test split method to split our dataset into training and then testing datasets. Once we have that, we'll build our decision tree classifier model, and then we'll use that model and use the training datasets xtrain and ytrain to train our model, and we'll call the predict method to make predictions using the testing dataset. Let's do that. So we'll start by importing the train test split method from Scikit-Learn. So from sklearn dot cross validation, let's import train test split. And let's also import our decision tree classifier library. That's also from Scikit-Learn. From sklearn .3, it's in 3, import decision tree classifier. Decision tree classifier. You don't have to memorize where all these libraries exist. You can simply Google them. Okay, so from sklearn .3, import decision tree classifier. Now let's split our dataset into training and testing datasets, and we'll save them in 4 variables: xtrain, xtest, ytrain, and ytest. Xtrain, xtest, ytrain, and ytest. So we'll set that to be equal to train test split, and we'll pass our features and target, x and y, and let's pass the test size attribute and set it to 30%. Again, this is optional. If you don't pass that, the default value will be used. And let's also pass the random set attribute and then set it to, let's say, 124. If you want to get the same result as me, you can use the same random state, 124. So we'll use 70% of our dataset for training and 30% of our dataset for testing. Now let's check out the shape of our training and testing datasets. Let's print xtrain.shape, xtest.shape.
So our training dataset is 1027 by 7. So 1027 is 70% of 1468, what we had earlier. Okay, and if we print the shape of our Y train and Y test, you will see that your training dataset is 70%, whereas our testing dataset is 30%. Now we can build our model. We'll start by instantiating our decision tree classifier model. So decision tree classifier. Let's save this in a variable called model. Once we instantiate our model, the next thing we'll do is call the fit method on our model so that we can train our model using the training datasets xtrain and ytrain. So let's pass xtrain and ytrain. Okay, so these are the default values used for our decision tree classifier model. If you are interested about them, you can check out the documentation on Scikit-Learn. Now that we have trained our model, let's call the predict method and then pass our testing dataset xtest model.predict and then pass our xtest. And we'll save this in a variable called prediction, and we'll set that to be equal to model.predict. Okay, what we can do next is evaluate our model, and we can use confusion matrix and classification report for evaluation. Okay, once we import them from Scikit-Learn's metrics, we'll use them for evaluation, and that's what we'll see in the next lecture. Thank you, everyone. Hello, everyone, and welcome back. In this lecture, we'll continue our discussion on decision trees and random forests. So now that we have built our model, it's time for evaluation, and we'll use confusion matrix and classification report for evaluation. So let's start by importing them from Scikit-Learn's metrics. So from sklearn.metrics, let's import classification report and confusion matrix. Okay, now we can simply say print. We can simply print the confusion matrix and classification report. So confusion matrix, and then we'll pass our Y test and our prediction. So our prediction is our model.predict, and then we pass X test. Let's run it. So this is our confusion matrix. We have 50 and 59, almost a total of 109 misclassified datasets. So those are the false negatives and false positives, 50 and 59. And let's print out the classification report and check out our result. Print classification report, and then we'll pass our Y test and our prediction. Run it. So overall we have a precision of 77%, recall of 75%, and F1 score of 76%. And if you look at the specific results for yes and no, you see that we have a better result for good loans yes. So our model has a better prediction when our good loan is yes. That's why you see a higher precision, recall, and F1 score for the value yes. As you can see here, 86%, 84%, and 85%. Whereas when good loans is equal to no, those values are very low, 22, 25, and 24%. Overall, this is the result of our model, almost 75-76% accuracy. And from the confusion matrix, we saw that these are the the false positives and false negatives. So 109 are misclassified as either false positive or false negative. What we'll do next is check out random forests. We'll import random forest classifier model from Scikit-Learn, and we'll build a random forest classifier model,
and used our training datasets to train our random forest classifier model, and we'll make predictions off of that and see how our model does by printing out the classification report and confusion matrix for our random forest classifier model. And once we do that, we'll compare it with the decision tree classification. Let's start by importing random forest classifier, and it's in Scikit-Learn's ensemble. Remember, decision trees are in Scikit-Trees 3, whereas random forest classifier is in Scikit-Learn's ensemble. So from sklearn dot ensemble import random forest classifier. Once we import it, let's instantiate our random forest classifier model, and we'll save it in a variable called random forest underscore model. You can save it anywhere you like. So random forest classifier, and our random forest classifier method takes an attribute known as n estimators, number of estimators, and I'll pass 150. Okay, as an exercise for you, you can try out different numbers and see the results of your random forest classifier model. Okay, for now I'll pass number of estimators to 150. Okay, and once we instantiate our model, we'll call the fit method to train our model with our training datasets. We have seen that before, so let's do that. We have our random forest model, and we'll call the fit method, and then we'll train them by using our training datasets xtrain and ytrain. And these are the default values: class, weight, none, criterion. These are all the various default values, except for, of course, number of estimators. We specified that to be 150. You can check out Scikit-Learn's documentation on random forest classifiers to find out more about any of these attributes or parameters. Now that we have trained our model, let's predict using the testing dataset. Okay, so we have our random forest model. We'll call the predict method on it, and then pass our training dataset x test, and let's save this in a variable called random forest prediction. Next, let's evaluate our model by using the confusion matrix and classification reports. We have already imported them from metrics, right, in the previous lecture, so we don't need to import it again. So let's print out the classification report. So print classification report, and we'll pass our y-test and random forest prediction that we just calculated. Let's run this. So this is the classification report. We'll talk about it later on. Let me print the confusion matrix and start our discussion from that. We'll pass our y-test and random forest prediction. Oh, there should be confusion matrix, not confusion report. Okay, so for our confusion matrix, 62 plus 12, that's 74. 74 of them are misclassified as false positive and false negative. Using the decision tree model, we saw that 109 of them were misclassified, whereas using the random forest model, only 74 of them are misclassified as false positives or false negatives. And if we check out the classification report for our random forest model, we see that it has an average precision of 77%, recall of 83%, F1 score of 79%. Overall, we have a bit better result compared to our decision tree model, right? Our decision tree model had 77, 75, 76%. So our random forest did better on recall and F1 score compared to the decision tree classifier. And if you look at each individual result, for good lone yes, we had a precision of 85%. For recall, we had 97% recall, and 91% F1 score. And our model didn't do very well when the value is no. When good loans is no, the precision is 29%. The recall and F1 scores are really low, 7% and 12%. But overall, our random forest model did better than our decision tree classifier model, right? And sometimes our models depend on what we specifically need, whether it's the recall value or F1 score or precision. So depending on what we choose, we can get or use different models, be it random forest classifier or decision tree classifier models. But usually random forest classifier model does better compared to decision tree classifier models. And that's true especially if we are dealing with a larger dataset. For this example, we use a dataset consisting of 1468 rows, about 1500 rows. But the larger our dataset, the better the random forest classifier model does compared to decision tree classifier models. That's another important thing to note. And from the classification report and confusion matrix result, we saw that our random forest classifier model did a bit better than our decision tree model. For confusion matrix, 74 of them were misclassified as false positives or false negatives, whereas 109 of them were misclassified with our decision tree model, right? So those are some things to consider. What we'll do in the next lecture is consider a larger dataset and build a decision tree classifier and random forest models for that bigger dataset and see and evaluate the models. Thank you everyone, and welcome back. In this lecture, we'll continue our discussion on decision trees and random forests. We'll consider a larger dataset to build our models and evaluate them. Here we have another dataset called Lending Club New Data. We'll start by importing it and then looking at the dataset. For that, we'll use Pandas read CSV method, and I'll pass the file name, and let's save it in a variable called loans. Let's check out what it looks like by calling the head method. So here we see the first 5 rows, and our dataset has 24 columns. Previously, we saw that our dataset has 7 columns, but this one has 24 columns. So we have additional columns. And this is the same dataset regarding whether the person will get a good loan or a bad loan, but we have some more features. For instance, employment length, subgrade number, payment increase ratio, and so on. So we'll use all the new columns as our features, and we'll try to determine whether a person will get a good loan or a bad loan depending on these features. Okay, the only difference is here we have a bigger data set, we have more rows, more data points, and more features to consider. So for that, if we call the tail method loans.tail, we have about 9,500 rows. The previous one had only less than 1,500 rows. And let's call the info method. Okay, we see that we have 9,116 rows and 24 columns. And here you have name of your columns, and the size of the file is about 1.7 megabytes, much larger than our previous dataset. Okay, so these are some informations that you can get from your dataset. We'll do the same thing that we did for our previous dataset. We'll start by adding a new column known as good columns, and we'll map it with the bad columns values 1 and 0. We'll set 0 as yes and then 1 as no for our new column good loans, and we'll use our good loans as our target, whereas we'll use all these remaining columns as our feature. So let's add our new column known as good loans, good underscore loans, and we'll set that to be equal to we'll take our bad loans and apply the lambda function. Okay, so bad loans, and you can call the columns method if you want to see a list of all the columns, and then simply copy those column names and paste them here, and if you don't want to type them, of course. So we have our bad loans, and we'll call the apply method, and we'll use the lambda function. We can say lambda y yes if x is equal to 0, or else we'll set it to no. Oh, sorry, this should be y. We used y. Okay, so lambda y, set it to yes if the value of y is 0, or else set it to no. Okay, now that we have added our new column, good loans, we can check it out by calling the head method on our loans data frame. And here we see that a new column is added. Whenever the value of bad loans is 0, the good loans value is yes, and whenever it's 1, the value is no. Next, let's define our features and target. As I mentioned, for our features, we'll use all the column except for the good loans and bad loans columns. So let's drop those two columns by calling the drop method on our dataset, and simply pass the two columns as a list. So bad loans and good loans, good underscore loans, and we're dropping the axis, we're dropping the column, so we'll pass the axis attribute and set it to 1. For our target, we'll use our good loans column. Next, we can check out the shape of our x and y features and target. So let's print x dot shape and y dot shape, and we see that our features is 2-dimensional, 9500 by 23 rows, whereas our target is 9516, 1-dimensional. Okay, now that we have defined our feature and target, we can use the train test split method to split our dataset into training and then testing datasets. After that, we can instantiate our decision tree classifier model and train that model with our training datasets, and later we'll use the testing datasets to make predictions. That's what we'll do next. Okay, let's start by splitting our dataset, and we'll save them in the variables xtrain, xtest, ytrain, and ytest. We have done this before. Xtrain, xtest, ytrain, and then ytest. We'll set it to be equal to train test split, and then we'll pass our x and y datasets. And for test size, we'll pass, let's use 30%. If you don't pass that, the default value will be used, and we'll pass a random state of 124. So I have already imported the train test split method in one of the previous lectures, but if you haven't done so, import the train test split from Scikit-Learn's cross validation. And if you want to get the same result as me, you can use a random state of 124. Otherwise, you can use a different random state. So now that we have split our dataset into training and testing datasets, we can print out their shapes. Let's print out xtrain.shape and xtest.shape. So our xtrain is 6600 by 23. So this 6661 is 70% of our dataset, since we are using 70% of our dataset for training and only 30% for testing. That's why our xtest is 2855, which is 30% of 9516. Similarly, if we print out the shape of ytrain and ytest, we'll get the same result, except they both will be 1-dimensional, but the split will be 70% and 30% of our dataset. Okay, now that we have split our dataset, it's time to instantiate our decision tree classifier model. Decision tree classifier. That's our model, and we'll save this in a variable called, I'll save it in a variable called model2. And now that we have instantiated our decision tree classifier model, we can call the fit method to train our model by passing our xtrain and ytrain datasets. And these are the default values that our model uses. Again, you can check it out on the documentation. Next, let's predict by using our testing datasets. So we'll call model2.predict and then pass our xtest dataset, and we'll save our result in a variable called prediction2. Next, we can print out or evaluate our model by calling the confusion matrix and classification report. Let's do that. Let's start by printing the confusion matrix. We'll pass our y-test dataset and then our prediction2 that we just calculated. So let's run this. Okay, here we see that only 12 plus 9, about 21 of our dataset is misclassified. Those are the false positives and false negatives. Only 21, right? Even if we have a larger dataset, only a few of them are misclassified. And if we print out the classification report, let's pass y-test and prediction2 and run it. We have a much better classification report accuracy, an average of 99%. And if you look at it for each of the good loans values, when it's yes, we have 100% accuracy, whereas when it's no, we have 98% precision, 97% for recall, and 98% for F1 score. So our model did very well, and we can tell that from the confusion matrix and classification report result. And if you ask why our model did better this time, one reason is we have a larger data set, and we trained on, our model was able to train on more data sets, right? So here if you see, we were able to train on more than 6,000 data sets, whereas our previous model only learned on about 900 data sets. And since we considered more columns, more features, we were able to get a better precision, recall, and F1 score. That's because, this good loan or bad loans is influenced by just more than a few columns or a few features. So all these features play a crucial role in determining whether a person gets a good loan or a bad loan. Okay. In our first model, we only considered 7 of these features, whereas in this model, we considered 23 features or columns. Okay, so that's another reason why the second model did better than the first model. Great. What we'll do in the next lecture is build a random forest classifier model and check out the result. You can guess that the random forest classifier model will most likely do very well, and you won't be able to see the difference between those two, since this one already has a 99% accuracy, and as a model, even if we get 100% accuracy, average accuracy, both models did pretty well, and it will be very hard to distinguish the differences, right? So we'll see that in the next lecture. Thank you, everyone. Hello, everyone, and welcome back. In this lecture, we'll continue our discussion on decision trees and random forests. Let's start by quickly building a random forest classifier model and do some evaluation on our previous data set. Okay, let's start by instantiating our model. Random forest classifier, and we'll pass the number of estimators attribute n underscore estimators, and we'll set it to be 150. So let's save this in a variable called random forest underscore model 2. Now that we have instantiated our model, let's call the fit method and train our model with the training datasets xtrain and ytrain. So ref model2 dot fit, and then we'll pass our xtrain and ytrain datasets. Let's run this. So here are the default values used for the various parameters, and you can check out what these are on the documentation. Now that we have trained our model, let's make predictions by using the testing dataset xtest, and we'll save the result in a variable called prediction. Let me call it rf prediction for random forest prediction, and that will be equal to our random forest model 2, and we'll call the predict method on it and pass our xtest dataset. Now we can make some evaluations by calling the confusion matrix and classification reports. So let's print them out. Let's start by printing the confusion matrix. We'll pass our y-test and random forest prediction that we just calculated. Run this, and next let's print out the classification report, and we'll pass again our y-test and random forest prediction. Okay, so let's start by looking at the classification report. We see that we have an average accuracy of 100% for precision, 100% for recall, and 100% for F1 score. And using our random forest classifier model, we had a 99% accuracy. And if you check out each of the individual rows here, when good loans is equal to yes, the precision is 99%, whereas the recall and F1 score are 100%. And when our good loan value is equal to no, we had 100% precision and 97% for recall and 99% for F1 score. Our previous model had about 97 and 98%, right? So let me print out the classification report of our previous decision tree classifier model. Print classification report. So if we pass our y-test and prediction 2, so that's the classification report of our decision tree classifier model, right? There isn't much difference because 99% average accuracy and 100%, they are very close, right? Even if you take individual rows for good loan yes and good loans no, you don't see much difference because you have already achieved a very high accuracy. And here, if you look at the confusion matrix, we only had 13 misclassified data points, right? Whereas our previous model had, I believe, 21. If we print out the confusion matrix, let me add another cell here and print out confusion matrix and pass y-test prediction 2. So if we compare those two, we had 12 plus 9, about 21 misclassified data points, whereas the random forest classifier model only had 13 misclassified data points. Okay, So 13 versus 21. Still, our model did better. Our random forest classifier model did better than the decision tree classifier model. You might not see a much significant difference, but usually random forest classifier models do better than decision tree classifier models. And that's especially true when you have a larger data set. For our last example, what we'll do is drop some of the features from our loans dataset. So let me call the head method on our loans dataset. So we used about 23 of these columns as our features, and we used the good loans column as our target. What we'll do for this last example is drop some of these features. We'll drop a few of these features, maybe 10 or 12 of these features, and we'll only consider the remaining features, the remaining columns as our features, and as usual we'll use the good loans column as our target, and we'll build a decision tree classifier model based on those specific features. And next we'll build a random forest classifier model using those features, and we'll compare them and see. So let's drop the following columns. We'll drop the bad loans and good loans columns as usual, and in addition we'll also drop these columns. I just copied this to save us some time. So annual increase, DTI, all these columns, I just grabbed them from our loans dataset. So we'll drop all these columns, and we'll pass axis is equal to 1 to show that we are dropping the columns, and we'll use the remaining columns as our feature. Okay, and for our target we'll use the good loans column as our target. So we'll save it in a variable y, loans, then good underscore loans. Next, let's check out the shape of our x and y, our features and target x and y. Print x.shape and y.shape. Run it. So for our x, for our features, we'll use 11 columns or 11 features. We have dropped about 12 of the previous features we have used. In the previous lecture, we used 23 features. Now we'll only consider 11 features. Okay, so the shape of our features dataset is 9516 rows by 11 columns. So number of rows stays the same, only number of columns changes since we have dropped all these columns. And y.shape is 9516. Next, we'll use the train test split method to split our dataset into training and testing datasets, and we'll save them in variables xtrain, xtest, ytrain, and ytest. Xtrain, xtest, ytrain, and ytest. That will be equal to train test split, and we'll pass our features and target x and y datasets. And for test size, we'll use 30%. Again, you can leave it if you want to use the default value for the test size, and we'll pass a random state of 124. If you want to get the same result as me, you can use the same random state, or else you can use any other random state. Now let's check out the shape of our xtrain dataset, xtest dataset, and ytrain and ytest datasets. Xtrain.shape, xtest.shape. So we are using 70% of our dataset for training and 30% for testing. That's what you see here. Xtrain is 6661, which is 70% of 9560. and our testing dataset X test is 30% of 9560. Similarly, if you print out the shape of Y train and Y test, you will see the same 70-30 division. 70% for training and 30% for testing. Next, let's instantiate our decision tree classifier model, and we'll save it in a variable called model3 since it's our third decision tree classifier model. So we'll call the decision tree classifier. Once we instantiate our model, we'll train our model by using the training datasets X-train and Y-train. So model3 dot fit, and we'll pass X-train and Y-train. And those are the default values for our decision tree classifier model. Next, we can predict by using the X-test dataset, and we'll save our prediction in a variable called prediction3. We do that by calling the predict method on our model, on our decision tree classifier model. So let's pass X-test. Now we are ready for evaluation. We'll call the confusion matrix and classification reports to evaluate our model. So let's print out the confusion matrix, and we'll pass Y-test and prediction3. Let's run this. So this is the confusion matrix. About 145 plus 167 data points are misclassified as false positive or false negatives. Right? That's a big number compared to the previous results. Next, let's print out the classification report. We'll pass Y-test and prediction3. And here is our classification report. We have an average precision of 89%, and for recall and F1 scores, we have 89% also. And if you check the individual rows, when good loans is equal to yes, we have about 93-94% precision, recall, and F1 scores. So our model does good when good loans is yes, but it doesn't do as good when the value is no. Here you see a precision score, a precision of 65%, recall of 68%, and F1 score of 67%. Okay, and from the confusion matrix, we saw how many of them were misclassified as false positives or false negatives, which is 167 plus 145. Next, let's build out a random forest classifier model and compare our results to our decision tree classifier model. Let's start by instantiating the random forest classifier model, random forest classifier, and we'll pass the n estimators attribute and set it to 150. I'll save our model in a variable called random forest underscore model3. Now let's call the fit method on our model to train our model by using the X-train and Y-train datasets, X-train and Y-train. Now that we have trained our model, let's call the predict method and pass the X-test dataset to make predictions. And we'll save our variables in our result in a variable called random forest prediction3, and that will be equal to random forest underscore our model3 dot predict, and then pass our X-test dataset. Let's run this. Now let's do some evaluation by calling by printing out the confusion matrix and classification report. So print, let's start by printing the confusion matrix. We'll pass y-test and then random forest prediction 3 that we just calculated. Run it, and let me print out the classification report, and we'll discuss after that. Let's pass y-test and random forest prediction 3. Run it also. So let's check out the classification report. We have an overall average precision of 91%, recall and F1 score are also 91%. Our previous decision tree classifier model had an average accuracy of 89% throughout, right? And if you consider the individual rows, we have a 93%, 97%, and 95% accuracy for precision, recall, and F1 scores. And when good loans is equal to no, we have about 79%, 60, and 68%. So it depends on what we are actually looking at, whether it's precision score or recall or F1 score. Okay, and if we check out the confusion matrix, about 182 plus 73 of them are misclassified as either false positives or false negatives. The value was a bit higher with our decision tree classifier model, which was 167 plus 145, that's what, 112, I believe. Whereas with our random forest classifier, it's less than 260, right? You see the difference. So we see here that random forest usually does better than our decision tree classifier models. And the larger your data set, it becomes more and more visible. So that's what I have for decision trees and random forest. Thank you everyone, and see you at the next lecture. Hello everyone, and welcome to the lecture on text analysis. In this lecture, we'll see how to represent text in numerical formats. We'll see how to vectorize our dataset and convert it into a documenter matrix. And finally, we'll look at model building and evaluation. As usual, we start by importing the libraries that we need. Import NumPy as NP, Pandas as PD. I copied this from one of our previous lectures. Before we get into text analysis, I want to review by looking at the iris dataset. So let's start by importing our iris dataset from Scikit-Learn. So from Scikit-Learn, we'll import iris. From Scikit-Learn, import datasets. And then we'll import iris by using the load iris method. And I'll save it in a variable called iris. Iris is equal to datasets.load iris. And we know that our iris plant has 4 features: sepal length, sepal width, petal length, and petal width. So we can call the data method on our iris dataset. And let me save this in a variable called x. And we know that we can call the target method on our iris dataset also. So target will be one of those 4, one of the 3 iris species, right? Setosa, versicolor, or I forgot the third name, but those are our targets. So if we check the shape of this x and y, we'll see that x is a 2-dimensional array. Let me show you. Print x.shape. So it's 150 by 4, right? 150 rows. And then by 4 columns, which are the features: sepal length, sepal width, petal length, and petal width. Whereas if we print the shape of y, we see that it's a 1-dimensional array, 150, right? Those will be
one of the 3 Irish species. Okay, next let's create a data frame to represent our Irish dataset. Okay, and I'll save our data frame in a variable called iris. So pd.data frame, and then we'll create our data frame from our x, which is 2-dimensional array 150 by 4, and then for our columns name we'll simply pass the names of our 4 features: sepal length, sepal width, petal length, and petal width. For that we can use the method known as feature names. Now if we check out our iris dataset and call the head method, we have sepal length, sepal width, petal length, and petal width. And again, each row represents a single Irish species. And as I mentioned, y is 1-dimensional. It represents either one of the 3 species. So if I simply print y, I'll get an array consisting of 0, 1, or 2. So 0 represents 1 Irish species, 1 represents the 2nd Irish species, and 2 represents the 3rd Irish species. And based on this, we can build a model to predict which Irish species a given observation is. And we know that in order to build a model, all of our features must be in number format, right? So our model algorithms work on numbers. So it's important to have our features in a numerical format. And we can build a model by using this iris dataset. So we have our x and y, right? We can define a model and then fit our model with x and y and try to predict an Irish species from there. Okay, I will not do that in this lecture, but I just wanted to give you a brief overview. Great. Now let's go into text analysis. Let's consider the following text. I'll create a list of texts and save it in a variable called train text. And let's say we have the following text: go home tonight, go take a cab, soccer, go play soccer. Okay, let's try to analyze these 3 texts. We have go home tonight, go take a cab, and soccer, go play soccer. The first thing we need to do is convert this text into a number format, into a numerical format. That way our algorithms can work with those. Okay, so that's one challenge. The other challenge is our texts are of different lengths, right? If you consider this is of length 3, the second one is of length 4, and the third one is of length 4. And I'm ignoring the punctuations. So for our algorithms to work, all of our documents have to be of the same length or fixed length, right? First it has to be in number format and they have to be of the same length. Okay, that's what we'll do next. Transform this text document into a numerical format and then find out ways to make it of the same size. Okay, and for that we'll be using what's known as a count vectorizer. Okay, the purpose of a count vectorizer is to convert our text document into a matrix of token words. So if you go to the Scikit documentation here, count vectorizer, what it does is it converts a collection of text documents into a matrix of token counts. Token means words. Okay, you can read more about count vectorizer here. Okay, back to our notebook. Let's use count vectorizer to convert this words into a matrix of word counts. The first thing we need to do is import count vectorizer from Scikit-Learn. Let's do that. So from sklearn .feature extraction .text, let's import count vectorizer. And then let's instantiate our count vectorizer. And I'll save it in a variable called vector. Vector is equal to count vectorizer. Okay, so this count vectorizer
it's not any kind of model. We only use count vectorizer. Its purpose is to convert our text into a number format. Now that we have instantiated count vectorizer, the next thing we can do is fit our count vectorizer object and then pass our trained text. So for that we can say vector.fit and then pass our trained text document. So this fit method is used to learn the vocabulary of our trained text document. Okay, now it has learned the vocabulary of our document, right? And then let's see what it has learned. Okay, and there's a method known as get feature names. Let's call that method on our vector object. So vector dot get feature names, and then run it. So this method returns a list of strings. So here we have cab, go, home, play, soccer, take, and tonight. Right? What do you notice from this list of words? So compare this list of strings to what we entered here and tell me the difference. So let me type our train text object here. So there are a few differences. One is here in our vector object, all of our strings are in alphabetical order, right? Cab and then go, home, play, soccer, take, tonight. So that's one difference. Another difference is there is no duplicate, only one word, right? Whereas in our original text document, we have duplicates. And the third difference is we don't see any punctuation keys in our vector object, right? So here exclamation and all these dots are dropped in our vector object. Okay, great. In the next lecture, we'll continue our analysis of this text. Thank you, everyone. Hello, everyone, and welcome back. In this lecture, we'll continue our lecture on text analysis. In the previous lecture, we imported and instantiated our count vectorizer object, and then we used count vectorizer to convert our trained text document into a matrix of word counts. And then we use the fit method to learn the vocabulary of our trained text document. And we saw that by using the get feature names, we differentiated it from our original trained text document. The next thing we'll do is transform our document into a documenter matrix. For that, we'll be using a method known as transform. Okay. So we have our vector object, and we'll call the transform method on it, vector.transform, and then we'll pass our train text document, train underscore text, and we'll save this in a variable called train text dt matrix for documenter matrix. Now let's see what our train text documenter matrix object looks like. Train text documenter matrix. So here now we have a sparse matrix of type numpy 3x7. So what does this 3x7 mean? This means 3 rows by 7 columns. Okay, now our original train text document is converted into a documenter matrix, a 3x7 sparse matrix. So 3 stands for the number of rows. In our case, each row represents a single string in our train text. So that will be 1 row. Go take a cab will be a second row, and then this string is our third row. So that's the number 3, number of rows. How about 7? 7 represents number of columns. That represents this feature names, which are cab, go. So if we count this, these are 7. 1, 2, 3, 4, 5, 6, 7. Okay, that's what the 7 means.
number of rows by columns. And later we'll build a data frame and analyze all of these words in separate columns. Okay, but that's what the documenter matrix looks like. It's a 3x7 sparse matrix for this example. And we use the transform method to convert our vector object into a documenter matrix. Okay, and we can take this documenter matrix object and then convert it into an array by simply calling the array method to array method. To show you an example, so let's call our train text documenter matrix object and then call the toArray method on it, and it will give you an array representation of our document. So here in the array representation we see 3, right? We have our 3 rows, and then those will be our columns, and each column represents each of our feature names. So the first column is for cab, second column is for go, and so on. Let's create a data frame. I think that will be more visual, and I'll save our data frame in a variable called text pd.dataframe, and we'll be creating a data frame from our train text documenter matrix. So I'll convert that, so copy it here, and then our column names will be this vector that get feature names. So each word or each string represents a single column. So let me copy this and paste it here. Okay, now let's call the head method on our text object, text.head. So here we have a data frame, 3 rows by 7 columns, right? So the numbers are the same as we see in this array. Okay, cab, go home, play, soccer, tonight, take, and tonight. So 7 columns. Let me call our train text object and show you what this data frame means. Okay, I mentioned that the first row is this first document, this first text, go home tonight, right? And the presence of each word is represented by either a 0 or a 1, right? 0 means that word is not in that document. So for instance, if you take this go home tonight, so if you go under go, there's one go in the entire document. Home, we have 1 home, right? And then tonight, we have 1 word tonight in the first document, in the first text document. And so we have the number of count of those words in the first row. So 1 go, 1 home, and 1 tonight. Okay? Similarly, if you take the second row, we have go, take, and cab. So if you go to those columns, under go, we have 1 word go, 1 take, and cab, a single word. Whereas if we take the third document, we have soccer appears twice, right? So if you go under the soccer column, you'll see 2. It means soccer appears twice. Then play appears once, and go appears once. So this is what this sparse matrix represents, the 3x7 sparse matrix. If you remember what we said about our algorithms, they work on numerical data, and each of the features have to be of the same size, right? We have to have the same feature names. That's what we have here. So we have the 7 features for our entire document. Okay, that's very important. And we were able to create that by using count vectorizer. So let me summarize what we did so far. We looked at a simple train text document, and we used the count vectorizer to convert this text document into a matrix of word counts. And then we used the fit method to study the vocabulary of this text document. And we dropped punctuations and the letter A and so on. And we were able to see the feature names by using the getFeatureNames method. And after that, we converted our document into a documenter matrix by using the transform method. And we saw that our documenter matrix is now a 3x7 sparse matrix. So from here, we can conclude that a given document can be represented by a matrix of words, by a sparse matrix, right? Where a single row represents each document in our document set, whereas each column represents a single word or token. And we don't really care about the position of the words, right? That's not necessary for us, for our purpose. So you might hear or read various words about what we have learned so far. You might read bag of words or vectorization, corpus, and so on. But that's what we did so far. And in order to understand more of those words, I have a link here under Scikit-Learn. If you look for text feature extraction, you can be familiar with those words. That's what we did so far. Vectorization, counting, and so on. Hello everyone, and welcome back. We'll continue our discussion on text analysis. So far we have seen feature extraction, and you can check out the documentation about feature extraction on Scikit-Learn. We have seen that in order for our algorithms to work, we have to first convert our data into a number format. And we saw various methods for that. We looked at count vectorizer, and we saw some terms like token, tokenizing, and counting. And we called the overall process vectorization, which is the process of tuning a collection of text documents into a number format. And that strategy is known as bag of words or bag of n words representation. So you can read more about it in detail in this document. Okay, so I'll go back to our Jupyter notebook and show you one more thing. Let's see the type of train text documenter matrix. Train text documenter matrix. And we saw that it's a matrix, a sparse matrix. And one more thing I want to show you is if we try to print our train text documenter matrix and run it, here we'll see the position of each of our words. Okay, so this 0, 1, 0, 2 represents the row index position and the column index position. Okay, so when we work with the sparse matrix objects, what we store is the position and the number of occurrences of our words, only the non-zero values. Okay, that's why we have 1, 1, 1, 1, 1, 2. We don't store any of the zeros. So 0, 0, 0, we don't store them. Okay, that's one thing to remember about our sparse matrix objects. Great. Next, let's look at an example. So previously, we trained our model on these features, right? So these are the features that we extracted from the given document set. What we'll do next is consider a different document set. And let me save our document in a variable called test text. So let's take this document for example. And what we'll do next is convert this document into a documenter matrix and see what we'll get. Okay, so if we take our vector object, our count vectorizer, and then call the transform method, and then pass this test text document, test underscore text,
And let's save this in a variable called test text documenter matrix. Okay, so we are converting this text document into a documenter matrix. Now let's convert this test text documenter matrix object into an array by calling the toArray method. Okay, what do you think we'll get when we run this? So our document is first converted into a documenter matrix, and then an array representation of a documenter matrix will be printed. So what we'll get is an array format. Let me run it and show you. So here we got the result 0, 1, 0, 1, 1, 0, 0. If you remember, we have trained our model previously on these 7 words, right? We use the 7 words to train our model. So anything that we pass that is not represented by any of these words will be dropped. So for instance, here in our test text document, the word don't will be dropped. That's because our model doesn't know anything about the word don't, because we haven't trained on it, right? There's no don't in here. So that's what it does. Since we trained our object on this our model on this 3 by 7 sparse matrix, the first thing it does is drop any words that it doesn't know or recognize. In this example, the word don't will be dropped. And the second thing it does is it makes sure we have the same length of features, right? So that's the transform method. It transforms so that we have 7 features as a result. Okay, that's why we have the 7, 0, 1, 0, 1, 1, 0, 0. Okay, let's convert this into a data frame and show you. So pd.data frame, and then we'll pass our test text documenter matrix into an array object. We'll pass that, and for our column names, we'll pass our vectors get feature names. So we'll pass, let me copy this, our columns get feature names, copy it and paste it here. Now let's run it. Oh, I copied columns twice. Let me remove this, run it again. Okay, there you go. So we have cab, go home, play soccer, take tonight. Those are the same features as we trained our model earlier, right? And here our document, we only have one document. That's why we have one row here. And then we represent the words and then check the occurrence of the words. So soccer is in our feature and it appears once, so you see a count of 1. Don't doesn't appear at all in our features, so the word don't is dropped. Play appear once, so we have a count of 1. Go appears once, so here we have a count of 1. So any consecutive test document that we pass will be first converted into a documenter matrix, and then all the words that are not recognized will be dropped because our model doesn't know about those words. Okay, let's look at one more example. Okay, next let's consider this test document. So we have 4 documents. Soccer, don't play, just go home, and then hey, I hope to see you all in the soccer game. And then we have the game was awesome, he scored at the end and won. And finally we have the game was awesome, he scored at the end, won, and off to home. What we'll do is we'll convert this into a documenter matrix, and then we'll use the toArray method to build our data frame and see what we have for our test text document. Okay, the first thing we'll do is use the transform method on our vector object, on our count vectorizer, and convert this object into a documenter matrix, and I'll save it in a variable called test text documenter matrix, and that will be equal to our vector object, our count vectorizer, and then we'll call the transform method vector.transform, and then pass our test text. So here we have trained our model on the 3x7 sparse matrix as we have seen previously, and all the words that it doesn't know will be dropped. For instance, this awesome, was, game, scored, all of those, they will be dropped, and the number of features will still be maintained. So we have 7 features. Our model has 7 features, so the number of features will be maintained. It won't be different. Even if we have a bunch of words here, the number of features will still be maintained. Okay, that's an important concept. So when you try to make a prediction, the number of features must be maintained. So the number of features in your training and testing dataset should be the same. So once we have our documenter matrix, we can convert that into an array by calling the toArray method. That toArray, okay, and run it. So we have a 4x7 array. So 4 represents, right, the number of documents that we have. We have 4 documents, so 1 for each, and the columns represent our features, the 7 features. So let's convert this into a data frame. So pd.data frame, and then pass our array object here, and then for column names we'll pass the getFeatureNames method that we used before. So we'll pass this, command C, paste, and then paste it here, command V. Let's run it now. Okay, now we have our 7 features, and then it will check each of our documents. Test text, let me type it here, test text. So if you take the first document here, which is represented by row 0, so the word soccer and go are recognized, so, and they appear once, so we have a count of 1 1 1 1 for those, and don't and just will simply be dropped because those are not recognized in our model. And similarly, if you take the third row, which is our third document here, none of the words are recognized by our model, so we have a count of 0 for each of our features. Whereas if we take the last document here, only one word is recognized, which is the word home. Home has a count of 1, and all the other words are dropped. Okay, so what we have done in this model building is we have learned the relationship between each of these features, right? We have learned the relationship between the 7 features. And if we pass any new word, since we haven't trained on those new words will be dropped. Okay, so this is the basis of text analysis. What we'll do in the next lecture is consider a dataset which consists of spam and ham messages. Spam and ham. Okay. Ham basically means not spam. And we'll analyze the dataset, convert it into a documenter matrix, we'll build a model, and then evaluate how our model will do, okay, on differentiating spams from ham. For that, we'll be using a dataset by University of California. So if you go to this website and then click on the data folder link here, you'll see an SMS spam collection zip folder. What you can do is you can download this zip folder and then unzip it where your Jupyter Homebook is located. Okay, and then we can simply use the
read CSV method to grab the contents, or you can simply use the file I have provided. I have saved this file as smsdata.tsv file. You can simply use that file, or you can go to this directory and then unzip this folder and place it where your Jupyter homebook is located. Okay, I'll leave the link in the lecture note. Thank you everyone, and I'll see you at the next lecture. And welcome. In this lecture, we'll look at a dataset consisting of spam and ham message, and we'll try to build a model and predict whether a message is ham or spam. For that, here is the location of the dataset. It's in UCI's database. So if you go to that URL, you can click on the data folder here and then download this SMS spam collection zip folder and then unzip it where your homebook directory is located. Okay, this is what the SMS spam collection looks like. It consists of ham and spam messages. Or you can use this SMS data.tsv file that I have provided. Okay, let's start uploading the dataset by using both of these options. Okay, and you can use whichever you prefer. So if you have downloaded the folder and then unzip it where your homebook is located, it will have this name, SMS spam collection, upper S and upper C. We can use Pandas read CSV method. Let's do that. So if you haven't imported Pandas, import Pandas. So pd.read CSV, and then we'll pass the name SMS spam collection. Make sure to pass the same name. Whichever is uppercase has to be uppercase, otherwise you'll get an error. And then for separator, we will use tab, and let's pass the names attribute and then pass the following names: label and message, and let's save this in a variable called SMS messages. Okay, now if we call the head method on our SMS message object, we see that we have two columns, label and message. So the label is whether it's a ham or a spam. Ham basically means not spam. And then we have the actual message. Okay, this is one of the methods. And if you want to use this SMS data.tsv file, for that we'll be using the read table method. So we have our SMS underscore data.tsv file. So if you want to use this option, we'll be using the read table method. So panda dot read table, and then pass your tsv file sms underscore data dot tsv. Then for header, we'll set it to be none, and then for names we'll pass label and message as we did before. For names, let's pass label and then message, and let's save this in a variable called SMS messages. Okay, run it, and let's check our SMS message by calling the head method. That head. Okay, we have the same result. We have two columns, label and message, whether the label is ham or spam, and the actual message. So feel free to use any of the above two methods. Okay, now let's analyze our SMS message dataset. Let's call the describe method. So if we call the
Oh, this is SMS underscore message. Let's run it again. So if we call the describe method, we have a count of 5,572. We have two unique ones, two unique labels, which are spam and ham. And the top one is ham. We have frequency. Okay. So SMS message, if you call the tail method, you'll see the last 5 rows, right? 5,571. Indexing starts with 0. So that's the number of rows that we have. Now let's call the let's call the shape method to see the shape of our dataset. So SMS message.shape. You'll see that it's 5,572 by 2. So number of rows, and 2 is the number of columns. And you can call the value counts method on your labels to see how many of the messages are spam and how many of them are labeled ham. Let's do that. So we have SMS message dot label. We'll index the label column and then call the value counts method on it, and we'll see that we have 4,825 of them are ham messages, whereas 747 of those are spam messages. So our goal is to distinguish whether a message is a spam or a ham, right? But our algorithms won't know spam or ham. So for that, we need to convert these labels into a numerical format, which is 0 and 1, right? Let's do that. Let's add another column, and then we label the spams as, for instance, maybe 0 and the other one as 1. So let's add a new column. We have our SMS message dataset, and then name of our new column, let's call it label underscore number. Then we'll say SMS message. We'll index our label column, and then we can simply call the map method and then pass a dictionary to map our ham to a 0 and our spam to a 1, or vice versa. So for ham, we'll map it to 0, and for spam, we'll map it to 1. Okay. Now let's see if it has worked. So we'll call the dataset dot head. Okay, you see now ham is 0 and spam is 1. Now this is much easier to work with since it's in numerical format. The next thing we'll do is identify our training and then testing datasets, right? What we'll do is we'll train on messages and try to predict whether that message is a spam or ham. Okay, so let's define two variables, and we'll store all of our messages in the variable x, and this label numbers will be saved in a variable y to represent target. Okay, so we have our SMS underscore message, and then we'll index the message column, and our target will be whether it's a spam or a ham. So SMS message dot label underscore number will index the label number columns. Okay, now let's print the shape of our x and y objects. So the shape of x is 5,572, and if we also print the shape of the y variable, it will be the same, 5,572. So here we see that the shape of our x is one-dimensional, and that's important to remember because when we use the count vectorizer only accepts one-dimensional objects. Okay, and the purpose of the purpose of count vectorizer is to transform this one-dimensional object into a two-dimensional object. Okay, so it's important to pass our count vectorizer a one-dimensional object. Next, let's split our x and y datasets into training and testing datasets. For that, let's import the train test split method from Scikit-Learn. So from sklearn.crossvalidation, we'll import the method. From sklearn.crossvalidation, import train test split. And we'll use this train test split to divide or split our x and y datasets into training and then testing sets. And we'll store them in 4 separate variables: xtrain, xtest, ytrain and ytest, ytrain and ytest. Again, you can use any variables that you want, it doesn't matter. But you have to be consistent throughout your model. So we'll call our train test split method and then pass our x and y datasets. And for random state, I'll just pass 13. So if you want to get the same exact result as me, you need to pass a random set of 13. And let's also pass the test size attribute and set it to 0.3. So we'll use 70% of our dataset for training and 30% of the dataset for testing. Okay. Now let's print the shape of our xtrain, xtest, ytrain and ytest. So print xtrain, xtrain.shape, xtest.shape, run it. Okay, so xtrain we have 3900 and for xtest we have 1672. So our training dataset is 70% of the entire dataset, and our testing dataset is 30% of 5572. Similarly, if we print the shape of ytrain and ytest, ytrain.shape and ytest.shape, you'll see the same number, 3900 and 1672, 7030. The next thing we'll do is instantiate the count vectorizer object and then convert our training dataset into document term metrics. So one question you might ask is that why did we split our dataset into training and testing datasets before we instantiate our count vectorizer? The reason is because when you analyze your testing datasets, there will be certain words that your model won't recognize, right? So we want to be able to drop those features as we have seen in the previous lectures. So that's why we are splitting our dataset before we call the count vectorizer object, as some of your training data will not distinguish or know certain words in your testing dataset. And we want to be able to drop those words that our model doesn't know. Hello everyone and welcome back. In this lecture, we'll continue our discussion on the SMS message spam ham classification. So in the previous lecture, we have split our dataset into training and then testing datasets. The next thing we'll do is instantiate the count vectorizer object, and we'll save it in a variable called vector, and we'll set that to be equal to count vectorizer. Once we have that, we'll call the fit method on our count vectorizer object so that we can learn the vocabulary of our training dataset. Let's do that. So we have our count vectorizer object, and we'll call the fit method and then pass our xtrain object. And once we fit our count vectorizer with our xtrain object, we'll need to transform this into a document term matrix. For that, we'll call the transform method. Okay, and then we'll save our document term matrix in a variable called xtrain dt matrix for document term matrix. Okay, and that will be equal to our count vectorizer, that's the fitted count vectorizer now, dot transform. Okay, and then pass xtrain. So this will transform our xtrain dataset into a document term matrix. So the count vectorizer accepts a one-dimensional object and then transforms it into a two-dimensional object. So now if we check the shape of our xtrain document term matrix, we'll see that it's a two-dimensional object. Let's print the shape. You see now it's 3900 by 7125. We'll come to see what the 7125 is. So here, once we instantiated our count vectorizer object, we call the fit method, and then we call the transform method. We could have done this in one step also by calling a method known as fit transform. Okay, so we could have also done this. We have our count vectorizer object, and then we can simply call fit underscore transform, and then pass your xtrain dataset. You could have done this also in a single step. Okay, I just wanted to show you that. So now let's get back to our xtrain document term matrix object. And if you look at it, it's a sparse matrix, 3900 by 7125 sparse matrix. What do you think this is? Just to give you a clue, in the previous lecture, our sparse matrix was 3 by 7, right? So this 3900 represents the number of rows, whereas 7125 represents the number of columns. So in this case, our columns are words, right, or tokens. So 7125 is the number of tokens or words, which are represented as columns. Okay, and this 3900 is the number of rows that we have in our xtrain. So if you check the shape of xtrain, it's the same, 3900. Let me go back to the previous lecture. So the shape of xtrain is 3900. Okay, so that's our xtrain dataset. Now we also need to transform our xtest dataset into a document term matrix, right? Because we need to convert it into a two-dimensional object, right? So the count vectorizer object will take a 1D object and then transforms it into a two-dimensional object by calling the transform method, right? So let's do that for our xtest dataset, and then once we convert it into a document term matrix, we'll save it in a variable called dt matrix for document term matrix, and that will be equal to our count vectorizer object dot transform, and then we'll pass our xtest object, then run it. Now if I call the xtest document term matrix object, what do you think the shape will be? So the shape will be, if I go back to see the shape of xtest, let me print it here, print xtest.shape. So xtest is 30% of our dataset, which is 1672. So the shape of xtrain document term matrix will be 1672, 1672 by our number of features, which is 7125. 7125. Remember, we'll always have the same number of features Otherwise, our models won't work. Okay, so let's run the cell. So we have a sparse matrix with a shape of 1672 rows by 7125 columns. Okay, and one important thing to note here is when I converted our X-test dataset into a document term matrix, we only applied the transform method, right? We did not apply fit first and then transform next, as we did with our X-train dataset. Okay, so any new word in our X-test dataset will be dropped. Okay, so when we use the X-train dataset to train our model, we analyze the vocabulary of X-train, right? That's the fit method. Whereas we're not using this fit method in our X-test. So anything new that's seen in our X-test dataset will be dropped. Okay, that's one thing to remember. Now we are ready to build our model. And for building our model, we'll be using multinomial naive Bayes. Multinomial naive Bayes is a good model for this kind of text analysis where we know the number of our features. Okay, first we'll need to import it from Scikit-Learn. Let's do that. So from sklearn.naive Bayes, import multinomial NB. Multinomial NB. What we'll do next is instantiate our multinomial NB model and then call the fit method to train our model with our X-train document term matrix and Y-train dataset. After that, we'll call the predict method and pass the X-test document term matrix for prediction. Okay, let's go ahead and do it. So once we instantiate our model, we'll save it in a variable called NB model, and we'll set that to be equal to multinomial NB. Now that we have instantiated our model, let's call the fit method on our NB model, that fit, and then we'll pass our X-train document term matrix, and then we'll pass our Y-train. Now we can call the predict method on our fit multinomial model. So NB model dot predict, and we'll be making predictions based on our X-test document term matrix object or dataset, right? And then we'll save this in a variable called Y prediction. So this will be the prediction. Y prediction will represent the prediction. And for comparing the result, we'll print out the accuracy score and compare this Y prediction and our Y test. Y test will be the actual result. So let's import metrics before we can run the accuracy score. From sklearn, let's import metrics, run it. Now we can say metrics dot accuracy score, right? And then simply pass our true result or true values, which is Y test, and then our predictions will be Y prediction. Okay, let's print this and run it. Okay, so here we have an accuracy score of 98%. So our model has a 98% accuracy in labeling messages as spam and ham. We can also print out confusion matrix for our result. We can say matrix dot confusion underscore matrix, and then pass your true result, which is Y test, and then your predictions, which is Y prediction. Run it. So this is your confusion matrix. This is your true negative, true positive, false positive, and false negative. It looks good. Only a few of those
are miscategorized as false positive or false negative. So in the next lecture, we'll analyze this confusion matrix and try to see why those are incorrectly labeled as ham or spam. So let's summarize what we did in this lecture. We instantiated our count vectorizer object, and then we used count vectorizer to convert our datasets from one-dimensional to two-dimensional. And once we did that, we fit our model to learn the vocabulary of our xtrain object. And once we transformed it into a documenter matrix, we saw that we have a sparse matrix, 3900 by 7125. This 7000 represent the number of tokens or words, which is the number of columns. And then we also used the transform method to transform our xtest into a documenter matrix. After that, we used multinomial naive Bayes for our model. We instantiated our model and then called the fit model to train our model with the xtrain documenter matrix object and the ytrain object or dataset. And then we made predictions off of our fitted multinomial NB model. And here we saw that we have an accuracy score of 98%. We also printed the confusion matrix for our result. And we see that we have some results labeled as false positives and false negatives. Thank you, everyone. Hello, everyone, and welcome. In this lecture, we will build a logistic regression model and compare our result with the multinomial naive Bayes predictions that we did in the previous lecture. The first thing we'll do is import logistic regression from Scikit-Learn. So from sklearn.linear model, linear underscore model, import logistic regression. And once we import our model, we'll instantiate our logistic regression model, and I'll save it in a variable called log underscore model, and that will be equal to logistic regression. And we'll do the same thing as we do with other models. Once we instantiate our model, we'll fit our model with our training dataset, in this case our xtrain documenter matrix and ytrain datasets. And after that, we'll use the predict method to make predictions off of our model. So next we'll take our instantiated model and then call the fit method and pass the xtrain documenter matrix and the ytrain. So we'll be training our logistic regression model with the training datasets. And once we train them, we can call the predict method, and we'll save our result in a variable called y prediction 2 to distinguish it from our previous y prediction for the multinomial naive Bayes method. So our y prediction will be equal to our logistic model that predict, and then we'll pass our xtest documenter matrix object. Now that we have our prediction, we can call the accuracy score method and print out the accuracy score. So let's print matrix that accuracy score. We have already imported matrix in the previous lecture. So print matrix that accuracy score, and then we'll pass our true result, true value y test, and our prediction y prediction 2 in this case. Okay, y prediction 2. Now if we run this, we get an accuracy score of 97.9%, right? With the multinomial naive Bayes method, we had an accuracy score of, I think, 98%, close to 98.1.
let me print it, y test and y prediction, run it. So 98.08, almost 98.1% accuracy score with our multinomial naive Bayes method model, and an accuracy of almost 98% with our logistic regression model. Okay, so you can use more than one model to distinguish whether a message is a ham or a spam. And if you get almost a similar result with two different models, you can use the faster model. So in our case, the multinomial naive Bayes model is faster than the logistic regression model. We can also print out the confusion matrix result. So print metrics.confusion matrix, and then we'll pass our y test and then y prediction too. So that will print out the confusion matrix for our logistic regression model. So here we have our true negative, true positives, false positive, and false negatives. We have 29 and 6. With our previous model, if we print the confusion matrix and change this to ypred, we had 24 false negatives and 8 false positives versus 29 and 6 with our logistic regression model. One thing I want to show you is how we can print out those false positive and false negative values. How can we distinguish those? So for that, let's say we have our y-test, right? This y-test represents the actual result. And if I say y-test less than y prediction, what does this mean? Y prediction. So for our case, spam or ham, it could be either 0 or 1, right? And the only case where y-test will be less than y prediction is if y-test is 0 and y prediction is 1, right? And if you remember, we assigned ham labels as 0 and then spam message as 1, right? So in this case, it will be a y-test value of 0, which is the actual value is ham, the actual message is ham, but it's predicted as spam. So if we index that, let me show you. If we take our x-test dataset and then index this, where y-test is less than y-pred, and run this, this will give us the false positive ones. These are all the false positive messages, where the actually they are ham, but they are predicted as spam. So this represents the false positive. Similarly, for the false negative, all we have to do is convert the comparison sign to greater than, right? So in this case, y-test, the only time y-test will be greater than y prediction is when the y-test value is 1 and y prediction value is 0, right? Since we only have those two values, 1 and 0. So 1 is spam, so the actual message is spam, but it's predicted as ham, right? So if we print this, that will give us all the false negatives. So if we copy this and then try to find the length of it, so this will give us the length of our false negatives, which is, if I go back here, our false negative is 24. We have 24 false negatives. Run it, we have 24. And the length of this false positives is, the length of this false positive is 8. Right? 1, 2, 3, 4, 5, 6, 7, 8. Which is here in the confusion matrix. Right? And then we can take a single message, a single row, and then see why
it was inaccurately labeled as either a spam or a ham. So for instance, you can take this 731 and then index it here, xtest 731, and run it. So this is the message, email alert from this person. It goes on like that. So you can further analyze this and try to see why it was inaccurately predicted as either a spam or a ham. And we can use the same methods to find out our false positive and false negative values for our logistic regression model. So basically we do the same thing, right? We do the same exact thing, except we'll use y prediction 2, right? We saved our predictions in the variable y prediction 2. So I'll change that to 2, and let me remove that. So if we run this length of our y prediction 2, that means length of our false negative for our logistic regression model. The length is 29. And here, if we run this, we'll see all those 29 messages, which are false negatives. And similarly, to see the false positives, we just convert this to less than, and that should give us, how many false positives did we have? I think 8. Well, we have 6 false positives, right? We have 6 false positives. So if we run this, we need to change this to y prediction 2. Run it. We have 6 false positives, and we can see all those messages by simply indexing our xtest dataset, and we can see all 6 of those. Okay, so that's how we can compare different models and try to analyze the false positive and false negative results. Okay, thank you everyone, and see you at the next lecture. Hello everyone, and welcome back. In this lecture, we'll try to find out the most common words in our spam and ham. One method we have seen before that the count vectorizer object has is known as the get feature names. We have seen that method to find out how many words we have, right? So for instance, what we did was we have our vector object, and then we can call the get feature names method on it. Get feature names, and we can save this in a variable. Let's call it xtrain words. Okay, now if we check the length of xtrain words, we see that it has a length of 7,125, and we can, if we want to print out any specific words in our xtrain words object, we can simply index it. For instance, we can say xtrain words, and then let's say we want to see the first 5 words, so we can simply index it up to 5. So these are the first 5 words in our xtrain words object, and we can simply index any position that we like. For instance, if we want to see words from index 89 to 100, we can simply index those positions. So these are the numbers, and towards the end, let's say we can say 7,000 to 7,010. Those are the words that we have. We can also use negative indexing to see to see words at the end. Another method I want to show you is known as the feature count method. Feature count. We can use this method to find out how many times a certain word or token appears at a given instance. Okay, so we can call this feature count method on our multinomial naive Bayes model. Let's do that. So last time we saved our model in a variable called
NB model, right? Multinomial NB model, and we can call the feature underscore count method on it to see how many times a certain word appears. So here in the result we have an array. So the first row represents our ham message, whereas the second row represents our spam message. Okay, and what do these numbers mean? So for instance, if we take this first number, it means the first word or token appears 0 times in our ham message, and it appears 6 times in our spam message. Okay, and if we consider the second word, it appears 0 times in our ham, and it appears 25 times in our spam message. So this is what it is. So this whole object is an array, right? It's a 2 by, we have 2 rows by this number of columns, 7,125. To double check that, we can simply call the shape method on it. So I'll call the shape method on our object, and it's 2 by 7,125, 2 rows by this number of columns. What we can do now is separate this array rows. We know that the first row is in ham and the second row is spam, indicates spam, right? So if we are to index this array, the first row will be index 0 and the second row will be index 1. So that's what we will do next. We'll index the feature count method and then store the first row in a certain variable and the second row in a different variable. And those variables will represent words in our ham and words in our spam. Let's do that next. So we have our NB model, and then we'll call the feature count method on it, and let's index the first row, right? So that will be 0 for rows, and we'll consider all the columns. Okay, so beginning to end. And let's save this in a variable called ham word count. Okay, and let's do the same for our second row. So our second row will be for our spam message, and we'll save it in a variable called spam word count, and that will be equal to our naive Bayes model, and then we'll call the feature count method on it, and then we'll index the second row, which is index 1, right? And then we'll consider all of our columns. Okay, now if we call ham word count, we'll see a single array. Its shape will be 1 by 7,125. So ham word count, run it. So that's our array, and if we call the shape, if we try to see the shape of it, it will be 1 by 7,000, right? Single array with 7,125 columns. Similarly, if we call our spam word count object spam word count and run it, we have the second row. Now let's combine these two together and create a data frame which will represent ham and spam and a list of words that we have. Okay, and we'll save our data frame in a variable called tokens. So pd.dataframe, and we'll pass dictionary key and value combination to create our data frame. So for our token, we'll use the xtrain words object that we created earlier. So we'll use that for our token, xtrain words. Let me pass that here. Token will use xtrain words, and then for our ham column, we'll use the ham word count object that we just created. Okay, ham word count, and finally for our spam column we'll use our spam word count. Spam. Okay, now let's see what our data frame looks like. I'll call the head method on our data frame. Okay, we have ham, spam, and token, and we have the first 5 words, right? 0, 0, this is the second word, then we have that, we have this. So for instance, if we take this fifth token, it appears 0 times in our ham message and once in our spam message. So what I will do is I will set the index of our data frame to be this token, so that token will be our index. Let me do that. So we have our data frame tokens is equal to tokens, and we'll use the set index method, and then we'll set the index to be token. Okay, now let's check our data frame again. Tokens.head. Okay, looks much better now. Again, these numbers indicate how many times the specific token or word appears either in ham or spam. For instance, this token 000 appears 25 times in our spam. Okay, and similarly we can check the last 5 rows by calling the tail method, and that's what we have. There's also another method known as class count, and we can call this method on our naive Bayes model, and this will tell us the number of observations that we have in our ham and spam classes. Okay, let me show you that method. We have our multinomial naive Bayes model, and we call the class count method on it, class underscore count underscore, and if we run this, we get an array of this value. So these numbers indicate the number of observations that we have in our ham and spam classes. So we have 3,386 observations in our ham class and 514 observations in our spam class. Okay, what we'll do is we'll take these instances of observations and then try to calculate the frequency of each word in our ham and spam class, and once we convert these observations into frequencies, we'll calculate ham to spam ratio for each of the words, and then after that we can deduct which words are the most common in spam and which are the most common in ham messages. That's what we'll see in the next lecture. Thank you everyone. Hello everyone and welcome back. Let's continue our discussion on text analysis. So in the previous lecture we have seen the occurrences of tokens or words in our ham and spam classes, and here in the example, in this data frame, you see that the first token 00 appears 0 times in our ham class and it appears 6 times in our spam class. Later on we'll be calculating the ratio of ham to spam, right? For instance, if we were to calculate the ratio right now, we would have to divide for instance 1 by 0, and that will give us a 0 division error, right? And in order to avoid that, since we have 0 in both ham and spam, what we'll do is we'll add some numbers, that way we don't run into a 0 division error. So I'll take this column and then add a certain number to it, and then we'll take the spam column and add the same number. Okay, that way we don't run into a 0 division error. Let's do that. So we have our tokens data frame, and then we'll take the ham column and then add a certain number to it. Let's add 10 to it. Okay, and we'll save it in the same data frame, tokens ham column. Okay, and we'll do the same for our spam column. So we'll take our tokens data frame and we'll index our spam column, and we'll add 10 to our spam column. So tokens.spam plus 10, and you can add any numbers that you like, but make sure to add the same number to both ham and spam classes. Okay, now let's check out our data frame by calling the head method. Okay, now we have 10 added to each of our ham and spam classes. Earlier we have seen the class count method, and that tells us the frequency of each observations in our ham and spam classes. And we saw that we have 3,386 observations in our ham class and 514 observations in our spam class. So what we'll do next is take our ham column and divide it by their appropriate class count observations. That way we'll be converting these numbers into frequencies. Let's do that. So for our ham column, we'll take our hams column tokens.ham and divide it by our class count. We have our model nb model that the method is class count, and we saw that the result we have two numbers, right? So this is for ham and that's for spam. So we can index it. This is index 0 and 1. So here for our ham message we'll pass index 0. And before I run this, let me import the division function from future, from __ future, since I am using Python 2. If you are using Python 3, it should be fine. So from future, import the division module. Okay, let me run our spam ham token. Okay, and next let's do the same thing to our spam column. We'll convert the occurrences of our spam tokens into frequencies. So we'll index and take the spam column and divide it by the class count of our spam class, nb model that class count. And for our spam class, it will be index 1, right? Now let's check out our data frame by calling the head method. Now we have the frequency of occurrence of each of the words instead of number of observations, right? What we can do next is take the frequency of occurrence for our ham and divide it by the frequency of occurrence for our spam, and that will tell us the ratio of a certain word in ham versus spam. Okay, let's start by adding a new column, and we'll call that column spam to ham ratio. You can call it whatever you want. So we'll take our data frame and then add a new column. I'll call it spam to ham ratio, and that column will be equal to our ham column. Let me change the name from spam to ham to spam. Okay, so we'll take our ham column and then divide it by the spam's column. So tokens that spam. Okay, let's run it and then check out our data frame by calling the head method. Okay, now we have a new column added, ham to spam ratio. We just took the frequency of occurrence for ham and divided it by the frequency of occurrence for spam, and we have a ham to spam ratio for each of our tokens. Next, we can simply use the sort values method and sort this ham to spam ratio values in ascending or descending order and see which are the most common words in our ham message or spam message. Let's do that. So we have our tokens data frame, and then we'll call the sort values method on it. and then pass the column that we want to sort, ham to spam ratio, ham to spam ratio, and we'll pass the ascending parameter and then set it to true or false, whichever you like. I'll set it to false, and let's check out our data frame. Okay, once we sort it, then we call the head method and then pass 20. So we'll see the first 20 most common ham words. Okay, so we have our word list here, token, and then ham to spam ratio. So this is by descending order, right? So these are the most common words that appear in our ham message. Okay, my, bet, gt, I, it, it, me, he, and so on. Okay, those are the most common ham words. And if you check the reverse, or instead of head, if I call tail, we'll see. So those will be the most common spam words, right? Since the frequency of ham to spam ratio is the lowest, right? So these are the most common ham words, as the ratio of ham to spam is the highest. And if you check the end of your data frame, you have this common spam words. For instance, claim, price, www, txt, and so on. If you like, also you can add another column and check the ratio of spam to ham. Let's do that quickly. So we have our tokens data frame, and then let's add a spam to ham ratio column, and then we'll set that to be equal to our spam column divided by our ham, tokens.ham, and then let's call the sort values method on it, and then pass our new column, which is spam to ham ratio, and let's pass the ascending attribute and then set it to false. Okay, and let's call the head method on it and pass 20. This will display the 20 most common spam messages. Okay, spam tokens or words. Let me run this. Okay, so we have claim is the most common spam word, followed by price, and then www, text, tone, UK, and so on. Okay, so these are the most common spam words, and that's what we also got in our previous data frame, right? When we call the tail method, we have claim, price, www, text, tone, UK, mobile, and so on, Nokia, right? So this will be the most common spam words. Okay, as an exercise for you, what you can do is, if you remember, we added 10 to our ham and spam columns so that we don't run into a zero division error. Try out this example by adding a different number to our ham and spam columns. Let's say add 5 or 3 or any number different than 0, or 20 maybe, or 100, and see the difference that you get. Okay, so these are some of the methods that we can use to analyze our text in general and find out the most common ham or spam words. Thank you everyone, and see you at the next lecture. Hello everyone, and welcome back. In this lecture we look at k-fold cross-validation examples. Okay, so for this lecture we'll use the iris dataset, and we'll create a model that can predict the iris species using the attributes sepal, length and width, and petal length and width. So if we have those 4 attributes, will we be able to predict the iris species? So for that, we'll be using the SVC model with linear kernel. Okay. And what if we use a k-fold cross validation with this SVC model with linear kernel? Will we still be able to predict the iris species? And finally, we'll see if we can get a better result by using the polynomial kernel. Okay? So we start by importing the modules and library that we need. Okay? From Scikit-Learn, import datasets. From Scikit-Learn, import cross-validation and SVM. Once we have that, let's load our iris dataset. I'll store the result in a variable iris. Okay, so datasets that load iris. And then let's store the iris data and target in 2 variables, x and y. Iris.data and y is iris.target. Okay, let's print an instance of our iris database. Okay, so for that we'll use the describe method, describe diskr. Okay, this should be load iris, not irs. Let's run it again. Okay, so we have an instance of our iris plant database, and these are the 4 attributes: sepal length and width and petal length and width. Okay, now let's use our train, test and split method. Okay, so the first thing we will do is split our iris dataset into some training and testing datasets, and then we'll build an SVC model, support vector classification model, so that we can predict the iris species using our training data. Okay, let's see that. So once we split our iris data into training and testing data, we'll store them in 4 variables: xtrain, xtest, ytrain and ytest. Okay, so xtrain, xtest, ytrain and ytest, and finally we have ytest. Okay, we'll be using the cross validations train test split method. Cross validation that train test split method, and we'll pass our iris data and target. Okay, so for iris data we have our variable x. Here we have iris data as x and our target as y. So we'll pass those x and y, and we'll use a test size of, let's say, 40%. So for test size we'll pass 0.4, which is 40%, and then I'll pass a random state of 0. Okay, so x contains my iris data, which is the actual measurement of each iris flower dataset, and y is our iris target, which are the things that we are trying to predict. In our case, we're trying to predict the species of the iris flower. Okay, and a test size of 40% means we are using 40% of our data for testing purposes. The default is 30%. Okay, now let's build our model. So we'll be building the SVC model. Okay, so we'll use that method, and then we'll pass svm.svc, and we'll pass a linear kernel first. Okay, so kernel will be linear, and our C value is 1. Okay, and then we'll call the fit method on it, and then we'll pass our training data set. So that's fit, and then we'll pass our X train and Y train and Y train. Okay, so here we fit our SVC model with linear kernel using our training data features. Okay, so training data features, and then our target data. Good. And let's store our model in a variable called, let's say, CLF. Okay, now we'll pass the score method on our CLF model and try to see its measurement, okay, or its performance. So CLF that score, and then we pass our X and Y test variables. So X test and then Y test. Okay, so we're gonna measure the performance of our SVC model that we created using our testing data set. Okay, let's run it and see. Okay, here we have 0.96667. Okay, so this means that almost 96.7% of the time our SVC model is able to predict the correct species of the iris flower based on this measurement attributes, this 4 attributes. Okay, so our model with this linear kernel, our SVC model with the linear kernel, is able to accurately predict the iris flower species 96.7% of the time. Okay, that's what this means, this result means. Okay, remember we are only using 500 and 150 data sets, right? For each of the, we are using 150 data sets, 50 for each of our iris plant species, iris flower species, and this is a relatively small data set, so we could be overfitting to our train test split method. Okay, and in order to avoid this, let's use the k-fold cross validation so that we can protect against this overfitting. Let's see that next. For this, we'll be using the cross-val score method, and then we'll pass our model that we created here, which is the CLF model, and we'll also pass our iris data and target and a cross-validation value. Okay, so cross-validation, that we'll be using the cross-value score method, cross-val score, and then we'll pass 4 attributes, which is our model that we created earlier, SVC model, and we stored it in the variable CLF, so we'll pass that CLF, and we have our iris data X, we have our iris target that Y, and then we'll pass a cross validation value of, let's say, 5. Okay, so basically this cross validation fold is equal to 5. It means that it will use 5 different iris training data sets, and it will reserve one for testing. That's what this cross-validation fold means. Okay, you can pass any number, 6, 7, 4, it doesn't matter. It basically means it will use the cross-validation fold, 5 in this case. So this way it will use 5 different training data sets. Good. And let's store this in some other variable. Let's say score. Okay. And then let's print our score. So we can print our score so that we can see the accuracy of each run, right? Each fold. Since we passed 5, we'll be able to see 5 score results. Okay? And then we'll also print the mean of those 5 scores. Okay? So we'll print the mean by calling the mean function on our score. Let's see the result now. Okay. So we have a mean score value of 98%. And for the individual runs, we have 96.7%, and we have 200%. Right? So that's for each fold. That's the accuracy, and overall, we have a mean score of 98%. So we have a 98% accuracy, which is better than the 96.7% accuracy that we got earlier. So by passing this cross validation fold, we are able to predict the right iris flower species 98% of the time. Okay? Now that we have seen this, let's see if we can get a better accuracy by using or passing a polynomial kernel. Remember, so far we have only used a linear kernel, right? Now let's pass a polynomial kernel. Good. So what do you think the result will be? Do you think we'll get a better accuracy or a better fit? Or will we still have a problem of overfitting? Okay, let's go and see that. Okay, let's create our model again. So svm.svc, and then we'll pass a kernel. In this case, poly instead of linear. So we have our poly for polynomial. Then we have a c value of 1, and we'll pass the fit method, and then pass our xtrain and ytrain datasets, xtrain and ytrain. Okay, and let me save it again in a variable called clf. So this will be my model. Okay, now what we did is we fit our model into the training datasets. Okay, now let's do the same as we did here. Okay, so cross validation, and then we'll call the cross val score method, cross val score, and we'll pass our svc model object clf. We'll pass our iris data, our iris target, and then we'll pass a cross validation fold of 5. Okay, and again we'll store this in a variable score, and we'll print the individual scores and the mean score value. Okay, so we'll print score, and we'll also print the score values, average score.mean. Let's run it. Okay, and this time we have 300% accuracy, 190%, 193%, and an overall accuracy of 96.7%. Okay, here we have an accuracy of 96.7%, which is lower than where we used a linear kernel, right? So this 96.7% is lower and basically the same as what we got earlier, right? So in this case, our polynomial kernel is overfitting, right? Since it produced even a lower accuracy than the simple linear kernel. So this polynomial kernel is overfitting since it produced a lower accuracy. And one thing to know is that this polynomial kernel, by default, its degree is 3, right? And you can play around with this polynomial kernel and see if you can get a better accuracy by passing different degrees for our polynomial. So this takes another attribute called degree, right? And by default, our polynomial kernel has a degree value of 3. And see if you can get a better result or a different accuracy result by passing, for instance, degree 2 or 4 and so on. Okay. So to summarize what we did here, we used the 4 attributes of our iris flower dataset to predict the iris species. And for that, we used the SVC model with a linear kernel, and we saw that we were able to predict the accurate iris plant species or flower 96.7% of the time. And since we are only using 150 data, and this is a small data, so there could be overfitting to our train, test, and split method. For that, we use the k-fold cross validation technique, and we passed a cross value fold of 5 to protect against this overfitting. And we got a better result here, 98% accuracy. And we also used another SVC model using a polynomial kernel to see if we could get a better accuracy or to see if that was overfitting. And then we found out that the SVC model with a polynomial kernel of degree 3 was overfitting. Okay? Thank you everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the lecture on PCA, Principal Component Analysis. Let's start by looking at dimensionality reduction. Dimensionality reduction is deriving a set of new features which is smaller than the original feature, while preserving variance in our data. So this dimensionality reduction is where we derive a set of new features which is smaller than our original feature. And while we do that, we try to retain the variance of our original data so that the new data is not much different from the original data. And PCA is one of the most commonly used dimensionality reduction techniques. It stands for Principal Component Analysis. It's a commonly used dimensionality reduction technique. And we use this dimensionality reduction in many applications like facial recognition and recognizing handwritings and so on.
So PCA is performed using linear combinations of the original features of the data. In this lecture, we'll look at the famous iris dataset. We'll look at our iris dataset and see how we can apply principal component analysis. In the coming lectures, you'll see where PCA is applied. We'll have a few projects that will apply PCA. So as usual, let's start by importing NumPy as NP, Pandas as PD, and Matplotlib. We'll be using PyLab for plotting figures. So this is the PyLab magic function. It will help us. This is similar to the Matplotlib inline magic function. And I will import Cycle from Ether Tools. We'll be using that later on. And from Scikit-Learn's dataset, we import load iris. We'll be working with our iris dataset. Next, let's import PCA, Principal Component Analysis, from Scikit-Learn. Let's do that. From sklearn, that decomposition, we import PCA. Let's load our iris dataset, and I'll save this in a variable called iris. So load iris, and then as we have seen, iris, we have a data and target. I'll save those in x and y variables. X is equal to iris dot data, and y is equal to iris dot target. So as we have seen, the iris dataset has 4 dimensions. So the sepal length, sepal width, petal length, and petal width. Those are the 4 dimensions. And we'll use this PCA to reduce those dimensions into 2. And while we do that, we'll have to preserve the variance of our original dataset. Okay, now that we have imported PCA, let's pass. So I'll call the PCA and pass number of components variable, attribute, n underscore components, and I'll set that to be 2, and I'll pass a second attribute which is called whiten, and I'll set that to be true. So that will help us in normalizing our data set. Okay, so we are able to visualize 2 or 3 dimensional figures, and PCA helps us in doing that. So I'll save this in a variable called PCA. Okay, and then next we'll fit our PCA object. So we can simply call PCA and then apply the fit method on it, and we'll pass our iris data X. Okay, now we see that our model is fitted, our PCA model is fitted with n components is equal to 2. And I will show you another example, another method known as the components method, and this method will help us in reducing the dimension. So if I call the components method on our PCA object, which is the fitted model on our PCA model, let's call the components method. So components underscore, and run it. Okay, here we see a 2-dimensional array, right? So we reduce dimension from 4D to 2 dimensions, to 2D, by projecting it down to these 2 4-dimension vectors, which are the basis for our 2-dimension projection. Okay, that's what we see here by calling the components underscore method. Okay, and we have some other methods that we can call on our PCA object, like explain variance ratio, which will show how much of the variance is preserved from our original data. Let me show you that. So PCA, we call the explained variance ratio method. Explained variance ratio underscore. Let's run it. So we have an array of 0.92 and 0.053. This means that we have captured about 92.5% of the variance in the first dimension, and we have captured an additional 5.3% of the variance in the second dimension, right? And we can also call the sum method on this. So we can call a sum method on our variance ratio. And here we see that we have captured almost 98% of the variance. So our transformed 2D dataset has captured almost 98% of the variance from the 4D original dataset. Great. We can call the transform method to transform our iris dataset. So PCA.transform, and then we'll pass x as we did here, iris.data, and then let's save that in another variable called xPCA. Now let's try to visualize our iris dataset by using PyLab. If you haven't imported, please import the Matplotlib and ether tools. Okay, I'm going to define a function before we can plot so that we can specify certain things in our function. So I'll name my function, let's say plot iris. I'll just name it plot iris in 2 dimensions. Or let me just call it plot iris. And my function will take three arguments or parameters: data, target, and let's say target names. Let's specify colors as a cycle of RGB, and we'll use the length of our target names later on in our plot for scattering the plots. So length of the target names, then we'll create a range using the length of our target names. So I'll pass that as a range, and let me save this in a variable called id. And finally we'll plot our figure, plt.figure. And let's use some for loops to specify our x and y axis, and then to pass this ID and color that we created. So let's say for x and z in label, in zip we'll pass our IDs that we created, colors, and then target names. We'll plot a scatter for each of those, and then let's pass our x and y axis, our x and y. So we'll pass data, and then we'll set the target
to be equal to our x value to 0, and we'll do the same for our y-axis. Data, we'll pass target to be equal to x and 1. We'll set c to be equal to c, and our label will be equal to label. And finally, we need to set our legend. Let's do that. plt.legend. Okay, I think everything is set now. Let's call our function. So plot iris, and we can pass text 3 parameters. So we can pass our transformed model, which is xpca, and our iris target data, and then we'll pass our iris target names. Let's run it. This should be iris.target names. Okay, so this two-dimensional projection using PCA gives us a good insight into the distribution of the different iris species, and we see that iris setosa is distinct compared to the other two species. So that's how we can use PCA in reducing dimension to 2 or 3D dimensions. Great. So this is just a quick overview of dimensionality reduction, specifically PCA. So just to recap, dimensionality reduction is deriving a set of new features which is smaller than our original feature. And principal component analysis, PCA, is a common dimensionality reduction technique. And here we saw how we can apply PCA on our iris dataset. And I have a link here for you. You can read more about it on Scikit-Learn's documentation about principal component analysis, PCA. We'll look at more examples in coming lectures and projects. But in the meantime, if you want to read more about PCA, here is the link. This documentation is good and goes in depth. Okay, great. Thank you, everyone, and I'll see you at the next lecture. Hello, everyone, and welcome back. In this lecture, we'll see how we can identify outliers and how we can deal with them. Okay? So sometimes outliers, they can skew our result to the right or to the left, and we may not get the result that we want. So usually we use standard deviation as a way of determining outliers. Okay? Usually if some value is within 1 to 2 times the standard deviation, it's okay, but anything outside of that range is considered an outlier. That's what we will do in this lecture. Okay? We'll start by creating a normal distribution function, and we'll draw that normal distribution function of the average income, and then we'll introduce an outlier and see how we can remove that outlier. Okay? So as usual, we start by importing NumPy and Pandas. Okay? Let's do that. Import NumPy as NP, import Pandas as PD, and then we'll import Matplotlib. Import Matplotlib.pyplot as PLT, and then we'll import the matplot libraries inline. Matplotlib inline. Okay, let's create a figure to show the normal distribution of income. Okay, so I'll use the random.normal method. This will create a normal distribution. This is the simplest way to create a normal distribution function. Okay, so np.random.normal, and I will pass my mean value, let's say 30,000. So that's, let's say that's the average yearly income of a certain country. Okay, 30,000, and let's have a standard deviation of 10,000. Okay, and let's consider 20,000 people. Okay, and let's save that in a variable. Okay, income normal distribution. Now let's plot this income normal distribution. Okay, so plt.histogram, and we'll pass our income normal distribution object, and let's say number of pins, let's see 25. Okay, and then we'll show our graph. Let's see what our histogram looks like. So this is a normal distribution function, right, with a mean of around 30,000. Now what I will do is introduce an outlier and then see how it will affect our normal distribution function. So for that I will add a higher income in my income normal distribution function. Okay, so let's do that, and I'll save it back in the income normal distribution. So np that I will use the append method. Okay, and then I will take the income nd object and then introduce, let's introduce a higher income so that it will be an outlier. Okay, let's say 2 million, let's say 2 billion. How much is that? 1 2 3 1 2 3, that's 20 million. Okay, so I have introduced one person with a yearly income of 2 billion into our data. Okay, so I have added that, appended it to our income normal distribution object. Okay, and now let's plot and see the result. Okay, you see what the graph looks like now? Just by introducing one outlier we get a different result, and this is not very helpful if we are analyzing the normal distribution of average yearly income. This will mislead us, right? So we have to define what outliers are. We cannot just go and remove any outliers, right? So for that, the standard deviation is a good value for identifying outliers. So any data that lies outside of, let's say, 1 to 2 times the standard deviation value is considered an outlier. Let's see an example of that. So for that, let's introduce or define a function, and that function will remove outliers, if any. Okay, so let's define, let's call it remove outliers, and then it takes some data, and then let's see np.median. We have the median of our data. Okay, let's save it in a variable median, and let's define let's find out the standard deviation and store it in a variable sd. Okay, so np.std, that's the method to find out the standard deviation of a given data. Now what we will do is we'll use list comprehension to filter out the data, and we'll use standard deviation within 1.5 times within the standard deviation. Okay, let's do that. So we can say x for x in our data, if, let's say, median, we have our median, right? Median minus, and then we'll make it 1.5 times, our standard deviation. So 1.5 times our standard deviation SD, and that's less than our x, which is less than our median, right? Plus 1.5 times our standard deviation. 1.5 times our standard deviation, SD. Okay, let me put that in parentheses. And then this is a list comprehension. Okay, so I'll close that in my brackets. And then let's save it in another variable. Okay, let's say new value. So this will filter out any outlier. Okay, and then we'll return our new value, and finally we can set our new value to this function. So new value is equal to remove our outliers, and then we can pass our data. Okay, for this case we'll pass our income ND. Okay, so income ND. Now let's have a plot. So plt.histogram, and then we pass our new value. Let's use 25 bins. Okay, and let's show our histogram. Let's run it. Okay, good. Now we have a normal distribution function, right? A normal distribution histogram. So the outlier was detected by this function and then removed by it. So we used 1.5 times the standard deviation value. Okay, usually it's between 1 to 2 times the standard deviation value. That's considered an outlier. Okay, so this is a brief introduction to how we can simply remove outliers. Okay, as I mentioned, we cannot simply remove outliers for no reason. We'll have, and at the same time, outliers may distort our expectation, right? In this case, we were expecting a standard normal distributed function of income with a mean value of 30,000, right? And a standard deviation of 10,000 in this case. But because we introduced this one outlier, our graph is skewed, right? And we defined a function. That function will check if the given data is within the median minus 1.5 times the standard deviation and the median plus 1.5 times the standard deviation. And then if it's not within that range, it will remove that data.
it will identify that data as an outlier and it will remove it. Okay, so that's how we can deal with outliers. So for your exercise, you can change this values and see if you get a different result. You can change this mean, standard deviation, and number of people. Use different data and see if you can identify an outlier and then remove it with this function. Okay, and again, you can also change the standard deviation to, let's say, 2 times the standard deviation or 1 times the standard deviation and see the effect. Okay, thank you everyone, and I'll see you at the next lecture. Hello everyone and welcome. In this lecture we'll look at a mini project exercise on k nearest neighbors. We'll be using the movie lens dataset from this website. So it contains ratings information from, let's say, movie lens 100k dataset has 100,000 ratings from 1,000 users on 1,700 movies. So they have lots of ratings data. For our project, we'll use this movie lens 100k dataset. Okay, so we'll need to download this zip file, ml-100k, and once you download this, unzip the file or folder and then place it where your Jupyter Homebook is located. Okay, so download this by clicking on it and then unzip the folder. It will download the folder folder named ml-100k. You can unzip that in the directory where your Homebook is located. We've seen that by defining some distance metrics between items in our dataset and then finding the k closest items, we can use those items to predict some property of our test items, right? And for this project, we look at the movie lens dataset and we'll try to guess the rating of a certain movie by looking at 10 closest movies in terms of rating and genre. Okay, so we'll be predicting or guessing the rating of a movie by looking at 10 movies closest to it in terms of genre and popularity or rating. And then we can apply this and check what the result will be if we consider 15 closest movies in terms of genre and popularity. And these are the steps we'll perform for our project. We'll start by importing columns and creating a data frame for our movie dataset. And then we'll define a function to calculate the distance between 2 movies. And we'll define another function to calculate the KNN of our movies. We'll start by importing NumPy and Pandas. So import NumPy as NP, Pandas as PD. Now let's load up the rating information of the movie lens dataset. Okay, for that I'll be using the read CSV function, and we'll pass the directory of our movie lens dataset. Okay, and we'll be using the u.data file, and this file has the rating information. This file has the rating information, and I'll save the result in a variable, let's say ratings. For you, if you unzip the whole folder in your Jupyter Notebook location, you'll have to pass the folder name also, which is ml100k. Okay, so it would look something like this if you unzip the folder also. Since I unzipped the files individually, I have the u.data file in my home book location. So I have u.data here. So I'm just going to pass u.data. Okay. And then let's see. Ratings that head. Let's run it. Okay, it looks like our values are separated by tabs. So let me pass a separator. So a tab separator or delimiter /t. Okay, I have 4 columns. So this is the user ID, ratings, and movie ID. We only need the first 3 rows for our project, the first 3 columns, and the numbers don't make much sense for us. So we'll convert this into some name that will make sense for us. So we'll convert that into user ID, movie ID, and ratings column. Okay, let me create that and store it in a variable called columns. So we'll have user ID, movie ID, and then we'll have rating. Okay, and let's pass that. So names is equal to our columns, and we only need the first 3 columns. We don't need the last one. So I'll pass another variable called use columns, and then range 3. That means we'll use columns 0, 1, 2, but not including 3. Okay, let's run it now. Good. Now we have a user ID column, a movie ID, and ratings column. For instance, user ID 0 gave this movie, whose ID is 50, a rating of 5, and so on. Okay? Now we'll group all the information by movie ID, and then we'll try to compute the total number of ratings. Okay? And once we have that, we'll calculate the average rating for each movie. Okay? So for that, we'll apply the group by method on our ratings data frame, and then we'll aggregate the result by rating and mean. Let's do that. So ratings that group by, and we'll group it by the movie ID. Then we'll call the aggregate method on it, and then we'll aggregate it by rating, by the ratings size, and the mean value. Okay? So I'll use a dictionary to pass the size and mean value for ratings. So rating will be my key, and for values, I'll pass the size and mean value. For that, I'll be using NumPy size method and mean method. Okay, np.size and np.mean. Good. Now let's store this in another variable. Let's say movie properties. Okay, movie properties. Now let's see what we have. Movie properties dot head. Good. Now we have our movie ID, rating size, and rating mean. For instance, 452 people rated movie 1 and the mean of the ratings, their rating is 3.87, whereas 86 people rated movie ID 5 and their mean rating was 3.3. Good. Here, the raw number of ratings is not very helpful for us for computing the distance between two movies, right? So for that, we'll create another data frame, and that will contain the number of ratings, the normalized number of ratings. So basically, it will have a value of between 0 and 1, where 0 means no one rated that movie, and then 1 will be the highest rating for that. So for instance, a rating of 3.87 will fall around maybe 0.75 or 0.7, something like that. Okay? So we'll be normalizing the number of ratings. Okay, let's do that. So we'll create a new data frame, pd.data frame, and then we'll pass our movie properties data frame. Okay, so movie properties underscore properties. Okay, and then we'll be using rating and size of our movie properties data frame. Rating and size. Okay, and let's store this in another variable. Let's say number of ratings, movie number of ratings. So movie number of ratings. Okay, now that we have our movie number of ratings data frame, we can apply a lambda function to normalize our ratings. That way, instead of this mean values, we'll get a value between 0 and 1. So for instance, 0 being no rating, and 5 is the highest rating, so a value of 3.87 would be somewhere around 0.7, and a value of 3.3 will have a standardized a normalized rating value of probably 0.6 or 0.65, and so on. Let's do that. So movie number of ratings, we'll apply a lambda function. So that apply, so lambda x, and we'll pass the minimum values and use the maximum values to get a range. So x minus np dot mean. I'll explain what I'm doing. Then we'll divide this by the maximum minus minimum, okay, to find the range. So np dot max minus np dot mean. Okay, so what we are doing here is we're finding the maximum and minimum number of ratings in our data set, and then we find the range and normalize everything against that range. That's what we're doing with this function. Okay, now let's see our new data frame. So movie number of ratings. Let me save this in a new variable so that it's easier, and let's call it our normalized number of ratings. So movie underscore normalized number of ratings. Okay, and let's view our result, our new data frame. That head, let's run it.
Good. Now we have our movie ID and size. So since it's normalized, so this rating mean value of 3.787, the new value, the new normalized mean is 0.77. Okay, and it goes on like that. So here we applied the lambda function on our entire movie number of ratings data frame, right? And then by finding the maximum and minimum number of ratings in our data set, we were able to find the range, right? And then we normalized the entire data frame against the range. That's what we did here using the lambda function. Okay, the second information we need is the genre information, and we get that from the u.item file in our folder. Okay, and this u.item file has 19 different kinds of genres, and then it has a value of 0 or 1, where 0 means that movie is not in that genre, and 1 means that movie is in that genre. In the next lecture, we'll look at the u.item file and then create some genre information. Thank you, everyone. Okay, now that we have our rating, let's look at the u.item file. And this file contains 19 different genres. So if we take a certain movie, and if the value is 0, it means it's not in that genre, and if it has a value of 1, it means it's in that genre. Okay, and then we'll create a dictionary, and this dictionary will contain the movie's name, its genre value, and we'll have a normalized score for its popularity and the average rating for that movie. Okay, I already created that dictionary to save some time, but let's walk through it and see what we did. So here in the first step, we are opening the u.item file. So in your case, you might have to pass ml-100k if you unzip the whole folder in your Jupyter Home Books location. Okay, that thing ml-100k / so you'll have to pass that. Once we open our u.item file, we iterate through every line in the file, so one line at a time, and then we strip out the new line at the end. Okay, and we'll split it by this delimiter. Once we do that, we'll then extract the movie ID, the movie name, and its genre. So we have 19 different genres, and once we have that, we finally construct a dictionary which maps movie IDs to their name, right, genres, and also their normalized rating. So this last step here, we're just constructing a dictionary which maps our movie IDs to their name, genre, and we also have our ratings information for those movies and their popularity. Okay, good. So let's see if this one works well. Good. Or we have an error. It says series object has no attribute ratings. Oh, this should be rating, not ratings. Let's run it again. Okay, looks good. Now let's see what information we have for certain movies. Okay, so I'll pass I'll call my movie dictionary and then pass, let's say, 1. Okay, for movie dictionary 1, I have Toy Story, and these are the genre information. So we have 19 different genres. So Toy Story is not in the first 3 genres. That's why we have 000, and then it's in the next 3 genres. So we have a value of 1. Okay, so that's the name of my movie. Genre, that's the genre. And then we have our movie normalized number of ratings. So that's what we got from our previous lecture, movie normalized number of ratings. So between 0 and 1. Okay, and size, that's the number of people who rated that movie, and the mean value of the rating is 3.87. Okay, now let's create a function. Okay, and that function will calculate the distance between 2 movies based on their popularity or ratings and their genres. Okay, good. So let's do that. Let's define our function. Okay, so define, and we'll be computing the distance between 2 movies. So compute, let's say, distance. Then let's have, it will take 2 variables, A and B. Those will be the movies. Okay, it will take 2 arguments, A and B. Okay, let's say genres. A is equal to, we'll pass A1. Okay, and genres for B, let's say B1, and then we'll calculate the distance between these 2 movies, genre A and B, and we'll base that genre distance based on its similarity using the cosine similarity function. Okay, let's do that. So for that, I'll use the distance method and then call the cosine similarity. So spatial that distance that cosine, and then we have our 2 genres, genre A and B. Okay, then we have genres B, and we'll store this in another variable. Let's say general distance. Okay, we are using this library spatial, so we need to import it. Okay, let's import that from SciPy. Import spatial. Okay, good. And we'll do the same thing for our popularity. Okay, we'll take the list of genres for each movie, and then now we'll take the list of how popular or similar they are to each other. Okay, let's do that also for popularity. So let's say popularity A is equal to A2, and popularity for my second movie is equal to B2. Okay, and we'll calculate the absolute value of the distance between the 2 popularities. Okay, so and then we'll store that in a variable called popularity distance. So popularity distance, absolute value of popularity A minus popularity B. Popularity A minus popularity B. Okay? And our function will finally return the result of general distance plus popularity distance. Okay? So let's pass that. Then it will finally return general distance plus popularity distance. Okay? So let's see what we did. The function takes two movie IDs, A and B, and then it calculates the distance between those two movies. That's what it will do. It will calculate the distance score. Okay? Here for general distance, we based it on similarity using the cosine similarity. Okay? Then for popularity distance, we took the absolute value of popularity A minus popularity B. So after this, we'll just take the list of genres for each movie and see how similar they are to each other. So 0 means it's not in that genre, and 1 means it's in that genre. Okay? Now let's call the compute distance function and see what we have. So let's compare two movies. Let's say movie 2 and 3. Let's do that. So compute distance, and then we'll pass movie dictionary 2 and 3. Okay? So movie 2 and movie 3. Movie dictionary 3. Okay, let's run it. Okay, so movies 2 and 3, we got a result of 0.49. So for this, the higher the distance, it means the movies are less similar. Okay? So let's check out movies 2 and 3 and see how similar they are. Okay? So I'm just going to print out the genre and rating information for that movie. Okay? And its name. So what we have here. Movie dictionary. So I'll print out this information. So let's print movie dictionary for movie number 2 and 3. So movie dictionary for 3. Run it. So movie 2 is Golden Eye, and movie 3 is 4 Rooms. So if we look at the mean score here, the mean average, they have 3.2 and 3.0. And if we look at the genre, they match each other in one genre. So they're somehow similar, right? They are somehow similar. So the higher the score, the less similar the movies are. Okay? So they are kind of close in terms of popularity, right? 3.2 and 3.0. But in terms of genre, they are a bit different. Okay? Okay. Now we have our code which computes the distance between two given movies, right? And you can do this with different movies. So you can compute values for different movies. For instance, movies 2 and
6 maybe. Run it, and then you can see the values and compare those. Now we are down to the last task, which is defining a function to calculate the KNN of our movies. Okay, so we will define a function, and that function will take some given movie ID and it will find the KNN value for us. That's what we'll look at in the next lecture. Thank you, everyone. Hello everyone, and welcome back. So in this lecture we'll look at the last task we have, which is to define a function that will calculate the KNN of our movies. Okay, so we'll define a function and it will take two attributes, movie ID and a K value, where K is what we want to calculate. In this case, the 10 movies closest to our movie. Okay, let's do that. So we'll be defining a function. Let me call it getNeighbors. Okay, getNeighbors, and it will take movie ID and then a K value. I'll create an empty list called, let's say, distances. Okay, and then we'll append to that empty list. Okay, so let's start. For movie in movie dictionary, so what we'll be doing is compute the distance between Toy Story, which is movie number 1, and all the other movies in the movie dictionary. Okay, and once we have that, we'll sort the results based on their distance score. So for movie in movie dictionary, we'll iterate through each movie that we have, and if it's a different movie than what we are looking for, it will compute the distance score from the previous result. Okay, that's what we will do. So for movie in movie dictionary, if the movie is not in movie ID, if our movie is not in our movie ID, so I'll write down the function and explain what I did. Okay, so it will calculate it will compare if movie is not in our movie ID. Okay, we'll have a distance variable and we'll compute that distance. So we have compute distance from our previous function here. So compute distance, and we'll pass the movie dictionary, and then we'll pass the movie ID and then the movie itself. So movie dictionary, and then we'll pass the movie itself. Okay, and then we'll append that to our distance list. So distances that append, and we'll pass movie and the distance. Okay, and then we'll sort out result. Okay, so distance that sort, and I'll pass a key operator, a key attribute. So I'll use the operator that item getter function, and that takes in
1 as an attribute. Okay. Now that I have that, I'll create another empty list. And once we have our empty neighbors list, we'll go through each individual k value. Since, for instance, since we are calculating the nearest 10 movies, it will go through each k value 1 through 10, right? And then we'll append the distances result in our neighbors list. Let's do that. Let's say for I in range k, neighbors that append, and then we'll pass the distances at index I. Okay, then we'll pass index 0. Good. And then we'll return our neighbors. Return neighbors. Now that we have this, we'll set our k value. So we'll set k to be 10, and then we'll find the 10's nearest neighbors using the getNeighbor method that we are going to define next. And then we'll iterate through all those 10 closest neighbors and compute the average rating from each neighbor, and this average rating will inform us our rating prediction. Let's do that. So k is equal to 10, and then so we'll start with an average rating of 0, and then we'll add to that. Okay, so neighbors, so we'll pass our getNeighbors function from 1 to our k value. Okay, and we'll iterate and append to that average rating. Okay, so for neighbors, in neighbors, you can say anything in this, it doesn't matter. I'm just doing a for loop. Okay, so for neighbors in neighbors, the average rating is equal to average rating plus our movie dictionary at the given neighbor. We have our average rating. Let me make this an underscore, that way it's more readable. Okay, so we have our average rating, which is equal to average rating plus our movie dictionary, and then we'll pass neighbors, neighbor, and then 3. Okay, and we'll finally print our movie dictionary at the given neighbor. Okay, so print, we have our movie dictionary, and then we'll pass our neighbor, index 0, and then let's also print some empty space, and we'll also be printing our movie dictionary to neighbor 3. Okay, neighbor and then 3, and we'll convert this into a string. Okay, and the average rating will be equal to the average rating divided by K, right? So average rating will be the average rating divided by K. Okay. So I'll convert K into float. So it gives us the result in float numbers. Okay, looks good. Now let's walk through what we did here. So our function getNeighbors takes a certain given movie ID and a K value, and it will calculate the KNN for us. We started by an empty distance list here, and what we did here is that we computed the distance between Toy Story and all the other movies in our movie dictionary and sort the results based on their distance score. So here, this if statement, it iterates through every movie we have, and then if it's a different movie than what we are looking for, it will compute the distance score from the previous one, and then it appends the result to the list of results that we have, and then it sorts that result. Next we have this for statement. So this will get the K-tap result, and then we set the K value to 10. So here in our example, we will find the 10's nearest neighbors using the get neighbors function that we introduced here, right? So we'll find the 10's nearest neighbors using the get neighbor function, and we iterate through all of this 10 nearest neighbors and compute the average rating from each neighbor. Okay, that's what we are doing here. And once we have the average rating, that average rating will inform us about our rating prediction for the movie we have, which is the Toy Story. Okay, so now let's run this and see the result. Okay. Oh, it says average rating is an invalid syntax. Okay, let's correct that. Okay, let's run it again. Okay, good. Okay, so now we have our 10 movies. The first one is Liar Liar, and then we have a mean value of 3.15. The second one is Aladdin with a value of 3.8, and then it goes on like that, right? And then we have Willy Wonka 3.6. That's for all our 10 movies. And we have George of the Jungle, Monty Python and the Holy Grail, Chocolate Factory. We have Home Alone. We have Aladdin. So it looks like we have a lot of kids movies and some comedy movies. And our Toy Story, it's more of like kids and comedy movie, so it looks like our KNN value seems to work, right? Since the 10's nearest movies in terms of popularity and rating, it's kids and comedy movies, so it looks like it seems to work. Now let's see what's the average rating of these 10 nearest neighbors to our Toy Story movie. Okay, so let me call the average rating. Okay, so for our average rating, we have a 3.34, right? We have 3.34. That's the average rating of all those 10 movies. Okay, do you guys remember what the rating was for our Toy Story? Let's call that from our movie dictionary. Let's see the average rating of Toy Story. So Toy Story has an average rating of 3.87, right? And by using our KNN calculation, we got an average rating of 3.34, which is not very different in rating, right? So that's how we can use the KNN. And one more thing. So for this average rating, we need to import the operator function. Okay, so let's import operator. Okay, so that's for this statement. Average rating is equal to average rating divided by the value of k. So you might have gotten, instead of 3.34, you might have gotten 33.44. Okay, in that case, don't forget to import the operator. Okay, I have imported this before, that's why I got this 3.34 instead of 33.4. So if you got 33.4, that's because we have an imported operator. Okay, so don't forget to do that. So that's how that's an example of the usage of KNN. Given a certain K value, we were able to calculate the rating of a movie. Okay, and you can also change the K values. In this example, we used a K value of 10. So you can change this K value to 5, to 15, to different K values, and see what you'll get. And you can also do the same calculation by choosing a different movie. So for this example, we chose Toy Story, the first movie, and you can change this to some other movie and then see if you can see what you will get using the KNN. Okay, so to summarize what we did in this project, we used the movie length data to calculate or predict the rating of a given movie by looking at 10 of the closest movies in terms of popularity and genre. Okay, and we did that by following these steps. And I left this question for you: how about the closest 15 movies, and what if we choose a different movie? Okay, so you can play around and work those problems. Okay, thank you everyone. Hello everyone and welcome. In this lecture, we look at finding optimal parameters for our model. So one challenge with different models is finding the optimal values for our parameters. For instance, if we are looking at k nearest neighbors, the challenge is finding the optimal k value. So in this lecture and the next lecture, we'll see how we can find out that optimal k value. We'll be working with our iris dataset. As usual, let's start by importing Pandas, Matplotlib as PLT.
I just copied this from one of the previous lectures. So if you haven't, please import this libraries and modules, or you can import them as we proceed. Okay, let's start by importing load iris from Scikit-Learn. Then I'll save our iris dataset in a variable iris. Next, I will save the iris data and target in two variables x and y, which will be our features and response. So x is equal to iris.data, that will be our features, and y is equal to iris.target, that will be our response. Now if we check our x and y, the shape of by calling the shape method, we can see that for our x, which is features, we have 150 by 4, right? We have 4 features: petal length, width, sepal length and width, and then 150 data sets. And then if we check the shape of our y, we'll see that we have 150. Next, let's divide our data set into training and testing sets for our model. We need to import the train test split library from Scikit-Learn. Let's do that. So from Scikit-Learn, that cross validation, will import train, test, and split. We'll first look at logistic regression model in trying to predict the iris species. So let's start by dividing our dataset into training and testing sets, and I'll save them in 4 variables: xtrain, xtest, ytrain, and ytest. We've seen that before. So xtrain, xtest, ytrain, and ytest, and that will be equal to train, test, and split. And we'll pass our features data, our response, and let's use a test size of 25%. The default is 30%, and let's use a random state of 3, for instance. Next, let's instantiate and train our model on this training datasets. So since we are using logistic regression, I'll just save it in a variable called logreg, and I'll set that to be equal to logistic regression. Okay, and once we have instantiated our logistic regression model, we'll call the fit method on it and pass our training datasets. Let's do that. So logreg.fit, and we pass xtrain and ytrain. Next, we can call the prediction model, the predict method on our fitted logistic regression model. Let's do that. So logreg model that predict, and then we'll be predicting on the testing set. So xtest, and let's save that in a variable called ypred. Next, we can call the accuracy score method to find out how well our logistic regression model did. So let's do that. Print metrics that accuracy score, and we pass our ytest and ypred datasets, ytest and then ypred. Let's import metrics. So I'll
import it here from Scikit-Learn, import matrix. Let's run this again. Okay, so we have an accuracy score of 100%. So our model can accurately predict the correct iris flower species. Okay, and see if we can come up with different accuracy scores by changing these values. For instance, let me make our test size 50% and random set of 5. Okay, let's run it. So by changing those different values, you'll get different accuracy scores for our model. So you can change, as an assignment for you, change the test size and random set values, and then see if you can come up with different accuracy scores for our logistic regression model. Okay. Next, let's look at k nearest neighbor. Okay, k and n. We'll consider a different number of neighbors and see the accuracy score for those. Let's look at that. Let's define our k nearest neighbor, k nearest classifier model first. And if you haven't imported, please import k neighbors classifier from Scikit-Learn. Okay, I'll save it in a variable called k nearest neighbor. So k neigh, k neighbors classifier. And I'll pass the n neighbors parameter. For instance, let's use 6. And let's fit our k nearest neighbor model using our training data sets, xtrain and ytrain. Next, let's make a prediction. We can call the predict method on our KNN model, and then we can make prediction on the testing sets. Let's do that. So KNN dot predict, and then we pass our x test, and let's save this in a variable called ypred. Next, we can print out the accuracy score of our model. Print matrix dot accuracy score, and we pass our y test and then ypred data. So we get an accuracy score of 96.7%. So our KNN model has a 96.7% accuracy in predicting the iris flower species when the number of neighbors value is 6 for a k value of 6. How about if this value was 2? Would we get a different result? So instead of 6, if I use 2, what value would I get? Let's check that. I get a 93% accuracy score when our number of neighbors k value is 2. Our model has a 93% accuracy
in predicting the correct iris flower species. So how can we know which k value will give us the highest accuracy score? Let's see that. So for this example, we'll take k values from 1 to 30. So we'll consider k values from 1 to 30 and see which k value is the best for our model. Let's check that out. Let's first create a list of this k values 1 through 30, and I'll save it in a variable called k value range, and I'll set that to be a list containing range from 1 to 30, and I'll create an empty scores list, and we'll use a for loop to go through each of this k value range values and then try to instantiate our k neighbors classifier model, and then we'll fit on our model, and finally we'll try to predict on the testing sets, and we'll append that accuracy score result in this empty list. Let's do that. So let's say for k value in k value range, let's instantiate our model. I'll save this in a variable knn. So k neighbors classifier, and we'll set the number of neighbors to k value. Number of neighbors will be equal to our k value. Next, let's fit our model knn.fit, and we'll pass our training data sets xtrain and ytrain. Next, let's predict by calling the predict method and passing our testing set, and we'll save that in a variable called ypred, and I'll set that to be knn.predict, and we pass our xtest, and finally we'll append the accuracy score to the scores list. So scores.append, we'll use the metrics accuracy score method, metrics.accuracy score, then we'll pass our ytest and then ypred. Now that we have this, we can simply print our scores. Let's do that. So print scores. So this will print out the accuracy score for each of our k value range. Here we see that we have the optimal accuracy score, which is 100% when k value is 7, 8, 9, and here when it's about 12, 13, 14, 15. So those are the optimal k values. Next, let's see how we can use this optimal search in grid search CV. Okay, this will allow us to define a grid of parameters, and those parameters will be searched by using the k-fold cross validation. It's called the grid search CV. Let's import it from Scikit-Learn. So from Scikit-Learn
that grid search will import grid search CV, and as what we did here, let's define a parameter value that we will use. So k value range will create a list of range 1 to 25, and next we'll create our parameter grid, and then we'll map each of the parameters to the value that we are going to search. Let's do that. So we'll use a dict method, dictionary, and then we'll pass number of neighbors as our k value range list. K value underscore range. Now if we print our parameter grid, we'll get a dictionary where the key is n neighbors and our value is a list containing this range of numbers. Let's check that. So if I print parameter grid, we get n neighbors and then our list. As we did with k neighbors classifier, let's first instantiate the grid search CV, and we'll save it in a variable called grid. So that will be equal to grid search CV, and we'll pass our KNN model and then the parameter grid that we just created, parameter grid, and then we'll pass cross validation fold of, let's say, 8. Then we can also pass a scoring parameter and we'll set that to accuracy. Next we can fit our grid by calling the fit method, and we'll pass x and y. Let's run it. Okay, we have all those attributes or parameters for our grid search CV. And the next thing we will do is this grid object has a method called, one method that it has is called grid score. And once we call that method, once we apply that grid score method on our grid object, it will print out the mean value, standard deviation, and our parameter number for each of this range of numbers. Let's do that. So grid scores, so here we have a list of named tuples with mean, standard deviation, and param of the parameters that we use. So for instance, when k value number of neighbors is 1, we have a mean result of 0.96. Remember, in this grid search CV, we have passed the cross validation fold of 8, so that's the mean of all those 8 runs. And to see each one of those separate, we can call a few methods. So I'll show you that. Let's analyze this first list of this first tuple here. So the first row, we'll analyze that. We can call certain methods like the parameters method and the CV validation score methods to see the score for each of the individual 8 runs, and we can also call the mean method to get the mean of all those 8 runs, which is 0.96. Let's do that, and we can simply print the result. So we can print our grid that we saw this method, grid scores. Then we pass for our first tuple we pass index 0, and then we call the parameters method on it. So that will just print out this part, and neighbors equal to 1. Okay, and neighbors equal to 1. And if we print the CV validation scores, so grid scores underscore index 0 dot CV validation scores, that will print out each of the individual 8 scores. 1, 2, 3, 4, 5, 6, 7, 8. Since we used CV is equal to 8. And then to print out the mean, we can simply pass the mean validation score method. So print grid scores index 0 dot mean underscore validation score. So that's our mean, 0.96, which is the same as what we got here. And we can do for any of those tuples. Let's see the 12's one. So we can simply change this value to 12 and run it. So, and the neighbors 13, then that's the individual cross validation score, and that's the mean, 97.3. So if we check here, we got the same result, 97.3. Okay, that's how we can print out and check each of the individual tuples, named tuples. If we want, we can also create a list of the mean scores only. We can do that by using list comprehension. And let me save it in a variable called grid mean scores. So for that, we'll say result that our mean validation score method, mean validation score, and then for result in grid scores method, right? Or if it makes sense, you can say mean result for mean result in our grid score method, and then we can simply print out this grid mean scores. Let's do that. So print grid mean scores. So that's the list of all the mean scores. Another thing we can also do is take this grid mean score values and then plot it against our individual k-range values. So here we have k-range of 1 to 25, and then we can print out the corresponding, we can plot that for each of our corresponding grid mean scores. Let's do that. So plt.plot, and we'll pass k value range for our x-axis, and then our y-axis will have our grid mean scores. Grid mean scores. And we can also label our x and y-axis by passing the x label and y label methods. So for our x label, we can say n neighbors or k value, and then our y-axis we can label it as the accuracy. Y label, we can just say accuracy. Let's run it. Okay, so here we have a plot. So when k value or our number of neighbors is what, around 11, 12, 13, we have the maximum score, right? So those are the maximum scores. And there are also some other methods to find out the best score for our parameter and our best estimator. Let me quickly show you that. We can simply print on our grid object, we can simply call the best score method on it, and that will print out the best score. And we can also print out the best parameter by using the best params method. Let's run those. So our best parameter is when our n neighbors or k value is 9, and then the score is 97.3%. And there's one more method called the estimator, so we can print that out. Grid.best estimator. Let's run it. So that's your best estimator for the k neighbors classifier. Okay, those are the params that will give you the best result. Algorithm auto, leaf size 30, that's the metrics. And JAPS 1, number of neighbors, k value is 9, and weights is uniform. Okay, so those are some of the methods that we can use to find out mean scores or the best values for the best optimal parameters. Okay, now let's look at searching more than one parameter at a time. So far we are only looking for one optimal parameter. Let's see if we can search for more than one parameter at a time. So for this example, we'll consider our k range values, and then we'll consider this weights. In this case is uniform. We will pass uniform, and there's another weight called distance. We'll pass both of those and then check which of the parameters will give us the optimal result. Let's do that. So let's define again our k value range. We'll create a list of range, same thing from 1 to 25. If you want, you can make it more or less, it doesn't matter. And I will define another parameter here, which is weights. Okay, I'll just call it weights param. Then we'll use uniform and distance. Okay, next we'll create our parameter grid by using a dictionary like we did here. So we'll create our parameter grid like we did here, but in this case we'll use both n neighbors and then weights. So those are our multiple parameters, so we'll use two parameters. Okay, so let's go ahead and map the parameter names to the values. Then we'll save it in a variable called parameter grid, param grid. So dictionary, and then we'll use n neighbors. N neighbors, we'll set it to be the k value range that we just created, and then we'll set the weights to be this weights parameter. Weights para. Good. Oh, let me run this. Okay, let's print our parameter grid. Okay, we have for n neighbors kn value, for weights kn value. Okay, those will be our two parameters. As we did before, the next thing we will do is we'll instantiate our grid search CV and then we'll fit that. So grid search CV, then we'll pass our KNN model, and then param grid. We'll use a CV value of, earlier we used 8, right? This time let's use 12. And again, you can use any CV value, 5, 4, 10, 20. Okay. And then for scoring, we'll pass accuracy. Let me save this in a variable called grid, and then we'll fit our grid search CV by calling the fit method, and we'll pass our x and y. Okay, we have our grid search CV value of 12, then param grid, weight, and all those attributes or parameters. As we did before, let's start by looking at the overall score by calling the grid score method. So grid scores. Good, we have a list of named tuples with mean, standard deviation, and then params as number of neighbors, k value, and weights. And to see one row, we can call the params method and the CV validation score method. Let me quickly show you that. So print grid scores, and then let's say if we want to see the first tuple, we'll pass index 0, and then we call the parameters method parameters. So the parameters are k value of 1 and weights is uniform. And next, let's print the cross validation, the CV validation scores. So print grid scores index 0 CV validation scores. So that will print out the score for each of the 12 runs. We use the CV value of 12, so we'll get 12 results. Let's run it. Okay, 1, 2, 3, 4, 5, 6, 12 results. And then we can call the min method on it to see the mean result. So instead of CV validation score, we'll call the mean validation score. So mean, so that's the mean, 96%. Okay, 96%. And you can change these values to different numbers and verify the results. Let's get the best parameter result by calling the best score methods and the best params method. So we'll print grid best params. So the best parameter is when k value is 12 and then when weight is uniform. How about the best score? Let's do that. Print grid we use the best scores method. The best score method, that's 98%. Okay, now that we have our best parameters, we'll use this best parameters to make our prediction of the iris plant species. Okay, hello everyone and welcome back. In the last lecture we saw that how to get our best parameters. Now that we have our best parameters for our k value and neighbors 12 and then weights is uniform, we can use those two parameters to make a prediction using our model. That's what we'll do next. We'll start by training our model using these parameters, our optimal parameter. Let's do that. So k neighbors classifier, then we'll pass our best parameter for number of neighbors, the k value, as 12, and weights is uniform. Good. We'll save this in a variable called knn. Next, we'll fit our model by using the fit method. So knn.fit, and then we'll pass our x and y datasets. And once we have that, we'll call the predict method on our fit model. So knn.predict, and we'll pass our testing set, and we'll save that in a variable called ypred. Once we have that, we can simply print out the accuracy score. Let's do that. So print matrix that accuracy score, and then we pass our ytest and ypred. Let's run it. Okay, here we have an accuracy of 100%. So our model can accurately predict the correct iris flower species 100% of the time. So we were able to achieve this 100% accuracy by first searching for the optimal parameters for our model, and then using those optimal parameters we are able to achieve 100% accuracy. Great. So without this optimal parameters, earlier we were getting 96%, 97%, and so on, right? So initially we were getting 96.7%, but by locating and finding out this optimal parameters, we were able to achieve 100% accuracy. So here we have seen that the methods we have seen so far, for instance, here we have to check out the grid scores for all of this, right? Probably these are so many rows, right? And at times this could be time consuming, and we might not be able to achieve those. It could be expensive. Imagine if we were doing this on thousands and thousands of sets of data. This could not be feasible, right? So in that case, with that, I want to introduce to you what is known as the randomized search CV. Randomized search CV. So in this case, this randomized search CV will search only a subset of all the parameters. So instead of going through, let's say if these are like 40, instead of going through this 40 rows, it will search for only a subset of the parameters, maybe 8, maybe 5, maybe 10, depending on the iteration numbers that you pass. So that's what we will see next. We'll start by importing the randomized search CV from Scikit-Learn. Let me go and see if I have imported it. Okay, I haven't. Let's import it. So from Scikit-Learn .grid search, we'll import randomized search CV. So we'll start by specifying our parameters, same as we did for specifying the parameter grid. So we'll use a dictionary method to map, and then we'll pass number of neighbors to be equal to our k value range, and then we have our weights. We'll set that to be equal to weights param. We saved it as weights param. Weights param. And I'll save this in a variable called parameter distribution. Next, let's pass parameters in our randomized search CV. So randomized search CV. We'll pass our KNN object, and then the parameter distribution we just created, param distribution. Let's say a cross validation fold of maybe 12. Scoring, we'll set it to be accuracy. Here we'll introduce a new attribute or parameter known as the number of iterations, n iter. Let's try 8, and let's pass a random state of 4 maybe. It's equal to 4. So this is the new parameter. By passing this number of iter parameter or attribute, we can control the number of searches our model will do. So if we pass n iter as 8, it will only do 8 searches. If we pass 20, it will do 20 searches, and so on. And let's save this in a variable called, let's say, run search, and we'll call the fit method on our run search. That fit, and we'll pass our x and y. Once we have that, we can call the grid scores method as we did before. So run search dot grid scores, and here is the grid score. So since we passed n ithers as number of iterations as 8, we get 8 search results, right? 1, 2, 3, 4, 5, 6, 7, 8. Similarly, if we pass n iter of 12, we'll get 12 results. You see the difference? Here we got 12, and then earlier we got so many results. That's how we can restrict this to a number of subsets by using this randomized search CV. Similar to what we did before, we can print out the best scores and best parameters by calling those methods on our run search object or model. Let's do that. So we can simply print run search, call the method best params, and we get our best params when number of neighbors is 12 and when weight is distance. And we can also print run search that best scores. That's the method, and we get a score of 97.3%. Okay, that's how we can restrict our search by using the randomized search CV. As an exercise for you, change this cross validation fold to a different number and run different iterations and see the results that you get. And based on those optimal parameters, fit those values, use those values to instantiate your model and then fit it and see what you will get. So same as what we did here. Okay, try that one out. So this concludes our lecture on searching for optimal parameters. We have gone through a few things. Just go through the lectures and try to see what we did. Overall, we tried to see how we can come up with optimal parameters for our models. We started looking at the iris dataset. We looked at a simple logistic regression model, and then we tried to incorporate the k-neighbors classifier and see if we could come up with a better result. And we did that by first finding the optimal parameter, and we looked at a few methods like grid score and parameters, cross validation scores, and so on. And we tried to visualize the best k value versus accuracy. And then we used the grid search CV to find out optimal parameters, more than one optimal parameter. In this case, we considered k value and weights parameter. So we tried to find out the two best optimal parameters for those two. And then we applied the randomized search CV concept to restrict our search, so that it only searches for a subset of the parameters instead of going through all of the parameters, which in some cases might not be feasible. Okay, thank you everyone, and I'll see you at the next lecture. Hello everyone, and welcome to the lecture on Introduction to Keras. Keras is a neural network library, and we will use this library to build different neural network models, and it runs on top of TensorFlow or Theano. And the official documentation for Keras is found at keras.io. You can read more about it or any specific details in the documentation here. As I mentioned, Keras is a high-level neural network library written in Python, and it runs on top of TensorFlow or Theano. We have already installed TensorFlow. The next thing we will do is install Keras. And to install Keras, we can use the pip install command. If you are using Windows, open up your command prompt, and for Mac Linux users, open up your terminal and simply type pip install Keras with upper K, and this should install the Keras library on your machine. So it might take a few seconds to install Keras, and once you finish your installation, restart your Jupyter notebook and follow along. And for our neural networks, we'll be working with a dataset known as the MNIST dataset. And this MNIST dataset consists of handwritten digits. And here is the URL where you'll find the MNIST database. It consists of 60,000 training datasets and 10,000 testing dataset samples. Okay, here I have the URL for the MNIST database of handwritten digits. It consists of 60,000 training and 10,000 testing sets that we can work with for neural networks. Okay, and here are the links for downloading the training and testing datasets. I have already done that and saved it in a certain path. I'll provide that path to you so you can use it for uploading. And you can read more about the MNIST database if you are interested here. Okay, I'll go back to my Jupyter notebook and start our lecture by importing the libraries that we need. As usual, we start by importing NumPy as NP, import Pandas as PD. We have our Matplotlib for plotting, and we have our magic function to see our plots in Jupyter notebook. Okay, and the next thing we need to import is Keras. For that, we simply type import and then Keras. Oh, this is lowercase, sorry. And once we import Keras, here you see we already have TensorFlow installed, so it will be using TensorFlow as its backend. And we also need to import the MNIST dataset from Keras dataset. For that, we simply say from keras.datasets import MNIST. Run it. Okay, now we are ready to use Keras. Let's start by uploading our MNIST datasets. And I have saved this. Our MNIST paths, as I have saved it in a file named mnist.pkl.gz. And this MNIST dataset is a very large dataset. Okay, what we'll do next is I have provided this for you, so you can simply put this package where your Jupyter Homebook is located, and we will simply load our MNIST dataset by using the load data method. Okay, let's do that next. So MNIST has a load data method, so we'll use that method to load our dataset. So simply call the load_data method and then pass the path for our dataset, which is MNIST_path. And we'll save the dataset in 4 variables: xtrain, ytrain, xtest, and ytest. Let's do that. So xtrain, ytrain, and then xtest, ytest. Okay, the reason why I'm using xtrain and then ytrain, so the training datasets followed by the testing datasets, is that here I mentioned that the training dataset has 60,000 samples and the testing dataset has 10,000 samples. So that way, by appropriately naming our variables here, these two variables will have 60,000 datasets, whereas the testing variables will have 10,000 datasets. Okay, and we'll confirm that later on by calling the length method on them. Oh, here we have an error. We don't need this quotation mark here. Let's run it again. So if you are running this for the first time, it might take a few seconds to upload. Okay, now that we have uploaded our dataset, let's check out the shape of our xtrain, ytrain, xtest, and ytest variables. Okay, let's start by checking the shape of xtrain. Run it. So here the shape is 60,000 by 28 by 28. What does this mean? As I mentioned, our training dataset consists of 60,000 samples, and each dataset consists of handwritten digits from 0 to 9. Okay, and each digit is 28 pixels by 28 pixels. Okay, so that's what this means, 28 by 28. We have 60,000 samples, and each sample or each digit is 28 by 28 pixels. Similarly, if we print the shape of our ytrain, it's a one-dimensional array, And let's check out the shape of xtest. Xtest.shape. Okay, and for our training datasets, we have 10,000 samples, and each sample is 28 by 28 pixels. Okay, and you can check out the shape of each of our datasets by simply using the type function and passing your variables. For instance, the type of xtest is a NumPy array. Similarly, if we check type of, let's say, ytest, this is type, it's a NumPy array. And we can also use the length function to find out the length of our training or testing datasets. For instance, we can find out the length of our y-train dataset. It's 60,000, whereas if we check the length of our y-test dataset, it will be 10,000. So these are some general information about our datasets. Next, let's check out some of our digits. Okay, let's explore some of our training datasets, for instance. So we have our xtrain, our training dataset, and let's check out the shape of the first digit. Let's see what the first digit looks like. Okay, so we'll index it 0, and this is what it looks like. It's an array, and we mentioned it's 28 by 28, right? So that's what we have here, 28 by 28, and most of them are zeros. Most of them are zeros, and wherever you have a number, that means that's where you'll see the digits. Later on, we'll have Matplotlib and draw a figure and explain what these numbers are. So this is in RGB. Again, in RGB, the numbers range from 0 to 255. Okay, so when you look at the figures, those will be the darker areas. The numbers will be the darker areas for our digits. Okay, so this is our array for the first record in our xtrain dataset. The shape of this array is 28 by 28. Okay, 28 rows by 28 columns. Similarly, you can check out any of your xtrain dataset by simply indexing. Let's say if I pass 34, you'll see an array 28 by 28. Okay, and that's what it looks like. I'll just comment this out, and next let's explore our y-train dataset. So our y-train will be, remember, these are the MNIST dataset consists of handwritten digits, right? 0 through 9. So our y-train dataset will consist of any one of these numbers. For instance, if we say y-train, and let's check out the first 5 results. So we have an array. The first number is 5 in our dataset, and then 0, and then 4, 1, 9. Okay, and if I say y-train, and if we try to check out the first 20 results, we have the digits 0 through 9. Okay, that's what our y-train dataset looks like. Similarly, we can check out what our y-test dataset looks like. Let's index the first 15 numbers. We have an array, and those are the first 15 digits in our y-test dataset. And we can also find out how many times a certain digit appears by using the NumPy's unique method. Let me show you an example. So we can say numpy.unique, and then we can pass our, let's check for our y-train dataset first. So we can say numpy.unique and our y-train, and we can pass another attribute known as return counts, and we can set that to true. That way it will tell us how many times a certain digit appears. So unique will only display digits 0 through 9, right? Those are the unique numbers. And the return counts will display how many times those unique digits appear in our Y-trained dataset. Let me run it and show you the result. So here we have our unique digits 0 through 9, and this is the number of occurrence of each digit in our Y-trained dataset. So on average, each digit appears 6,000 times, right? 6,000, 6,000. And if you add up all of these numbers, it should give you 60,000, right? That's our training dataset. And if we check out the unique number of occurrences for our Y-test dataset, Y-test, and then return counts, let's set it to true, we get the digits 0 through 9 and their occurrences here. So the occurrence for each is 1,000 times on average, right? Almost 1,000 times. And if you add up all these occurrences, it should give you 10,000, which is the number of our training dataset. Testing dataset. Okay, so we see that there is an even distribution of our digits in the training and testing datasets. Okay, that's important to remember. Now that we have some general information about our MNIST dataset, let's use Matplotlib to plot some of these digits. Okay, so let's first start by setting the figure size, plt.figure, and we'll pass the fig size attribute, and I'll set it to be, let's try 7 by 5 maybe. We can adjust this later on once we see what the figure looks like. Okay, and I'll set the axis to be fig.addSubplot, and then let's use 1 by 1 by 1, and we'll use the IamShow method for our image. So we'll set the image to be IamShow, and let's check out our X-trained dataset, and let's see the first digit in our X-trained dataset. And for color map, let's change the color map to gray. Okay, so we'll set the color map to gray. So we'll take our image and let's set interpolation to nearest, and then nearest. Finally, we can call the show method and see what it looks like. Okay, nice. So it looks like the first digit in our X-trained dataset is a 5, right? That looks like a 5. And remember, each image is 28 by 28 pixels, right? And here color map is gray. Let me copy this, paste it here. By default, we have the jet color map. So if I remove our color map, we'll get something that looks like this. So that's the default color map. That's the default color map, jet. And earlier, if you remember, when we check the X-trained dataset, we have a 28 by 28 array, right? So these numbers, wherever you see these numbers, 253, 242, 195, and so on, it represents these dark areas in our figure. Okay, so all the zeros indicate this area, whereas wherever you have a number, that's represented by this. That's what those numbers mean. And in a grayscale, it would be, the values would be between 0 and 1. So if you divide all of this by 255, the numbers will be between 0 and 1. Okay, and that's what will be represented here. Okay, close to 1 will be dark color and close to 0 will be white color. Okay, so let's check out some more figures. Let me copy that, paste it here, and let's check our Xtrain dataset at index 7. We have the number 3. And this time let's check our testing dataset. Let's see the first digit in our X test. It's 7. If I copy this, and if we try to see the fourth digit in our X test dataset, it's 0. So this is a general background information about our MNIST dataset. And in the next lecture, we'll start building models and try to calculate the accuracy of our models in predicting the digits. Thank you everyone, and see you at the next lecture. Hello everyone, and welcome to the lecture on multi-layer perceptron model. In this lecture, we'll build a sequential model for our MNIST dataset. As usual, we start by importing the libraries that we need. Import numpy as np, import pandas as pd, and let's import keras. Import keras. Next, we'll import MNIST from our keras datasets. So from keras.datasets, import MNIST. And next, we'll import our model, which we will use. It's called sequential model. And then we'll also need to import activation dense from our keras layers. That's what we'll do next. So from keras.models, import sequential. That's the model that we'll use. And from keras.layers, let's import dense layer, our activation function. Okay, so dense layer means everything in one layer, all the neurons in one layer is connected to all the neurons in the next layer. Okay, and this is the activation function that we'll use. And from, let's also import nputils. We'll use certain functions in nputils. So let's import it from keras.utils, import nputils. One good thing about keras is that it has certain functions that will help us build various kinds of models, and we can use those built-in functions to further analyze our models. Okay, and if you are interested in reading more about any of this, you can always check out the documentation, keras.io. Okay, here we'll be building a sequential model, and it's one kind of model where we have a linear stack of layers. Okay, let me go back to our Jupyter notebook. The first thing we'll do is load our datasets, our training and testing datasets. So our dataset, I have saved our dataset in this path, and then what we'll do is use the MNIST load data method to load our dataset. And as we saw before, I will save it in the following 4 variables: xtrain, ytrain, xtest, and ytest. Xtrain, ytrain, and then we have xtest, ytest. So MNIST dot load underscore data, and then we'll pass the path, which is mnist.pkl.gz. Oops, sorry, this should be mnist underscore path. Run it again. As I mentioned, we'll be using the sequential model, and this model takes all of the digits that we input as a single pixel. And if you remember, the shape of xtrain is 60,000 by 28 by 28, right? Xtrain.shape. But the sequential model does not accept 2 inputs for our pixel. So what we need to do is reshape this to make it a 1 pixel input. So instead of 28 by 28, we'll convert this to 784. Okay, that's the same as 28 times 28. Okay, let's reshape our datasets next. So for our X-train, we'll take our X-train dataset and then reshape it to make it 60,000 by 784. Okay, we have 60,000 by 784. And let's do the same for our X-test dataset. So we'll set X-test to be equal to X-test, and then we'll reshape it by calling the reshape method. And if you remember, the shape of X-test is 10,000 by 28 by 28. Print X-test.shape. It's 10,000 by 28 by 28. So each digit is 28 by 28 pixels. So instead of that, we'll pass 784. Okay, let's do that. 10,000 by 784. And again, our training dataset consists of 60,000 samples, and our testing dataset consists of 10,000 samples. Okay, now that we have reshaped our dataset, if we try to check, let's say X-test and then index 0, if we try to check the first digit in our X-test dataset, we have 784, right? So before it was 28 by 28. Now it's 784 and data type is integer. What we'll do next is convert this into a floating data type. And we can do that by using the asType method and then simply pass float. So let's take our X-train dataset and then we'll say X-train dot asType, and then we'll cast it into a floating number. So float 32, and let's do the same thing for our X-test dataset. X-test is equal to X-test, and then we'll call the asType method and then pass float. Okay. The next thing we'll do is convert our digits from RGB to a grayscale. Okay. For instance, if we check the first dataset in our X-train, you see here the values range from 0 to 255. What we'll do is we'll convert this into a grayscale by dividing each of the values by 255. That way, the numbers will be between 0 and 1. Okay, so let's do that. So we'll take our X-test and then divided by 255. And let's do the same thing for our X-train dataset. We'll take it and then divide it by 255. So now the value should be between 0 and 1. Okay, so let's check the first digit in our X-test dataset now. So here you see values between 0 and 1, right? 0.99. So this is a grayscale. That's why we first casted our dataset into a float. Otherwise, the values would have been either 0 or 1. Okay, now it's time to work with our dataset. We mentioned that we have 60,000 samples for training and then 10,000 for testing, right? So if we use the entire dataset for training and testing, especially for training, it will take us a long time to train all those 60,000 samples. So what we'll do instead is, instead of working on all of our 60,000 data, we can work on a certain subset of the 60,000 data. For instance, let's take the number 7. So we have almost close to 6,000 instances of the number 7, right? The number 7 appears 6,000, almost on average about 6,000 times in our training dataset. So what we'll do is we'll use all the number 7s from our dataset. That will be close to 6,000 records, and then we'll train our model on those 6,000 records. Okay, and we'll also randomly select 6,000 more samples which are not the number 7, and then we'll combine those two to train our model. And finally, we'll try to predict if our model can recognize if a number is 7 or not. Okay, so let's build a model to recognize if a given number is 7 or not. Hello everyone, and welcome back. Let's continue our discussion on building our model. Okay, we'll start by using NumPy's random seed method so that we get the same result every time we run our cells. So np.random.seed, I'll just pass 1111. You can pass any number you like. What I'll do next is take our y-test dataset and then distinguish all the numbers that are equal to 7. Okay, let's do that. We have our y-test dataset, and let's make a copy of that, and I'll save it in a variable y. Now I'll take my variable y and set it to be equal to 7. So that will be all of our y-test dataset where the value or digit is 7. And let me save that in another variable called y-test, and I'll set it to be equal to y, and that is double equal to 7. Now if we check our y-test object, let's see the first 8 numbers. So we have a boolean result of true, false, false, false. True means that number is 7. False means the number is not 7. Okay, so we need to convert this into an integer, right? So we'll have a result of either 0 or 1. So true will be 1 and false will be 0. Let's do that. We can do that by using the asType method, and then we'll pass integer. So we'll set our y-test dataset to be equal to y-test, and then we'll call the asType method on it and pass integer. Now if we check our y-test object, the result should be either 0 or 1. Let's see the first 8 numbers. So now we have 1, 0, 0, 1. And if we change this to, let's say 25, wherever we have a 7, it will be 1. And if the digit is not 7, it will be 0. And we can also use the NumPy's unique method that we have seen before. This will give us an array result of 0 or 1, 0 and 1 in our case, right? So np.unique, and then pass our y-test object. This will give us an array of 0 or 1. Okay, we're getting closer. Now let us select all of the digits where our output is 7. So what we'll do is we'll take our x-train dataset and we'll index it where our y-train dataset is equal to 7. Okay, and I'll save this in a variable called x_7. So that will be all the numbers which will be labeled 7. And let me make a copy of that, and let's do the same for our y-train dataset, and we'll save it in a variable called y7, and we'll set that to be equal to our y-train dataset where our y-train dataset is equal to 7. And let's make a copy of that also. So here we are selecting all the digits where our y-train dataset is equal to 7. So from our y-train dataset, we are selecting every instance where the digit is 7. And from our x-train dataset, we are selecting all our datasets where the y-train dataset is labeled 7. What we'll do next is select all of the instances where the value is 7 from our x-train dataset and from our
y-train dataset. So we'll take our x-train dataset and then index the y-train where the value is 7. So whenever the y-train dataset is labeled 7, we'll take that record of x-train. And for the y-train dataset, we'll simply set it to be equal to 7. And then take that. Okay, let's do that. So we have our x-train dataset and then we'll index y-train where y-train is equal to 7. And we'll save this in a variable called x7. Okay, and let's make a copy of that. That way we can distinguish it. And for y-train, we'll take our y-train dataset and index y-train where y-train is equal to 7. And let's make a copy of that and save it in a variable called y7. So this will select all the records where the value is 7 from our entire dataset. Okay, let's run that and let's check the shape of x7 in this case. What do you think the shape of x7 will be? So it will be two-dimensional and it will be about 6200 by 784, where 6200 is the number of records where y-train is labeled 7. Okay, let's run it and see. So 6265 by 784. And what do you think the value of y7 is? So if we call numpy's unique method and then pass y7, we'll see that we'll get an array consisting of only 7, right? So np.unique y7, this will give us an array of 7s because we have only selected records where y-train is equal to 7. Now that we have our x7 and y7, let's also select values where our output is not equal to 7. So we'll do the same thing that we did here, but when the value is not equal to 7. So that way we will select all the records where value is not 7. So to save time, I can copy that and let me rename this to x not 7. That will be x-train and then we'll index y-train. And this will be not equal to 7. Not equal to 7, we'll make a copy, and then for our y not 7, we'll take our y-train dataset and index y-train where y-train is not equal to 7. Okay, let's run this. Similarly, if we check the shape of x not 7, that shape will get, so we have 60,000 records, right? And this will give us about 60,000 minus 6,200 by 784. So about 53,800 by 784. And what do you think will be the unique value for y not 7? So if I run np.unique and pass y not 7, what will I get? Yes, so I'll get all the numbers except 7. So if I run this, I get 0, 1, 2, 3, 4, 5, 6, and then 8, 9. We have about 6,265 records where the value is 7. And what we'll do next is we'll generate a random. Let's generate 6,300 random numbers where the value is not equal to 7. So for that, random none 7 numbers from our dataset. For that, we'll use numpy's random integer method. So np.random.randint. Then we want to select 6,300 random numbers, right? Then we can simply pass the shape of x7, right? x7 that shape, that will be 6,265, right? And then we'll index, so the x7 that shape is 6,265 by 784. So we'll pass this shape and then pass the index 0, which will be the 6,265. So let's do that. We have x7 and then that shape. We'll pass the index 0 and let's pass 6,300. And then we can save this in a variable called random number of rows, or you can name it any variable that you like. What we'll do next is, so we have our x not 7 and then y not 7 variables, right?
So X07, we have 53,000 records, but out of that 53,735 records, we will only select 6,300 randomly. Okay, and we'll do the same for Y07. So let's do that. And then we'll save it in the same variable, X07 and Y07. So for X07, we'll take X07 and then simply pass the random number of rows that we define here. So random num rows. And let's do the same for Y07. Copy that, paste it here. I'll rename this to Y07. Then change this to Y07, random number of rows. Okay, now we have X7 and then X07, right? So we have about 6,200 and almost 6,300 numbers in X7, which are all sevens, and 6,300 numbers which are not 7, X07. So we need to combine both of them so that we can use them for training our model. That's what we'll do next. So we'll use numpy's append method and then simply pass X7 and then X07, X07. And let's save this in a variable called xtrain. So that will be our training dataset, our xtrain dataset, which will consist of X7 and X07. And one last thing we need to do is we need to reshape our xtrain. Okay, as you all remember, our sequential model, it accepts the digits as a single pixel. So right now, if we say xtrain.shape, let's print it, it's this much. So we need to reshape it. This doesn't make much sense. So what I will do is call the reshape method on xtrain.reshape. And then we'll take our X7 data shape and then call the shape method and take index 0, and then we'll add X07 dot shape index 0, and then we want to make the pixel to 784, right? And let's save this again in a variable xtrain. Now let's check the shape of our xtrain dataset. Print xtrain.shape. Run it. Okay. Now it looks good, right? 12,565 by 784. Again, where did this 12,565 came from? That's about 6,275 from here and almost 6,300 from X07. So when you add those, you have 12,565, and the shape is by 784. Okay, let's do the same thing for our Y-train dataset, right? We'll need to append it first. So we'll call numpy's append method and then pass Y7 and then Y07, Y07. And I'll save this in a variable called Y label 7. Okay, once I append it, what I will do next is let me rename this to Y label 7. Okay, so once I append my Y7 and Y07 dataset, we'll assign it to, we'll set this to be equal to our Y-train dataset as we did at the beginning. Then we'll simply set it to be equal to Y label 7, and we'll set that to be equal to 7, right? So this method will convert all the 7s to true and all the non-7 numbers to false. And then once we apply the asType method to this Y-train dataset and then cast it to an integer, we'll have the results 0 and 1. That's what I'm trying to do now. So let's run that and then let's convert our Y-train dataset into an integer. and then we'll set it to be equal to ytrain. So ytrain is equal to ytrain dot as type, and then we'll pass integer. Now if we call the np unique method on our ytrain dataset, we should get an array of 0 and 1. Let's run this. So we have an array of 0 and 1. And if we check our ytrain dataset, and then let's index up to 8. So we have 1 1 1 1. Okay, next let's check the shape of each of our datasets: xtrain, xtest, ytrain, and ytest datasets. Okay, let's print the shape of xtrain dot shape. Okay, we have 12,565 by 784. Good. Let's print the shape of our ytrain dot shape. We have 12,565. And finally, let's print the shape of our xtest data shape. We have 10,000 by 784. And finally, the shape of our ytest data shape, ytest dataset will be 10,000. 10,000. Okay, now our dataset is ready to be used for our model. So what we did in this lecture is redefine our dataset so that we have fewer number of training datasets. Instead of using 60,000, which will take a long time for our training dataset to train our model, we just considered a few of our datasets. We considered all of our datasets where the digit is equal to 7, which is about 6,200 results. And then we randomly selected additional 6,300 datasets where the digit is not equal to 7. So now we have a total of 12,565 records for training, and we'll use this for building a multi-layer perceptron. Thank you everyone, and see you at the next lecture. Hello everyone, and welcome back. In this lecture we'll build our multi-layer perceptron model. So first we'll build a simple multi-layer perceptron model, and then we'll add more layers to our simple model. I just copied this from our previous lecture. So these are the libraries that we need to import. In addition to that, we will also need to import stochastic gradient descent, SGD. So to import that from keras.optimizers, import SGD. Okay, now that we have imported the libraries that we need, we'll first need to define and specify some values that we'll use for our layers, for our various layers. We'll first start to initialize batch size and number of epochs for our perceptron. So we'll set the batch size to be equal to 128. So this will be the number of samples in each batch. Okay, and then another one is number of epoch, and we'll set that to be equal to 2. So this will be the number of times our model will update the weight. Okay, we'll see where all of this will be used when we build up our model. And for activation, we'll use the sigmoid activation function. So let's initialize that also. Activations is equal to sigmoid. Another value we need to initialize is number of classes, nb classes, and we'll set that to be equal to 2. So I'm using the same naming that you'll find in the Keras documentation. So I'm using those nb underscore epoch so that I use the same naming as in the document. So if you have to go and read more about it in the Keras documentation, it will be easier to identify. Okay, next we'll convert our ytest and ytrain classes into this number of classes. For that, we'll be using this nputils. It has a method known as toCategorical, and we'll use that to convert our ytrain and ytest into two classes, two forms. Let's do that. So for our ytrain, we'll save it in a variable called ytrain, and we'll take nputils, and then we'll apply the to categorical method. Then we'll pass our ytrain. This method accepts two attributes, two values, so we pass ytrain and number of classes, nb classes that we define here. And let's do the same for our ytest dataset. Ytest is equal to nputils to categorical. Let me change this to ytest and number of classes. Okay, next, for our model, we'll be using the sequential model. The sequential model is a very common model in Keras. So the first thing we need to do is instantiate our model, and we'll save our model in a variable called model. Then we simply type sequential. So now our model is instantiated. Once we instantiate our model, the next thing we do is add a dense layer, and then after that we will add an activation unit, and that activation unit will be sigmoid. Okay, so to add a layer, we simply call the method add. We'll use the method or function add on our model, and then we simply pass dense and pass the number of neurons for our first layer. Let's pass 512, and then this dense also accepts input shape, and then we'll set the input shape to be equal to 784. Remember, our sequential model accepts pixel of 784. That's what we did in the previous lecture. Now that we have added a dense layer, the next thing we need to do is add an activation unit of sigmoid. For that, we'll say model.add and then pass activation, and we'll use sigmoid for activation. Okay, so for this first sequential model, we'll keep our model very simple. So we have our input data, and then next what we'll define is our final output layer. Okay, so we'll first add a dense layer by calling the add method on our sequential model, and then this time we'll pass number of classes. So this is our final output layer, and then we will add an activation unit of softmax in this case. I'll explain why. So model.add, then activation, then pass softmax. So for our final layer, we only need to pass our number of classes. So when you pass nb classes, it means it's the final layer. So it will automatically take the output of your previous layer. Okay? So in your last layer, you don't need to pass number of neurons and then input shape like this. So once you specify this number of classes, it will automatically take the output from your previous layer. Okay? And for activation here, we used softmax. When we use softmax, it gives us a list of values between 0 and 1. And those values will add up to 1. That's why we use softmax for our final layer. Okay? So every time in our final layer, we'll use this softmax activation. What the softmax does is, it first adds your evidence and then converts that evidence into probability. So later on, we can calculate accuracy based on that probability. So in our example, we're trying to accurately predict if a digit is 7 or not, right? So what this softmax does is, it will check if your input is in the class 7 or not, and then it will convert that into probability. That's why we always use softmax as our final layer of activation. Next, we have our stochastic gradient descent, and we'll set it to be equal to SGD, and then pass, let's use a learning rate of 0.1 and use default values for the remaining parameters. Okay, so LR is learning rate, and if you don't pass it, it will also use the default value for the learning rate. And what we'll do next is we'll apply the compile method on our sequential model, and we do this before training. Okay, so this compile method is used to configure our learning process. Okay, let's do that. So we take our model and then apply the compile method. And this compile method, it takes 3 attributes. It takes loss, optimizer, and metrics. Okay, let's pass those attributes. We'll set the loss to be equal to categorical cross entropy. So this is one example of loss. You can read more about it in the documentation, but we have other kinds of loss like hinge loss and so on, but you can read more about it. Okay, and during our model, this is what we want to reduce. We want to reduce or minimize our loss. And then the second attribute is optimizer. So for optimizer, we'll pass our stochastic gradient descent, and this is our learning method. So we use this optimizer to minimize our loss. And then the last attribute is metrics. And for sequential methods, for sequential models, we want our metrics to be accuracy. So again, the compile method, this is compile. The compile method takes 3 attributes. It accepts 3 parameters: loss, optimizer, and metrics. And this is where we configure our learning process. Next, we'll use the fit method to train our model. So we'll call the fit model, the fit method on our sequential model, and then pass our training datasets, xtrain and ytrain. The other attributes the fit method accepts are number of epochs, batch size, verbose, validation data, and so on. So let's pass those one by one. So we'll set the batch size to be equal to batch size that we defined at the beginning. And we'll set the number of epochs to be here, this number of epochs. So we have batch size equal to batch size, number of epochs, and then there's another attribute known as verbose, and we'll set that to be equal to 1. And the last thing we need to pass is our validation data. There's an attribute known as validation data, and we'll be validating what? Our X-test and Y-test datasets, right? Okay, once we configure the learning process and once we train our sequential model with our X-train and Y-train datasets, so this will take some time. So here we have train on 12,565 samples, validate on 10,000 samples, which is our validation data, right? And our number of epochs is 2, right? So our first epoch, during our first epoch, loss was 0.56 and accuracy was what, 84.6%. And during our second run, our loss is 0.41 and accuracy is 92%. So this is the function of optimizer. The optimizer tries to reduce the loss. So as you see here in the second epoch, the loss is less. And let me show you the method that we will use for evaluating our model. It's called the evaluate method. We simply call the evaluate method on our model and then pass your X-test and Y-test datasets, and we'll set the verbose to be equal to 0. And we can save this in a variable called score. Okay, so if we print score, we get 2 values. So what are these 2 values? This tells us the entropy and this tells us the accuracy. So we can index and print this separate. So we can say print score index 0, run it, and then we can also print score index 1. Or we can even add, let's say, accuracy and then score 1. So we have an accuracy of 94.36%. And this first score tells us what the entropy is. Okay, so this is our first simple multi-layer perceptron. Okay, let's summarize what we did in this lecture. Once we imported the libraries that we need, we instantiated some values like batch size, number of epochs, activations, and number of classes. And then we converted our ytrain and ytest into binary categories. After that, we instantiated our sequential model. And once we instantiated our model, we added a dense layer, and then we added an activation unit of sigmoid. And for our dense layer, it accepts two values. The first value is number of neurons, and the second value is your input shape. And then we added another dense layer, which is our final output layer, and we passed number of classes. So when you specify this, it means it will automatically take the output from your previous layer. And for our final output layer, we use an activation unit of softmax. And we say that softmax converts your evidence into probability so that it can add up to 1. That way we can easily calculate or predict accuracy, right? And then we defined our stochastic gradient descent for our optimizer. And we called the compile method on our model, which we used to configure the learning process of our model. And this compile method, it accepts 3 parameters: loss, optimizer, and metrics. And for optimizer, we use SGD as a learning method, and we use this optimizer to minimize the loss. And for our sequential model, we use accuracy as metrics. And finally, we call the fit method to train our model with the training datasets. And here we passed additional parameters like batch size, number of epochs, and then we were validating it against our X-test and Y-test. So later on, when we call the evaluate method on our model, we got an accuracy of 94.4%. So this is a simple example. In the next lecture, we'll look at some more examples and see the result that we get when we increase, let's say, the number of epochs, or change the batch size to a bigger number or a smaller number, and what if we add more hidden layers. And again, check out the documentation on Keras about sequential model. You can read more about it there. Okay, thank you everyone, and see you at the next lecture. Hello everyone, and welcome back. In this lecture, we'll look at a multi-layer perceptron with more hidden layers. In the previous lecture, we looked at a simple model where we had an input layer and an output layer, and we considered these parameters for batch size, number of epochs, and number of classes. And we came up with an accuracy of about 94%. As an exercise for you, you can increase this number of epochs to, let's say, 5 or 10. And you can also increase or decrease the batch size and see the result that you get. What we'll do in this lecture is add some more layers, some more hidden layers. And we'll use the same data that we used in our previous lecture. Okay, we'll start by importing the libraries that we need. I copied this from our previous lecture. So let me run the cell
And then we have our MNIST dataset, paths, our X-train, Y-train, X-test, and Y-test. We have seen this before. We took our entire dataset and considered the digit 7, and we selected all the values where the number is 7. We had about 6,200 of those, and we randomly selected 6,300 non-7 numbers, and we combined those to make our training dataset so that we can use them to train our model. Okay, so you have seen this before. I just put everything in a single cell. So I'll run it now. Okay, now back to our lecture. What we'll do for our multi-layer perceptron is change the byte size to 256 and the number of epochs to 10. We'll use the same sigmoid activation, and these are all copied from our previous lecture. So I'm changing the few of the parameters. As usual, we start by instantiating our sequential model, and once we instantiate our model, we add a dense layer. Here our dense layer has 512 neurons and the input shape is 784, and then we add an activation unit of sigmoid. So this is our input layer or input, and this is our output layer, right? Output layer. What we'll do for this lecture is add some more hidden layers. Okay, so let's add a couple of hidden layers. I'll call the first one first hidden layer. So first hidden layer. So for adding one or more hidden layers, we follow the same process. We start out by adding a dense layer, and then we'll add an activation unit of sigmoid. Let's do that. So model.add, we add our dense layer and then specify the number of neurons. Let's say 512, and then we add our activation unit, which is sigmoid. Model.add, and then activation, and pass sigmoid. So for this first hidden layer, it will take the output of your previous layer, which in this case is this, our input. So the output of this input will be taken as an input by this first hidden layer. And then the output of this first hidden layer will be an input for your next layer. So it goes on like that. And if I want to add another hidden layer, let me call it second hidden layer. I follow the same steps. Model.add, we add a dense layer. Let's use 512 neurons, and then we specify our activation by calling the model.add method and then pass activation, and we'll use sigmoid for activation. So the output of our second hidden layer will be an input for your next layer. So this is a multi-layer perceptron with two hidden layers. We have our input, output, and any layers in between will be your hidden layers, one or more hidden layers. And again, for your output layer, we specified softmax. We use softmax because we want to convert our evidence into probability, and we do that by using softmax, okay, as it gives us a list of values between 0 and 1, and that can add up to 1. Okay, that's why we always use softmax as our final output layer. And for our output layer, we specify number of classes, and it will automatically take the output from your previous layer. After that, we call our compile method, and this is used to configure the learning process. And as we mentioned before, this compile method takes 3 parameters: loss, optimizer, and metrics. And optimizer is what we use for learning. This is the learning method, and we use this optimizer to minimize the loss. And for sequential models, we want our metrics to be accurate. So most of the steps are
the same as in our previous lecture. We just added a couple more hidden layers. So let me run the cell, and then we'll call the fit method to train our model with our training datasets, and we pass a few more parameters: batch size, number of epochs. Our batch size is 256, number of epochs is 10, verbose, and we'll be validating the X test and Y test. So let's run the cell. So the first epoch is running, and this might take a few seconds. So about 4 seconds for the first epoch. And here you see the loss, 6985, and accuracy. So as we go through successive runs, we are trying to minimize the loss here. Okay, that's what the optimizer tries to do. So let's give it some time. So we have 2 more epochs to run. Okay, it has finished running. What we'll do next is call the evaluate method to evaluate our accuracy. Let's do that. So model.evaluate, and we'll pass our X test and Y test datasets, and we'll set the verbose to be equal to 0, and let's save this in a variable called score, and let's print out our score. Okay, score will index 0. So this is the same thing that we did in our previous lecture. Score. Okay, let's run this. So here we have, let me change this to accuracy instead of score. Accuracy, run it again. Okay, here we have an accuracy of 89.7%. If you remember in our previous lecture, we had an accuracy of about 94%, right? But here we have accuracy of almost 90%. Why do you think the accuracy is lower? Even if we put more hidden layers, we increased the number of epochs and we added 2 more hidden layers. But despite all that, we had a lower accuracy. So one challenge with neural networks is a condition known as overfitting. That's one challenge we have in neural networks. And as you see here, our model has 784 inputs, right? And it gets connected to 512 neurons in your next layer. And each of these 512 neurons get connected to another 512 neurons in your next layer. And those finally get connected to your output layer. So at the end, you'll have so many parameters in your network, right? And that condition is known as overfitting. Again, you have 784 inputs and 512 neurons in your input layer, and you multiply that, you get your weight, and that gets connected to your next layer, and your next layer has 512 neurons, and they multiply that by the weight from your previous input, and that gets connected to your next layer. So the output of your first hidden layer will be the input for your next layer, and when you multiply that by the number of neurons, you get the weight, and that connection goes on and on. So you have so many parameters in the network, right? At least 1 million. When you multiply the weight, and then that gets transferred to your next layer and acts as an input for your next layer, and you multiply that by your neurons, and so the weight keeps adding and adding, and you'll have so many parameters, and this leads to a condition known as overfitting. And that takes us to our next lecture. We'll look at what is known as regularization, and this is a technique we use to reduce overfitting. We'll look at one method of regularization known as dropout. So keep in mind there is a condition known as overfitting, which is a challenge in neural networks. So in this lecture, we added 2 hidden layers, right? And I wanted to show you that. As an exercise for you, what you can do is only add 1 hidden layer. So remove the second hidden layer and work with only one hidden layer, so that you'll have an input layer, your hidden layer, and an output layer. And change this parameters batch size to maybe 128, or you can keep it the same, and change the number of epochs to 5 or 15 and compare the result you get with what we did in this lecture. Okay, thank you everyone, and see you at the next lecture. And welcome. In this lecture, we'll look at regularization. Regularization is a technique that we use to prevent or to overcome overfitting. We mentioned that overfitting is one challenge that we have in neural networks. That's because we have so many parameters in neural networks. In the example we saw in the previous lecture, we had 784 inputs with 512 neurons. So the weight of that gets transferred or serves as an input to your next layer, and that gets connected to 512 neurons, and the weight of that gets transferred to the next layer, and you easily have at least 1,000,000 parameters when you multiply all of that. So to overcome that, we'll use a technique known as dropout. There are a few regularization techniques, but the one we'll look at in this lecture is called dropout. Okay, to explain dropout, let's consider the following example. Let's say we have 100 neurons. So if I make a range here, okay, 100 is a lot. Let's consider 20 just for this example. Let's say we have 20 neurons. So what happens while we train our model is that, so without any dropout, if we consider this example, out of this 20 neurons, each neuron has a chance to be used for training or not, right? So the availability of a single neuron for training or not is 50-50. So in a normal situation without any dropouts, 50% of these neurons can be used for training, whereas the other person cannot be used for training, right? There's a 50-50 chance. And what dropout does is that it will drop some of these neurons. These are also called nodes. You might hear of nodes or neurons. So dropout will drop some of these neurons. That way there won't be any connection with those neurons, and we cannot use those neurons for training. So when the output from a previous layer goes or serves as an input for the next layer, and if the next layer has, let's say, 20 neurons, some of these neurons will be dropped out, so they won't be connected to your previous output. Okay, and using that mechanism, our model will handle noise much more efficiently. Okay, and we specify dropouts by probability. We can specify, let's say, 20% or 30%. If we use 20%, that's 0.2. What it does is, so 20% of 20 is 4. These neurons will be dropped out, so they won't be connected to your previous input. So only the remaining neurons will be used for training. So by using this mechanism, we can handle noise much more efficient. Okay, that's what dropout means briefly, and you can read more about it in the documentation. So we have used 512 neurons, right? And if you consider 20% of that, that's about 102 or 103, around that. So 100 neurons will be dropped out, right? And they won't be used for connection, so there won't be any connection with those 100 neurons. So only 400 neurons will be available for training. Okay, and that's how dropout works in short. Okay, let's go back to our example. So I copied this from our previous lecture. For dropout, we also need to import dropout from keras.layers. So add this line also from keras.layers import dropout. I'll run the cell, and I copied this from our previous lecture to save some time. So it's the same thing, I don't do anything else. I just copied this. So that's our data, right? We are trying to predict if a number is 7 or not. And here we have our initial numbers for byte size. Let's use 256, and number of epochs, let's use 10 or 15, it doesn't matter. And for activation we have sigmoid. We have our model, sequential model. So this is our, let me comment it, input layer, right? This is our input layer, and this will be our output layer. Output layer. So where do we add our dropout? How do we know, what to drop? Okay, as usual, we start by defining our model, our sequential model, and then we'll add a dense layer and specify our input shape, and then we'll add an activation unit of sigmoid, and after that we'll add our dropout. We just add a layer called dropout, and in that layer we'll specify the probability. Okay, let's do that. So we have our model, and then we'll call add. We'll be adding a dropout layer, dropout, and then specify your probability. Let's use a probability of 23%. So 23% of your neurons will be dropped out. Okay, so same scenario like this. Okay, that's where you add your dropout layer. Once you add your dense layer and then specify your activation unit of sigmoid, you'll add your dropout layer. So this is a single dropout layer, a simple perceptron, and what we'll do is we'll add some more layers. Okay, I'll add two more layers, two more hidden layers. So let's call the first one first hidden layer, and we have seen this in the previous lecture. We'll first add a dense layer, and then let's use 512 neurons, and next you add your activation unit of sigmoid, model.add activation, and then pass sigmoid. Okay, and after that you add your dropout layer, model.add, and then dropout. So we'll pass a probability of 23%. That way we will drop out 23% of your neurons. Let's add one more layer, and we'll call this second hidden layer. So everything is the same. So we have our model.add. We'll add a dense layer with 512 neurons, and then we add our activation unit of sigmoid, activation, and then pass sigmoid, and finally we add our dropout layer and specify the probability. Okay, so that should be good. Okay, and finally we have our output layer and activation unit of softmax, so that our probabilities can add up to 1. And we call the compile method to configure the learning process. As I mentioned, it takes 3 parameters: loss, optimizer, and metrics, and we use the optimizer to minimize our loss. And finally we call the fit model, so that our model can train on the training datasets. So for our dropout, we add a dropout layer after our activation unit of sigmoid, and then if we have more hidden layers, we do the same thing by specifying the probability of dropouts. Okay. Now let's run the cell and see our result. Now it says name model is not defined. Here it's model. Let me correct that and run it again. Let's run our next cell. Okay, now let's run our model.fit cell. Let me run this. So it will take some time. It has 10 epochs. Now it's running the first epoch. Loss is 73%. So every time we do additional epoch runs, we're trying to minimize the loss. And that's accomplished by our optimizer. Okay, so this might take about 45 seconds, it looks like. Okay, so now it has completed running. And let's run our model.evaluate cell. So this is just to print out our accuracy. Let me run this. Here we have an accuracy of 94.7%, right? So a little bit better accuracy. If you remember, our simple multi-layer perceptron model with just an input and an output layer, we had about a 94% accuracy. Now we have a 94.7% accuracy, which is much better than the accuracy that we had in the previous lecture, which was about 89% without any dropout layers. So with a dropout layer, now we have a better accuracy. And dropout is one regularization technique that we use to overcome the issue of overfitting, the challenge of overfitting. Okay? And as I mentioned, for your dropout, you specify the probability of your dropout. In this example, we used 23%. For you, as an exercise for you, you can try out different probability numbers for your dropout. Let's say try out 30% or 50% of your dropout and see what result you get. You can also add some more additional layers, or you can take out one of these layers and just try out to build a model with an input, one hidden layer, and an output layer, and compare your results. One thing to notice, if you have more and more hidden layers, it will take more time to run your model. And also, if you increase your number of epochs, let's say if you make this 25, it will take some more time. And also that will also depend on the speed of your computer and also whether you are using CPU or GPU. If you are running on a GPU, it will run much faster. So those are some other things to consider while building your model. Okay? If it's taking too much time, it could be one of the reasons that I mentioned. And again, dropout is just one technique of regularization. There are other regularization techniques. Another one is called L2 regularizer. I won't go into that, but just wanted to let you know that there are other regularization techniques. Okay? And you can read more about it or in depth in the documentation. Okay? So just an important note, in neural networks, there's a challenge of overfitting. So while you are building your model, think of all those parameters. Think of different ways to minimize your parameters and how it will affect your model. Okay? Thank you, everyone.